sobie mam komputer.
Czekaj, ty już to przerzuciłeś, czy nie?
Nie, to jest jego. To jest Niemca komputer.
No tak, ale ty tutaj...
Nie, to jest do, żeby mógł slajdy zmieniać w tym. To jest
Wow.
do zmiany slajdów.
Okej.
I can just use that. That's the adapter.
Okej.
Wrzuć w moją prezentację na swojego laptopa.
Let me see.
O, Piotr.
HD, but USB-C to HDMI.
Okay, where is this?
Piotr,
O, Piotr. O.
Umów zgodnie z tymi, wiesz, zgodnie z datami.
Ale zobacz, to jest... Show me...
Ja głupoty gada. Otóż zgodnie z date modified. Date modified. Kliknij na date modified. Kliknij tu. Date modified.
Aha.
Tu na górze. Nie, no co ty robisz?
No to weź, nie wiem.
Tutaj, jak klikniesz na to. I tu. To.
Okay. No dobra, no. Czekaj, to. Okej, dobra, no to już.
Yeah, the sound from that microphone is good. Merrick?
Yes, yes.
Yeah, the sound from that microphone is good.
Okej. Co? Trzeba chyba najpierw per, trzeba najpierw zrobić, nie?
Co?
Trzeba zrobić ten per najpierw. Tutaj.
So,
Aha. Per.
can you see?
Okay, just one second. Okay. Connect.
It's in Discover now. So now, let's see. Wait, I will see if we...
We need to pay Pietra danger pay. He could be our next skull fracture. Can I hear?
John, now is good?
Yeah, now that's good.
Good?
That's good. The sound is good. And the PowerPoint's hooked up. Do you want to make the PowerPoint bigger? It's small now. The PowerPoint.
Let's start there.
Okay. I think it's already 8, and today we have a busy schedule. And yesterday we didn't have the keynote speaker, so we could be much more relaxed with the timing. Today we have more time constraints, so I think I will just give a voice to the chair now. So each talk should be 15 minutes, and then if it would be more, then there will be no discussion. Discussion can be during the coffee break, so we can still have the presenters here and then have a discussion. But if someone will be less than 15 minutes, then definitely will be time to make some questions. So please, chairs.
Okay, Mir.
Hello, Merrick?
So I'm Peter Van
Merrick, hello, hello.
Kennedy Krieger Institute, and next to me is Ali Fatemi from Kennedy Krieger Institute and Johns Hopkins University. And we have an interesting session, I think, with all different topics. And the first speaker is Dr. Peter Ludewig from University of Hamburg, Eppendorf, Germany, and he's going to talk about magnetic particle imaging for neurological applications.
Good morning. Thank you very much again for the invitation this year. 8 in the morning, I'm tired, you're tired. So how can I get your attention? I think I have a solution for that. I'd like to introduce you to Dr. Hip-Hop. So why did I show you this? Because we have done a lot of advances last year, but still we are not really good in treating stroke. Lies on the key, which works really good, but still we have more than 50% severely disabled after stroke. So we need more solutions, and one simple thing is always prevention and education that we sometimes miss, because I still have some patients coming after 3 days after the stroke, and you can have so many good catheters when you not have those patients. And just to remember, in stroke, 2 million neurons die every minute. So time is the most important thing. So in our clinic, we are trying desperately to improve stroke therapy, and these are our main big groups. Our chief of the department, Radiology, is interested in reorganization of brain after stroke. Then we have the group of Götz Mahler, probably know him from the Wake Up study he published last year. And we have one preclinical lab I'm working with Professor Magnus, and our background is pure neuroimmunology. Our landmark paper published in 2009, where we described the post-ischemic inflammation in stroke animals. And this was our main model. It's flow cytometry to really describe the influx of leukocytes in great detail in animals. Nowadays, we're doing much more things, not only neuroimmunology. And a few years ago, in 2015, I met Tobias Knopf. And Tobias Knopf was talking about magnetic particle imaging, and I was talking about stroke. I had no idea what he was talking about. He had no idea what I was talking about stroke, but it went out quite well. So today I try to introduce you to magnetic particle imaging and show you some neurological application using today. I will give an outlook what the future of MPI might be in the clinic. Magnetic particle imaging was actually invented in Hamburg in 2005 by Bernhard Gleich and Jürgen Weizenegger. And they were thinking, how can we improve the existing imaging modalities? And they especially want to improve spatial resolution and temporal resolution. And they came up with magnetic particle imaging. So it's like MRI, it's a tomographic imaging method that only detects superparamagnetic nanoparticles. That's a superparamagnetic nanoparticle. You have an iron core, you have different surfaces coating, and the MPIs cannot only detect those particles. The imaging modality, this can be advantage or disadvantage, we will see later. So how does it work? We have different oscillating magnetic fields. So we have a dry field, and now we have here the particles. The arrows are particles, and if you move this dry field around, all the particles are moving, and this makes a signal, but we don't have any spatial encoding. For that, we need another field, so-called fish coil, and this is magnet in Maxwell configuration. And now you can see only in this field-free point the particles are moving. And this now makes the other particles are not moving anymore. And this makes the spatial encoding And here's some simulation how it looks like. So this is the P3 point moved by the selection field, and this P3 point crosses a particle like here. This makes a signal which we can make a picture out of it. And this is what magnetic particle imaging looks like. If you inject the fields into the animal, you don't see a lot. So normally we have to get some anatomical information with CT and MRI. And what you see here was one of the first pictures we made, where we injected the seals with a wave tail of a mouse, and you can see that color more or less in real time. Now, what's the advantage of MPI compared to other imaging techniques? It's really fast. Temporal resolution is like 21.5 milliseconds. It's really fast compared to other imaging methods. And spatial resolution in theory should be less than 1 millimeter. So we thought this might be an excellent imaging technique for vascular real-time imaging. And this is the scanner we have now at our university. It's the first preclinical commercial scanner from Bruker. And this is more or less the evolution of the scanners over the years. And this was our first experiment we did. This is our experimental setup. We used the temporal occlusion of the MCA with the silicon filament, and we used stroke on our animals. And then we did imaging. Here's a video how it looks like. So one side here is occluded. This one side is open, and we inject the tracer. And now you can see really a good signal in the
Thanks a lot. I'd like to thank the organizers for giving me this opportunity to talk to you all about CEST MRI and why it might be useful for image-guided neurosurgery. So first, I'd like to talk a little bit about MRI contrast agents and what they're good for. So MRI is based in general on detecting water and displays excellent delineation between different types of soft tissue. However, about 33% of scans require injecting compounds, which are called contrast agents. So by definition, a contrast agent is some sort of entity introduced into an anatomical region to alter the MRI signal. And since the MRI signal is based on water, because of its high concentration in tissue, they usually act on water to alter the water proton signal. And so what a lot of you all been using has been T1-based MRI contrast agents. So just to show a typical MRI image, here's a T2 image, T1 image, you see some sort of abnormal features in this region. However, after injecting gadolinium, you can see quite nicely this tumor highlight. And so gadolinium contrast agents are excellent for highlighting altered blood perfusion changes found in tumors or MS lesions. However, gadolinium is actually a member of the lanthanides and toxic in its free form, so that's not always desirable. So what I'm going to be talking about today is CEST imaging, or chemical exchange saturation transfer. So this is an imaging that was introduced back in about 2000 at NIH, and it relies on a very different mechanism. In this case, for CEST, you have these compounds which have exchangeable protons, such as this OH proton here. And in order to highlight these, what you do is you place a saturation pulse in front of your imaging sequence, and that saturation pulse destroys the magnetization on these solute protons. And through this rapid chemical exchange with water, this saturation pulse's influence migrates from the protons on the solute to destroy a lot of the water signal. And if the exchange is fast enough, you can see a large number of a large amount of signal loss from one single proton spread over many waters based on this rapid exchange. So it's a mechanism which allows an amplification of the signal on this compound onto water through addition of a saturation pulse. It's a growing field. Since 2000, the term being coined in NIH. There's been a large number of citations each year. People have applied it to stroke. At our site, it was applied to brain tumors. We, at our site, did the first patient studies back in 2006 using CEST imaging. And then reporter genes were reported, and then one of the first really nice uses of this technology for discriminating brain tumor recurrence from radiation-induced necrosis was found in 2011. And we now have a textbook on this technology. And in addition, Philips Healthcare coupled with our site with Peter Van Zyl and Jinyan Zhou to produce these nice CEST-optimized 3T MRI scanners for patients. And so what they did is they created this design where you can hop between one channel and another and produce very long saturation pulse to have a maximum efficient signal loss transferred to water. So this was nice. So why would we actually care about this technology for image-guided neurosurgery? Well, one of the real nice features of this technology is that you can encode color to discriminate between agents. So again, you have this solute proton here, place a saturation pulse on that, see the signal loss transferred to water. So what you can do is you can have agents with different solute protons, which are rapid exchange. So as you sweep the saturation pulse across the spectrum, you can see the signal losses introduced by all these different types of protons. And so we showed back in 2008 that you can use this to create MRI-based color maps to discriminate between the various different types of contrast agents. So we think this should be useful for image-guided surgery, image-guided chemotherapy to show where one agent migrated compared to another. You can imagine that optical imaging does this quite well. This is just an example of all the different types of colors. And with optical imaging, you can produce these very nice, beautiful, multicolored contrast maps. So this is kind of where we were trying to hope to go for image-guided intervention. So I'd like to mention what are the optimal properties for CEST agents at 3T, because we'd like to really create agents based on this features. So we did a series of block simulations defined based on applying a 4 microtesla saturation pulse. And what we saw is about the optimal protons should have something like a 5 to 12 ppm chemical shift, and their exchange rates should be on the order of 800 times per second, 1,000 times per second, to really get maximum detection capabilities. And so we then found actually a very nice platform which we could use to create these types of optimal protons. You might recognize this. This is actually salicylic acid. So this is something that's been used to treat pain for a very long time. In fact, as far back as 2,400 years ago, people have administered this to patients. So how does this particular type of agent work? Well, if you look at a phenyl OH, unfortunately, the exchange is extremely rapid with water. And so it doesn't really have the right properties to detect this proton. However, if you apply, if you attach a hydrogen bonding site right proximal to this OH proton, it introduces a shyness and slows the exchange rate down to be appropriate for CEST. And then because this scaffold has all these basically 4 additional sites, you can tune the properties of this OH proton to move it around and to alter the exchange rate quite well. So this is a very nice tunable platform. And of course, it's also based on a natural compound this is found in willow bark. So we looked at a few different types of alterations. What we noticed is if we altered this 4 or 5 position, we could move the proton from 10 ppm all the way down to 8.5 ppm, just changing the substitution at these 2 sites. We also noticed that the exchange was particularly sensitive to this R6 site. We can migrate it from 30 times per second all the way up to 4,000 times per second. Likewise, the exchange rate is very sensitive to the substitution at this site. So then we created these multiple color compounds, which have these nice tunable shifts across the spectrum. And so we published this 2 years ago. So how would we use these types of agents for guiding drug delivery? Again, we can use these to highlight where therapeutic agents are delivered, and we want to use this multicolor feature. And so I'll first show you how we might apply this to intra-arterial delivery. So again, intra-arterial delivery, I don't really have to probably introduce this to the audience. We inject mannitol to open the blood-brain barrier, inject our CEST contrast agent, and then collect our images. This is just a pre-infusion image, and this is just what we saw with iron oxide. So you can see that very big altered signal region, which then recovered within a minute. And so what we did is we infused this 2,4-DHB after doing the iron oxide, and you can see that the same region highlights fairly well, and it recovers pretty nicely at 15 minutes after infusion. So that's a single agent. What about two agents? So we picked these two agents, 2,4-DHB, cranberry metabolite, and then DHTA shifts at 8.5 and about 9.5 ppm from water. So we thought in this case we would infuse the DHB first, collect images at time of 0.1. Then after a little delay of 20 minutes, we start infusing DHTA and collect this 2-color image at time 0.2. So here's our first image at time 0.1. Again, the frequency 9.6 and 8.4. You can see there's very little signal at 8.4. Pretty nice signal at 8.5. Time 0.2, after infusing the agent that should show up at 8.4, you can see that in fact we do see signal at a different area and very nice color contrast in vivo in the brain. And just here's to show what the gadolinium showed after at this much later time point after a long time period with mannitol. So in fact, we can use this color imaging, and it does have some indication of where the agent's going at the different time points after mannitol infusion. Another opportunity to use these is for convection-enhanced delivery, described in detail in this meeting. People have been using gadolinium contrast agents for a long time for CD to show where the agents go. We want to use our new agent to also show this type of localization. So in this circumstance, what we did is we focused on a theranostic or a dendrimer optimized for CD. And dendrimers are fairly nice as a nano platform. This is what they look like in general. And so you can have a large number of contrast agents. You can change the surface to alter the perfusion properties, and you can add therapeutics as well. It's a fairly nice, flexible platform for convection-enhanced delivery. So what we did is we created this salicylic acid conjugatable entity, attached up to 42 per dendrimer surface, and we saw very, very nice CESS properties for this CESS theranostic. Again, you can infuse it with convection-enhanced delivery. Here's our pre-injection image, and then after infusing into this brain tumor here, you can see at 30 minutes and 60 minutes, fairly nice this agent actually has necessary therapeutics, so very nice. So just in summary, CESS MRI is a nice tool for molecular imaging, particularly for image-guided delivery. And we have designed and since tested a number of different CESS agents with shifts that are appropriate and color properties that are appropriate. And shown that color imaging can be used for looking at intra-arterial delivery, and also designed CESS theranostics, which do not require surrogate, but can also be therapeutic and MRI monitored at the same time. So I'd just like to thank my colleagues, coworkers, and also directors, and funding, and thanks for your attention.
Also perfect timing. So can the next speaker get ready in the meantime? And perhaps there are some questions for Mike. Everybody a little sleepy this morning. Oh, over there. Yeah.
So one of the issues with sets has always been in terms of that you need high concentrations of agents. Is that still the case in terms of what you're infusing, or has the sensitivity improved so much that even low levels of infusate you can detect?
Well, so what we're showing is compounds where you can detect high micromolar, low millimolar concentrations in 3T scanners. So these are near ideal. We haven't basically created the ideal imaging sequence. We're still working on various methods for doing that, but these are lower concentrations than what you would infuse for X-ray contrast. So they can be lower concentrations than the triad of enzymes that are routinely used for interventional radiology. So they're more sensitive than those compounds. So we think it's viable.
All right, then thanks, Mike. And we move on to the next speaker. And the next speaker is Dr. Marcel Dadi, and his title is Interventional Magnetic Resonance Imaging Guided Transplantation of Neural Stem Cell Progeny into the Brain. Okay.
Great, thank you very much. It's great to be here. Thank you very much, Mirak and Piotr, for inviting me. It's such a pleasure, and the organizing committee. Thank you. So I'm going to tell you a little bit about some of the work that we've been doing to deliver the cells into the brain. And as you know, it's really challenging. Not only the cell, but also the delivery can make a huge difference in the therapeutic aspects of the intervention. So I'm going to tell you a little bit about the cells that we work with. And yesterday, you have seen a lot of intraventricular and intraarterial injection. Today, we're going to talk a little bit about the intraparenchymal injection. And it really depends on the intervention. All of them, they're amazing. And depending on the intervention, depending on the disease, I think the strategy should be designed based on that. So our cells are iPS cells, induced pluripotent stem cell. We start from a biopsy or from blood samples. We can take them and modify them with the Yamanaka factor. There are 4 transcription factors that turns a cell into induced pluripotent stem cells. And then we have this technology when we can expose those pluripotent stem cells into growth factors. And those growth factors, they stimulate the generation of the neural stem cells. In here, I can actually use into a neural stem cell, and these neural stem cells, they differentiate into the progenies, which are neural stem cells, they differentiate into the progenies, which is neuron, astrocytes, and oligodendrocytes. So this is really the multipotency of a neural stem cell, and this is pretty much the definition of a stem cell: its ability to self-renew and generate large number of progeny and differentiate into these 3 cell types. And this technology we've been working for a few years, for many years, and we can isolate with this technology cells, self-renewable neural stem cells from the developing human brain, from the adult brain, from the ventricular zone, and as well as other parts of the brain, from the embryonic stem cell derived from the blastocyst, and also from iPS cells. We can scale them up. I think this is really what is established now in the literature. We can scale them up, generate a very large number of progenies. These ones, they grow into what we used to call a long time ago neurospheres. It's a little bit different from organoids. Depending on the regional isolation from the brain, they can grow in different structures. And this is our protocol for generating dopamine neuron. All those red cells in here are dopamine neurons. So this is for application in Parkinson's disease, and the idea was to use neural stem cell and differentiated one for the stroke. And we can scale them up, can generate a very large number of like, for example, a master cell bank of these cells that contain at least anywhere between a couple million to 20 million cells per vial, and store them for long term. One of the properties of stem cell is the ability to generate a clonogenic population derived from a single cell. So this is a really good test for us to make sure that the cells that we're working with, they have the ability to self-renew and to generate a clone. We can grow them, as I mentioned, for long term, and they grow as a neurosphere. And we study a little bit their growth rate. They're quite stable. We can maintain them for a long time. But the media, I have to say, the media is extremely important in maintaining them, so they don't drift into different lineages. 2.7-fold of increase, and the doubling time is about 1.4 to 5 every 24 hours. This is how they differentiate in vitro, neuron, astrocytes, and oligos. The astrocytes in here is stained with GFAP in blue in the bottom, the neurons with the beta-tubulin, and this is an oligodendrocyte stained with galactocerebrocyte. So it's a nice test assay for us to make sure that these cells, as you grow them, they don't really change the phenotype. I'm going to switch now to how we can deliver them into the brain. I think we heard yesterday about the design of the cannulas. It's very important to have, we find for both cells as well as for gene and also for small molecules delivery into the brain, the stepped cannula really prevents the reflux of either cells or drugs, or as well as I mentioned, the gene particles. So the cell delivery, the design, I'm going to tell you a little bit about the protocol that we use, which is based on the ClearPoint system, and I will go a little bit more in detail. We put a grid, we identify the target, and these are the fiducials to navigate the brain. But the main thing is really to avoid any kind of issues in hemorrhage, as well as any kind of correct for brain shift, as we're thinking to move into the clinic, is accurate. So we really see what you're doing as you are injecting the cells. I'm going to tell you a little bit about the animal models that we work with, as well as the method of transplantation. I'm going to touch a little bit at the end about some clinical protocol that we have in mind, and would love to get your feedback on this. So this is one of the animals that we work with. This is a marmoset, and the test that we use is object retrieval test. It's a well-established test that actually measures both the motor as well as the cognitive abilities of the animal. This video in here showing a marmoset reaching here for a marshmallow. So it's a really nice sensory motor test, and you can test for the right arm, for the left arm, and you can actually modify the position of the reward within the box, and you can turn the box. So really, you can touch on certain aspects of the cognition and the motor. This is a Parkinsonian, actually. So they respond very well into the drug that induces Parkinson's, which is MPTP. So you can see bradykinesia there and rigidity, and it goes away with the L-DOPA. So they respond very, very well to L-DOPA, which is the same treatment as in humans. We also work with the baboons. The baboons are a little bit different. They are much more skilled, and you can see in here the baboons, they love grapes, so they go for the grapes, and we can do exactly the same test, and with the baboon also, in addition to these kinds of tests, they love this. I mean, one time my postdoc, he was a little bit slow in pulling the tank, and the baboon, he actually pushed it up for the grades. This is actually now a CANTAB. CANTAB is a really advanced neuropsychological test for testing the cognitive abilities. So I'm telling you this because we wanted really to see the effect of stem cells on not only the motor but also on the cognitive aspects of the animal. And this is a CANTAB. This is a very simple discrimination test. It's associative learning, which basically there is two shapes, and they get to choose associate between the right shape and the reward. And so they have to make that choice. And you can see in here, it touches there, and then you get the reward. And then again, those shapes, they change. So we have to choose the right one in here and to get the reward. So this is really good for associative learning. And we have another test in here. It's the motivation. Motivation is also something that is affected in Parkinson's, and the idea in here is to show the animal a sign, and then they have to touch it multiple times. Either one, they get the first one, then the number of touches increases, and to get the reward. Sorry, I need to do this first. So they touch it first, and they get the reward. So then this is actually, we wanted to test the aging and the effect of aging on motivation. And they have to touch it multiple times now to get the same reward. So she's a little bit tired in there, switch the arm. So then to get the reward, she has to push it now almost 50 times. So, but she gets tired and then she just push it away. So we find actually interesting thing, we find the difference between it aged. When someone is young, as they sit there, they can touch the screen as many times as possible to get the reward. But with age, we see a very nice split between the two populations. I'm going to tell you a little bit about the paper that we published recently in the image guided using the ClearPhone system. So this is how the frame look like. This is an MRI compatible one, and we have the animal sitting in a supine position, and it works very well, and we can access the animal from the back of the MR. We use the same technique that it's been well established in here. Take the SPO label that we heard at the initial talk about it. Incubate them with the poly-L-lysine, and they penetrate into the cells very easily, and can track them in here. In this Prussian blue staining, you can see the particle inside the neural stem cells. So the injection process, we tested in a phantom gel. We tested different speed, 1 microliter and 5 microliter. You can see here a nice insertion needle and a picture of the cells as they migrate into the gel in here. We see that they really go in a ovoid one. And remember yesterday in the talk, depending on the distance between the next step, I think that's what influences a little bit the shape. But once you pull the needle, the shape becomes a little bit more round. While in 5 microliter, we see a lot of reflex of the cells, and it's captured in here in this movie. So you can see the cells coming through the needle, and it's like this pulsatile mode of distribution of the cells. They come out in here, and they move a little bit, and then as you take out the needle, they form a nice circle. So really, the speed of injection changes the distribution of this is 5 microliter per minute. You can see the cells are streaming up in our hand. They really went way straight up to through the cannula. We find also a little bit of changes in the cell survival. Once you inject them into a tube, microtube, we don't see much difference between the two speeds. But in 1 microliter per minute, there is usually a drop in the cell survival up to for about 40%. The design that we did to inject into the cells, this is a very well established process. The trajectory alignment, we put the grid in here, the 1, 2, 3 in here, and alphabet, you can identify exactly your target. And based on these fiducials, you can determine the entry point. And then with that, you can adjust the trajectory, align it exactly where you want to be, avoiding any kind of blood vessels or the ventricles. So any structure that you want to avoid. And then once you finalize the trajectory, you can inject the cell exactly where you want them to be. In here was in the pita main, and the cell, you can say them is hypointense area because the SPO labeling. Then we can track the cells with the Prussian blue in here staining, human marker stem 121, and the tunnel staining to see the cells, and methylene blue that show the live cells and some of the dead cells. So we get about 25% survival in this particular injection. These are the various ways it's been used in the clinic to inject the cells. The famous Lexcel stereotactic, which is actually evolving and trying to adapt it into an MRI compatible. The famous next frame Medtronic, and the StarFX of AHS. And this is the ClearPhone that by Daniel in UCSF, but it's still in development. It's kind of interesting way to deliver the cells, still in development. So this is really evolving, and I think it's an interesting. We see a lot of advance in this technology, and I think there's more to come. This is the design of the clinical trial that we did a long time ago. Some of you may remember with the with latent bioscience. This is how it was. It was 5 trajectory into a human trial that's been used in Pittsburgh and in Stanford. 5 tracks, 5 deposits, and surrounding. This is the core of the stroke in here, with 1 injection needle right in the center of the stroke. This is the preclinical study that we did at that time to go to convince the FDA to go for this protocol. So our thought is to use the clear points because it's cells that we use, they integrate better once you transplant them directly into the parenchyma, and depending for stroke, we find that in surrounding the stroke area in the penumbra works very well. So I'm gonna skip this because I think I am close, but I'm gonna show you just how many. 1 minute. Okay, fantastic. This is actually less than a minute. So the ACPC, I think you may be well versed with this. The ACPC, this is the clear point system. So it's really easy to manipulate and to work with. You identify the target, and then you align. You set the target, and then you make sure that that there is nothing in the flight through. To make sure that there is nothing on the way, and you are going to the right target, and then you align the trajectory of the needle to the actual cannula trajectory. So this is the predefined target, the yellow one, and then the red one needs to be adjusted. So it's an easy way. It's a little bit actually primitive way to use the red, to use this button to turn them a certain number of turns, 2.5, and then you align the trajectory with the actual needle. So it's a really nice and precise. Make sure that you are hitting the target. It's very non-invasive. You can see in here. This is one of the protocols that's been used to take actually a biopsy. You can see these are where the screws are, and this is the penetrance into. So it's a really percutaneous approach that you don't even have to cut the skin. I have to thank a lot of people in my lab. Those are the initial team that was part of the work, and also a lot of my collaborators and funding, as you see. We have our foundations and also the National Institutes of Health. Thank you very much. Thank you.
Thank you. Right, we'll do one quick question, and then the next speaker, please set up your talk. Sure.
I have a question about the slow infusions of cells. How reproducible they are? Because we found that if you infuse this particulate solution cells, they tend to aggregate, and then especially with the clear point system, when the cannula is not vertical, you tend sometimes happens that the fluid is gradually infused, and the cells are staying behind in the cannula. Could you see that? How reproducible were these cell deliveries?
There is actually a really great work that was published by Michel, and there is various kinds of solutions that you can change the buoyancy of the formulation or of the combination of the cells, and that really changes how the cell distributes. In a supine position, you don't have that issue of the cell sedimenting. We didn't really have we do have a little bit of clamping of the cells, and I think the cell preparation is really critical. We have we may have some magic hands, but we have this really amazing reproducibility, and I can really talk to you a little bit more about that, about the preparations of the cells and the injection process. Thank you.
Great, thank you. Okay, next speaker is Dr. Wojciech Lesniak from Johns Hopkins, and we'll be talking about applications of PET in industrial therapeutic delivery to the brain.
Thank you very much for introduction, and I would like to thank Mirek and Piotr for giving me opportunity to present here today. And
I'm going to switch gears a little bit because so far you were presented a lot of beautiful MR or CT images, but today I'm going to talk a little bit about, very briefly, about PET imaging and its application mainly in oncology, intraarterial drug delivery, and intraarterial PET-CT of intraarterial delivery of antibodies, nanobodies, and polyamide tendrimers, and their radiolabeling, kinetics, and biodistribution in the brain and peripheral organs. So starting with positron emission tomography is one of the fastest developing imaging modality because of the number of reasons, such as it's highly sensitive, quantitative, and functional. And we have a number of radioactive atoms, and which have different half-lifetime, and we have those which are covalently attached to biologically active molecules, and the radiometals needs to be chelated to these injected molecules. Upon injection into the patient, they emit protons which travel very short distance through the patient body, and they collide with the electron. And during this initialization process, two photons are produced, which are sent in two different directions, 180 degrees, and they are picked up by the detectors. And the signal is converted to the image during the reconstruction process, and then it is fused with CT for anatomical co-registration. And as I said, is one of the fastest growing imaging modality because it can be used in different applications in brain imaging, neuroimaging, in cardiovascular imaging, in cancer, and many others. So far, there were nearly 2,000 radio tracers synthesized. However, by far, the most extensively used is FDG, which is produced by substitution of this hydroxyl group by F18. And because of the substitution, it is metabolically trapped within the cell. And among different applications, it can be used for detection of the high-grade gliomas, as presented here. But it is limited only to the high-grade gliomas because brain is the most metabolically active organ in our body, and shows higher uptake of glucose around the tumor, because tumor is located here, and you can see the graph here indicating that there is a much higher uptake of the radioactivity around in healthy tissue. And I don't need to spend a long time today explaining that one of the major problems to treat the brain tumors is the blood-brain barrier, and which shields the tumors behind it and prevents the drugs to go through and reach their targets. So one of the ways to avoid this obstacle is the intraarterial delivery, as we already heard yesterday and a little bit today. And intraarterial drug delivery goes back to 80s. And they radiolabeled with C11 DCNU, and it was infused, and they obtained mixed types of results. And some patients would benefit from this, and some from this treatment, and some patients didn't. And they observed quite high rate of neurotoxicity. Some patients would even went blind after the treatment. And this method was almost completely abandoned. However, with the recent development of the newer and better improvement of the imaging modalities, as well as the new catheters, this method came to the picture again. And more recently, Bugbar performed a short, small clinical trial with the bevacizumab and different drugs with the intraocular drug delivery. And this I disconnected something, so I'm moving too much. I'm sorry for that. Back. Thank you, Mirek, for that. Thank you very much, Mirek. So, and you can see here MR image before treatment and 1 month after treatment. And as I showed, the glucose can be uptaken by the high-grade gliomas. And after the treatment, you can see the significant shrinkage of the tumor, as well as the tumor is much less metabolically active. The same was obtained with temozolomide, and but also they obtained a mixed type of the results. And as you saw the slide a couple of times yesterday, it was shown by Peter and Monica, that one of the reasons can be that delivery of the drug can be affected by slight difference in position of the catheter. As you can see here, very little difference in position of the catheter, and very different perfusion could be detected. And also, this was also shown in much better way in 3D yesterday by Michał. This is the case of this young lady with recurrent glioblastoma. And as they shown here, the speed of delivery can also affect the perfusion of the tumor with gadolinium. However, they infused the bevacizumab at a higher rate to achieve the. I'm not touching it. I have to stay away from this cable. I will move a little bit here. And then after the treatment, they observed quite a nice therapeutic effect. And this is great. We can use MR and gadolinium to predict the perfusion. However, it is still not a drug. We cannot say anything about the delivered drug, how much it went, and gadolinium is much smaller complex compared to big bevacizumab, so it can show very different distribution as well. So why don't we use antibodies and radiolabeling of the antibodies? So they can be labeled with zirconium, for instance, and one of the Dutch group already have shown that the uptake of the antibody doesn't really correlate with the uptake of the gadolinium in children with the DIPG. And we used the same approach. We took the bevacizumab, conjugated it with the ferroxamine, and subsequently labeled it with zirconium. And we checked if it doesn't affect the binding to the VEGF. And here is the chromatogram indicating that the radiolabeling was performed correctly. And we performed 3 different experiments. Mice were infused intraarterially with the bevacizumab, radiolabeling bevacizumab with intact BBB, and you can see some uptake in the brain, in the ipsilateral hemisphere, and here is the curve kinetics showing the first hour. Here the infusion was stopped and indicating that it was like a little drop of concentration, and then it remained there. Although upon opening of the blood-brain barrier with mannitol, we have significantly higher uptake of the bevacizumab, and here is the curve demonstrating it. And with opening blood-brain barrier and IV infusion, we don't have any uptake in the brain. This increase is only due to the increase of the background. And here is how the radioactivity increases in the heart. And then using one of the software, we could estimate how much of the bevacizumab was uptaken by different brain regions. And here is the full body imaging showing high uptake. I didn't touch it at all. Okay, and this confirms, and then also the ex vivo biodistribution showed the same result, that we have high uptake in the ipsilateral hemisphere 24 hours post-injection, and then upon IA infusion with osmotic blood-brain barrier opening and without, and there is almost nothing accumulated in contralateral and hemisphere. And then we have we're still in circulation quite a lot because bevacizumab is circulate for a long time in the bloodstream, and quite significant uptake in different organs as well. Then we labeled nanobodies using the same technique, and as you can, and we performed it. I'm sorry. Okay, maybe you can ask somebody from the. Anyway. With the nanobody, we observed the very high uptake. In case of this mouse, we observed almost 100% of injected dose per cc. And as you can see, much lower kidney uptake and almost everything stayed in the brain. And then with intact antibody, we have much higher kidney uptake and some also quite significant uptake in the brain. And upon IV injection with osmotic blood-brain barrier opening, there is no uptake in the brain of the nanobody, and everything is localized in kidneys and lungs. And full body imaging confirms that results which I was showing before. Very high uptake in the brain upon osmotic blood-brain barrier opening and IA delivery, and followed by the IA infusion with intact BBB and nothing in the brain upon IV injection with osmotic blood-brain barrier opening, and the same in 24 hours post-injection. Then I will talk a little bit about polyamidoamine dendrimers. It was very briefly introduced by the previous speaker this morning. Polyamidoamine dendrimers are synthesized based on two reactions. First reaction is the Michael addition of methyl acrylate to ethylodyamine and amidation of resulting ester with ethylodyamine. And in this case, the generation 0 dendrimer is formed, and upon the repetition of those reactions, dendrimers grows in size and next generations are formed, and more primary amines are on the surface of dendrimers. And starting from generation 4, they form nice globular macromolecules. And due to the presence of the high number of the primary amines on the surface of those dendrimers, we can modify them with different functional groups, drugs, targeting moieties, imaging moieties. Then the surface charge can be altered according to the needs. They can be negatively charged, they can be pegylated, they can be carboxylated or acylated. And okay, I have to glide very quickly through my slides. Then I modified dendrimer with deferoxamine for labeling, and the remaining primary amines were hydroxylated, and they had only hydroxyl groups. And the same set of experiments, as you can see, dendrimer basically went in and out very quickly. Within half an hour, we were quickly cleared from the brain. And the same is confirmed by the full body imaging and biodistribution. And this is the slide which concludes our studies. And intraocular delivery of antibodies and nanobodies might be the attractive therapeutic approach to treat the brain disorders. On the contrary, hydroxy-terminated neutral, very hydrophilic dendrimers goes in and out of the brain, and there is no non-specific uptake. However, upon proper surface modification, we can get very good targeting. I decided to add a couple of slides showing our recent results, which were quite exciting. I used the same dendrimer and modified with PSMA targeting moieties and some fluorescent dyes. As I can see, the mouse here has two tumors, one with a very high PSMA expression and the other is with a very low PSMA expression. As you can see, it is exclusively going to the tumor with high PSMA expression, and it can be picked up by here are the organs. Basically, you can see an accumulation in the PIP, high PSMA expression, and almost nothing in different tissues except kidneys, because those dendrimers are around 5 nanometers, so they are still excreted by kidneys, and there is some liver uptake. And this is actually dual imaging, because you can see, you can also use the photoacoustic imaging to detect those dendrimers. And the same dendrimers can be, maybe skip this, can be radioactively labeled. And as you can see, the non-targeted dendrimer again clears from the bloodstream very quickly. Within 1 hour, is completely gone from the blood. Then we have quite significant uptake in kidneys and bladder, followed by liver. However, the targeted PSMA dendrimer, you can see that changes completely pharmacokinetics, much higher concentration in the blood. And then we have quite significant uptake in the targeted tumor versus non-targeted tumor, and some spleen uptake as well due to the long circulation. And this can be also confirmed by PET imaging, SPECT imaging, because in this case, they were radioactive indium. And with that, I'd like to thank you, thank Mirek, Piotr, and Marty Pamper, who made this research happen, and other our research team members. Thank you very much for your attention.
Can we have the next speaker please set up the slides quick? Let's set up this. While he's setting up this, half a question time. Go ahead.
How I prepare them? No, it doesn't. I just wanted to show you the capability of those dendrimers that upon different modification you can use for optical imaging, you can use for photoacoustic imaging, you can nuclear imaging, you can load them with gadolinium, then it would be nice MR contrast agent. Mike showed that we can, I did the work with Mike actually, prepare those dendrimers for CEST imaging. So you name it, I can prepare it using dendrimers. Yeah, it can be used for the brain perfusion as far as I know, but I don't know much about the technique of it.
Can we postpone that maybe because we're already running 12 minutes behind? Why don't we do that conversation? Sorry about that. Right, so the next speaker is Dr. Chin Chin from Hopkins. He's going to be talking about novel techniques for non-conscious cerebral MRI.
Thank you for the introduction and thanks for the invitation by the organizing committee. So my talk today will be about cerebral MRA, and so contrast enhanced MRA use mostly gadolinium contrast agents, and through the venous injection, it has some a small percent of people will have some adverse reactions. But mainly the safety concerns of gadolinium-based contrast agents start to become a problem in the field. About 10 years ago, the nephrogenic fibrosis has been reported, and for people with inadequate kidney function. So nowadays, in the hospital, people have to be tested with their kidney functions to make sure that they can receive the gadolinium injection. And then about 2 or 3 years ago, even for people with normal kidney functions, has been reported that gadolinium deposition in the body and even in the deep brain has been founded. So this really become a concern for the field. Before the summer of last year, the FDA issued this warning that for the first time, if you go to the hospital to receive if you need to receive the gadolinium injections, and the patients need to be informed of all these issues. So luckily, we have with MR, we have non-contrast enhanced techniques to do MR angiogram. So it has been around for like 30 years with phase contrast MRA and time of flight MRA, where these methods have been used routinely, but the limitations of those methods are either small coverage or the lack of a clear display of the slow flows. So today I'm going to talk more about some new methods. One technique is called velocity selective MRA, where we want to overcome the limitations of this small spatial coverage and try to have better delineation of slow flows. Also, there's a method called active spin labeling based MRA, where they can allow the time resolved MRA and even visceral selective MRA, which can be more relevant with neural interventions procedures. So in MR, we know that the gradients can have some static moment and also the fourth degree moment, which is related to the velocity. So if you have a bipolar gradient, then you have a 0 moment for the static things, but then for the first moment will be proportional to the velocity, and which is the basis of the phase contrast angiogram, where you have the 2 bipolar gradients toggled, and then you subtraction of the phase, you will calculate, and then you derive the velocity. So and also in MRI, it was long ago being derived that the excitation pulses can be considered to have a case-based encoding for the spatial encoding, so that similarly they can use that to derive a velocity selective excitation by using the bipolar gradients to encode the velocity case space. So quickly through the history of this development of velocity selective pulse streams, where originally the pulse streams is only using the bipolar gradients, but without any refocusing pulses. Later we found that in MRI, the field inhomogeneity need to be considered, where the additional phases out of the field inhomogeneity need to be refocused, so that only the phase of the bipolar gradients can be accumulated. So refocusing pulses are inserted in this refocusing pulse stream, in this velocity selective pulse stream. to make sure that the velocity selective profile is can be intact in the presence of large field inhomogeneities. And also there's a B1 inhomogeneity, so there's also some improvement in the pulse streams to make sure that both B0 and B1 inhomogeneity can be tolerated with advanced design of the pulse streams. So this is a simple sequence where that we apply this velocity selective pulse stream right before acquisition. On the left, you see that traditionally they use the hard pulse encoding, and you don't see the background still have some the static tissue background is still a little bit large, and then when you apply this more advanced pulse that can saturate the static tissue background better. And so we want to ideally want to select to visualize either arteriogram or venogram. Then in this pulse range, in this pulse sequence, we insert a spatially selective inversion pulse in the brain, and then so that we can knew the outgoing venous blood, such that only the incoming arterial blood can be visualized in the end. And or alternatively we can invert and knew the incoming arterial blood and only visualize the outgoing the venous blood in the brain. So here we see that we can do this separately, either see the entire vessels in the brain and or only arteriogram or venogram separately. To compare with the time flight MRI, you can see that on the left is the coverage from the head to the neck, but within the yellow dashed volume, which is a typical coverage by the time flight MRI. So we compare the images, the data only from within this covered area by the top flight and compare with VSMRI and top flight. We see that there's also more vessels can be more small vessels can be seen by the velocity selective MRI compared to top flight. So here it shows that the two advantages of this velocity selective MRI, which is larger spatial coverage and better delineation of slow flow. So in this patient with focal lesion in the M1 segment, we can see that both time flight and the VSMRA show this lesion nicely, and but the VSMRA again shows more small vessels, distal small vessels. Another example here is this patient has a aneurysm on the top of the ICA within the focal villus area. You can see the time flight has a not so good of a delineation of this aneurysm because the flow in that aneurysm is very slow. So VSMRA can show better qualities there. So the current trend of the MRI is to accelerate the acquisition. Here we integrated with compressed sensing techniques to see that the time flight MRA now can be extended to large coverage, but with a high acceleration factor, like 8 CS factor here, it can be acquired in 60 minutes. So with velocity selective MRA, we can also using the 8 factor acceleration, but speed is 4 minutes now. We also is also working on to extend our techniques, going down a little bit to visualize the carotid from the above the aorta and see the subclavian and common carotid until the bifurcation. So this is ongoing project. So now I want to introduce some other advanced techniques in the based on arterial labeling that can give you the time resolved MRA. It's called 4D MRA. So normally what they do is that participant labeling, you label some upstream vessels and with a pulse, either label or control. So you do that 2 separate scans, one is with the label on the upstream vessels, and then the other one is with the control pulse. And then you do a subtraction of the 2 to see the downstream vessels feeding effect. And then you apply some kind of multi-phase acquisition or loop locker multi-phase acquisitions after this label control pulses to see the dynamics of the incoming bolus. So here is an example of the normal volunteer. I think you can see that nicely, that in this volume, that different angles, you can see the different feeding effect to the distal vessels. This can be acquired in 6 minutes with a temporal resolution of 50 milliseconds, and 1 by 1 by 1 spectral resolution. And this is the AVM lesion that you can see that with time of flight, you don't see much of this nidus in the, and you don't see the venous aneurysm around the nidus, but this 4D MRA can nicely see this heterogeneity within the nidus, which is consistent with the DSA results. So another recent advance in this field is that we know that I just said that AFL needs to acquire 2 times. One is the label, the other one is with control. So that doubles the time that's necessarily for the MRA. And then the neural method actually use the fact that for the vessels, they don't have to use to acquire the control, repeat the same amount of time only for the control, which normally was the ASL was already derived for the quantitative perfusion measurement, where the perfusion signal is really small, so they really want to be accurately accounting the perfusion signal, so that they have to cancel out the static tissue background. But to cancel out the tissue signals. But for the MRA, where the signal is much larger, so they only use the control. Here, they only acquire the control in the beginning before the labeling pulse, and making the multi-phase to be a static signal, a static state, so that the tissue signal can be subtracted from the first control images. So this is called the actress imaging technique. Only one half, so using the half of the acquisition time, but with only one control images. So here they show the comparison with between the conventional ASL approach with the actress approach, so that you can see the time is half, but then the image quality is very similar. Lastly, this is a way to do the vessel temporal time resolved vessel selective MRA, where in MRI they can use the RF pulses and the gradients to selectively only label the one vessel of interest. And so here they can they can select left, right carotid and also the vertebral arteries separately, and then in the end they can show that you can see that the vessels have, you can see the vessel territories or the vessel color coded MRA here using this approach. Okay, so in summary, we went through we showed that the velocity selective MRA need to apply the advanced Fourier transform-based VS pulse streams to suppress the static tissue background, so that this method is doesn't need a subtraction, it's non-subtractive, and offers 3D whole brain coverage, and so give you a high quality of MRA with better delineation of slow flows And then just enabling-based MRA allows time-resolved 4D MRA and even vessel-selective MRA with high time efficiency, because they can even they do the separation, but doesn't need to acquire the image twice. So hopefully some of this method can be increasingly used by the field of the neurointervention.
Thank you. Since we're running behind, want to have any questions during the break? Then we want to start the break. How much time? 5 minutes? 2 minutes?
No, I think those are still new developments. So it depends on the vendors. I think I'm not sure about Siemens, which is a scanner in Hopkins, the clinical scanner in Hopkins. I also don't know for sure for Philips. So we can look into it. It's yeah.
Hello, Marco. Are you there? We're in a break time. And Sunil?
Hi.
Hey, how you doing?
Oh, I'm fine enough. A bit tired of that.
Well, you know, I don't know if we go in front. Sometimes we broadcast this on, well, this is on YouTube now, but
really?
It's not going to be recorded. I mean, right now, you and me talking, it's on YouTube, but it's not recorded.
Okay, perfect.
I take it out. So how you doing?
Well, fine. I just back home from work, but I have to back for the night shift. So
what time? And what time does that start? In a few hours.
Yeah, now is 3 and a half p.m. here.
Oh, okay.
Okay. So I have just time.
This is a good conference, huh?
Yeah, very impressive. Very. I could not figure out how the technology went over. It's very impressive.
Yeah. I mean, it's really advanced, but
yeah.
John Hopkins is tops in the world, especially in robotics, because the government funds them because of military reasons. They're trying to develop like robotics arms and legs. They're trying to develop robots to be soldiers.
I see.
You
So
understand, right?
yeah, yeah, it's
So
completely.
there's big money in this. Big,
Yeah, yeah.
big. So the United States government didn't think, well, let's improve medicine by, no, they just thought, let's build an artificial arm, artificial robot that
Yeah,
can function. And medicine went to them, says, hey, we can use that artificial hand. And so
Yeah.
they're actually doing that now, are using robotic hands, but it's very well funded. That's why they're making progress.
Yeah, federal funding. Yeah.
Federal funding. They don't throw it around, but they give it to valid. And
Yeah.
Johns Hopkins is very close to the Washington, D.C.
Mhm.
It's the closest research institute to the government. So, and plus they have a good reputation as a medical research center anyways. So certainly the tops in robotics.
I see.
But that's the reason why.
Mm-hmm. Yeah, I see. Because you say the robotic can be used in medicine, but is a consideration for the federal government for soldier amputated. It could be some very useful. So
Right.
definitely.
Right. That's, yeah, I'm sure for medical reasons, but that's not their main purpose was military.
Yeah, yeah. True.
And that's why they put big money into that.
Yeah, I understand.
So, and it just happened that there are medical uses. So what they do, because I interviewed a guy that got a robotic arm, and maybe I'll send you that interview, but with a patient that goes to Johns Hopkins and
yeah.
But they won't let him take the robotic arm home. He has to come to the center to use it, to test it, and then he has to give it back and go home. So then they're careful about that, about someone stealing the tech. So we better pay attention. I better pay attention here. So
yeah, I agree.
Yeah, I guess they still haven't started yet. They're just getting ready. Sunil, are you there? Sunil, are you there? You know Sunil, right, Marco? He's he's a neurosurgeon from China.
Yeah, from China. Yeah, I met him last Sunday, I guess.
Yeah.
Okay.
Okay, Sunil, are you there? Hey, I'm coming to Europe in September.
Oh, really? Where?
Yeah, my brother's daughter is getting married in Portugal. In Portugal.
Congratulations.
Yeah. She works for Google.
Oh, great.
Yeah, and she's doing very well.
Yeah.
She was in Australia, and now for some reason they decided to get married in Porto.
In Porto.
So I'm going to go there at least for a couple of days. I hope to have some time to spend in Europe, and maybe I'll swing by Lake Como.
Oh, why not? Just make me know.
I would love to. I would love to. I'd love to go meet my mentor, is a neurosurgeon from the Netherlands, Peter Kerben. He's the one that really encouraged me to do this.
Really?
Yeah. When I first started off, he encouraged me, and I got to know him a little bit. He made an app called NeuroMind, which you may have, Neuromind. It's a real popular app. And I've interviewed him a couple of times, but he's very strict about his time. He will not spend any weekends
I
on
see.
the internet. Yeah. He's got an agreement with his wife. He can't no weekends. So I don't see him that much because the weekend's the time really to connect with neurosurgeons.
It's a pity because it should be interesting to know the history of neurosurgical TV.
Yeah. I'll tell you about it. He was the one that really he gave the name Neurosurgical TV. I wasn't sure. Yeah, I wasn't sure because I was the neurosurgery TV was taken. And I thought, what other word can I use? Maybe I'll try neurosurgery. And I gave him a couple of choices. I said, which would you do? He said neurosurgical. So I said, okay, because he's internet smart. And so I just took his word. Yeah, he's
absolutely
some talks on TED. Those conferences, TED conferences. He's given some of those on various aspects of medicine, not necessarily neurosurgery. He's big on informatics. So he's not just neurosurgery. But I hope to meet. I'd like to meet him. And Europe is so different than this country. Everything's so darn close.
Sorry, in Europe?
Europe, everything's close.
Yes. Yes, it's so sometimes as a little bit federation Europe. So it's
I'm going to Boston next week, and that's 1,300 miles.
Yeah.
That's very far for Europe. That would be like going from Italy to Russia.
Yeah, that's correct. In fact, when I planned my trips in United States for next August, I could not figure out how was the distance because from Europe we see the United States of America and we figure out this.
Excuse me, Marco. I'm sorry.
Of course.
Speaker is Johannes Bolze from the University of Warwick, and the talk is on stroke modeling and neuroimaging in sheep.
Yeah, good morning, everybody. And I want to thank the organizers to give me the opportunity talking here to you. It's an amazing conference. I learned a lot so far. It's a really unique mixture of biological aspects, technical aspects. And it's all about imaging. So we use imaging, but we are not primarily imagers. So what I brought you today is a number of application examples. So how we do it, and hopefully you find it a little bit inspiring. And as said, we are working a lot with large animal models. Not solely, we also have a small animal branch, but we came to large animal models when it became clear that the failure of the neuroprotectants has shook the confidence in the rodent stroke models that are around. It doesn't mean that they are bad, but they have some translational shortcomings, actually. And the field recently notified that there may be a need for more translational animal models, actually. And in our field, the stroke field, the STERN STEPS conferences actually recommend testing new therapies in large animal models. So why should one do that? Indeed, there are a number of very nice advantages that come with the use of large animal models. So to an anatomical consideration, they are much more similar to us. They have a geoencephalic brain, they have a more complex behavior. Many of them can express comorbidities that are also present in humans, especially pets, because we share the same environment and the same risk factors, actually. They have an outbred genetic background, meaning that results are a little bit more heterogeneous working with those animals, but that is what you also see in humans, actually. And you can have very long follow-up periods, which may also be advantages if you take advantage of those for testing safety issues, for instance, or long-term efficacy, actually. And finally, many of these animals can be used with clinical equipment, and we have seen very impressive examples from that in the previous talks, actually. What is also interesting that the larger the brain gets, the more information traffic is in there, and that requires more white matter. So that means actually that the white matter content in many of these species approximates that of humans. And it's not so much of a difference whether you go for a rhesus monkey or you go for a sheep and you got already a slight difference to humans here with an even larger brain, but you can also see this huge difference to the rodents models we usually apply. And that also means that white matter damage has more severe complications in those larger brains, which may be a translationally relevant aspect actually. But it's laborious and you need a dedicated infrastructure. So these are examples from our large animal lab we built up in my previous institution, which is in Leipzig. And this is an OR which had, before we used it with the first sheep, had a human standard actually. It's pretty well equipped. You can do a lot of things there, but you also have to train your team. And it's not only one postdoc doing that, you need like 2 or 3 or 4 doing that. So that's not only expensive, it also binds a lot of labor force. But as you can see from that guy here, which is pretty well connected to all the machinery, you can derive a lot of information from a single animal. So continuous measurement of physiological parameters gives you a very good information of the health status, of the condition of the animal. And you also find good arguments to exclude or include animals. And this thorough monitoring is really something which gives you an advantage once you have established that. Stroke modeling, in principle, can be done in 2 different ways, and we have also seen examples about that. So the first example, or the first way, is that you do an external surgical occlusion of a brain supplying artery. The other is that you make direct access to the brain vessel and occlude it by thermocoagulation, for instance, or by placing a clip. That is probably the way to go with swine and sheep, because he has this Riti mirabile, and we had an excellent talk from Piotr's group yesterday explaining that. This is the Riti mirabile, and this is the corrosion cast. You can see it here in sheep. So this is the circle of Willis. Everything is very comparable to the human anatomy, but the circle of Willis itself is fed from the maxillary artery. That is the middle cerebral artery that has been occluded here, and you see all the capillaries here are missing, so that you would expect a stroke actually. This transcranial approach is technically a little bit more demanding. You have to train it actually, but it also gives you good control on the area you assess. And if you train it well enough, the risk of parenchymal damage is even minimal. You can do transient or permanent occlusion, for instance, by placing a clip and removing one later. And you can decide whether you seal the trepanation here or you leave it open. It gives you an advantage, especially with larger stroke, so you can mitigate a severe ICP spike. If you close it, have a major stroke, the animals will herniate as humans do. And that's also good for long-term follow-up. And you have, of course, because you can decide whether you occlude here, here, or here, a good control on lesion size, actually. We use imaging together with partners of the University of Leipzig, for instance, combined PET MRI imaging. And this is one of my favorite examples here, gives you a very good estimation of the cerebral blood flow by 15O water PET. And you see nicely here the perfusion deficit. In the diffusion-weighted MRI, you can see the emerging lesion here, and the difference between both, of course, is the penumbra. That is the interesting part, the juicy part in stroke. Actually, you want to salvage that particular tissue. And you can see there's a very nice penumbra here in this particular animal 3 hours after occlusion of the middle cerebral artery. If you have the time and do serial imaging, you can also see the stroke growing over time. That is from a running study, actually. So I just brought you 3 examples. For instance, that one here, as you can see, as the stroke evolves over time in these MRI scans here. Same as here, you can see it's getting larger and larger and larger, and you can easily also see how the penumbra declines and the core lesion goes up actually. In 2014, our partners from the Department of Nuclear Medicine received a pretty nice toy. So they won a DFG grant, the German research foundations financing them a PET MRI device. It comes with fancy light applications here. There's no additional price, but the real good thing is that you can do like parallel MRI and PET imaging with that particular device. We have been part of that grant, and that meant that we have a fixed time available for us doing scanning on those devices. But we also supplied our sheep model to help our colleague answering a number of questions. This is Henrik Bartel and Osama Sabri is heading this particular department, and they were very much interested in penumbra imaging at the time. So they approached us and said, well, can we use your sheep model to test a couple of things? And we said, yes, of course, we can do that. And their rationale for doing that was, it is a pretty old study from the pre-recanalization era, that there was a lot of trials going on thrombolysis with an MRI-based mismatch, actually, and they came up with almost neutral results. So they maybe said maybe there may be a way to think about how we could analyze the penumbra or detect the penumbra a little bit better. And particular in those times when you go for perfusion-weighted imaging, depending on the parameter you use, you can see there are considerable differences of what you could consider a perfusion deficit. So that may actually impact the way in which you estimate the penumbra. So they decided to do a case study in a number of sheep, and at that time it was possible, with a number of patients actually. And with the sheep, again, very standardized conditions, permanent occlusion of the middle cerebral artery. You see the nice core lesion here after 4.5 hours, and you can see the penumbra here. So that was pretty consistent in that particular model, actually. But what we also found when we compared ways to calculate the penumbra based on PET and on MRI, that they really do not very well correlate, depending on what parameters they applied, actually. And in all three cases, in all three sheep, it's not a lot, but the penumbra volume was always overestimated. So if you do that in a clinical trial, probably you have a higher chance ending up with more neutral or maybe even negative results. Then they went on actually for human patients that were not eligible for recanalization, pharmaceutical recanalization by TPA at the time. So at the moment, most of these patients would have been recanalized actually. So that is the basic protocol here. And what they found actually in one patient, they had a spontaneous recanalization and recovery, which was good for the patient, but he had to be excluded. Another one had a lot of motion artifacts, also needed to be excluded. But they also found moderate to rather good correlation in the cerebral blood flow calculated between PET and MRI in 4 patients. And in those 4 patients, there was also a good correlation between the penumbra volume in MRI and in PET, actually. But there have been other cases as well. So there have been 2 cases where there was no initial lesion despite these stroke symptoms, actually. But a perfusion deficit has been detected with MRI, but there was no one in the PET measurement. So at day 5 follow-up, they found that it has not been a stroke, but a non-critical hypoperfusion. So those patients, luckily, did not end up with a lesion, actually. In another case, the MRI detected a penumbra, but again, no penumbra was visible in PET, actually, and the 5-day follow-up, that there was no infarct growth, meaning that the infarct probably already had finally matured at the time, which was not shown by the MRI imaging. This is a case I personally find relatively impressive. It's a 72-year-old lady, actually, with a wake-up stroke, left hemiparesis and dysarthria, actually, and they had a pretty pronounced core lesion already at the time. And depending on the MRI parameters, we had a huge penumbra even here in these offsite signals, actually, but even in the most conservative estimation, it was still 42 milliliters. The PET scan actually was much more conservative, estimating the penumbra volume of about 11 milliliters. And when we had the 5-day follow-up, it pretty much correlated with what the PET gave us. So the final lesion volume 5 days after the event was 32 millimeters, which pretty well corresponded to the sum between the lesion core and the penumbra estimated by the PET. So overall, our colleagues have been pretty satisfied with that. The sheep actually could predict what we saw in the penumbra, so tends toward an overestimation of the penumbra volume. MR imaging started relatively early. One can do a little bit better, actually. Scan time was moderate. Total scan time was longer, if you would like to have it nowadays, but please consider they also measured a lot of additional sequences for this particular protocol, actually. Of course, PET is not something you can apply in a routine diagnostic, even though it's applicable and this parallel imaging could come well along with that scanner. But logistic refinements are important actually. You need an arterial input function, and data analysis may take actually a long time. One cannot do that anymore because everyone having a penumbra, having no contraindication, which is the minority actually of the patients they see, receives now recanalization. Another example I brought you is based on the work of Nicole Terpolilli and Nick Plesnila from Munich, and they applied nitric oxide. This is also one of my favorite examples to treat stroke actually. Nitric oxide is known that it can dilate the venous vessels, as you can see nicely here. If you have a look at arterial vessels in a steady state, you don't see much. But if you go for a hypoperfusion paradigm, you see also an increase of the diameter of arterial vessels. And the concept behind this, that is the nitric oxide, which can be inhaled actually, binds to hemoglobin and is released in areas of particular low oxygen pressure. And if you have a hypoperfusion paradigm, actually, it's already the case at the arterial branch. If the vessel gets larger, you may have sealing effects, but you may also increase the local blood flow actually. That does not work in the stroke core, as you see, because there is not much of a perfusion actually, but it works pretty nicely according to the results of Nick and Nicole, if it's the case for the penumbra. There's also no effect in the normal brain because local oxygen concentration is pretty fine. If that has all been done on mice, and if you house these mice under nitric oxide atmosphere, what you can also see that it translates in the long term into a behavioral benefit. If you turn it off, of course, it will be returned and you will not expose humans to like a week of nitric oxide inhalation because it can emit hemoglobin, can form it. But for a couple of hours, it's safe. It's even applied in newborn and intensive care units. So that is something one could do. And they addressed us to check that paradigm in sheep, actually. That's what we did. We had a serial PET investigation. That is, by the way, how it looks. We have a sheep in a PET scanner, actually. And what you can see in the baseline when nitric oxide is still off, we have this, again, this nice perfusion deficit here on those both scans. If you turn it on, actually, you can see that you can partly recover the blood flow in those areas, here and here. And it's also well controllable because if you turn the nitric oxide off, you can see that the blood flow already goes back to the baseline, actually. We had arterial input function being available with this kind of experiment, so we could calculate the actual cerebral blood flow in the area of interest. And what you can see that the infarct core, which is presented in yellow here, does not change. There's even a tendency that it gets larger a little bit, what you would expect after a permanent middle cerebral artery occlusion. But what you can do, you can transiently turn the penumbra into normally perfused brain tissue. So that may be an approach to preserve at least parts of the penumbra and to increase the number of patients that may benefit from recanalization. It's very hard. We tried a long time to test that clinically because whenever you have a penumbra, it's going for recanalization, which is a good thing, but there's no time to test that particular setup actually. With that, I want to thank you for your attention. That's my university. It's a pretty new and modern one in the UK, a little bit contrasting to the very, very beautiful landscape we have. That is Warwick Castle here. I particularly love that actually. It's a great area for hiking and everyone who comes there is very welcome to visit me. And next year, I didn't touch anything. So, yeah, so I'm over time already. So, yeah. It's only a commercial left. So we are organizing a conference as well next year in October in Berlin. It's a neuroprotection, neurorepair. Yeah, it's shut down. Okay, it's only my commercial. Yeah. Never mind. No. Okay, for the sake of time, I think that's it. And thank you for your attention.
Very much. And I'd like to introduce the next talk, the next speaker, is Rebecca. Are there any questions to the current speaker? So now I'd like to introduce our next speaker, Rebecca Klimas from Johns Hopkins University here in Baltimore, and the talk is about learning from brain cancer in pets.
Thank you for that introduction, and to the fine organizers, it's a pleasure to be here. The incidence of brain cancer in dogs is approximately 1 to 3%. This is significantly higher than the incidence of brain cancer in humans. We typically categorize brain cancer in dogs as being one of 3 types: pituitary tumors, extraaxial or intraaxial tumors. There is a lack of reliable data in veterinary medicine. There's also a lack of qualified specialists to perform diagnostic and therapeutic procedures. The tumor type and grade are often unknown prior to treatment. We do not yet have an effective biopsy technique available for performing biopsies in dog tumors. Treatment is largely based on advanced imaging. Dogs that are treated symptomatically for brain cancer, symptomatic treatment usually consists of prednisone and or phenobarbital, have a median survival time of 2 months. Secondary brain tumors are more common than primary tumors. The 2 most common types of brain tumors are meningiomas and gliomas. Brachycephalic, which are the type of dog breed that have the squashed face, the flat face and the short nose, have a high incidence of brain cancer. Treatment usually consists of surgery, chemotherapy, and radiation therapy. Radiation therapy has become the gold standard, but because of the cost affiliated with this, the lack of available facilities for performing radiation therapy, and the requirement of anesthesia, surgery, and chemotherapy are more commonly used. Prognosis with brain cancer in pets is very poor. This is a workflow for gamma knife stereotactic radiosurgical treatment. There are 2 facilities in the United States that I know of that perform this type of treatment. This type of therapy will cost about $20,000 to the pet owner. So not many pet owners can afford this. It requires multiple visits. Usually there's diagnostic MRI that's performed first, followed by CT planning, and then the radiation. Between 1998 and 2014, there were 78 investigational brain tumor drugs that entered the clinical trial evaluation process. 75 failed. That's a 25-to-1 failure ratio in developing new brain tumor treatments over the past 2 decades. This is a publication that came out last year from Cornell University with a comparative retrospective study between 2008 and 2017. There were 40 dogs that were looked at. The most common breeds were boxers, Boston Terriers, and bulldogs. 55% of the dogs were spayed females. Median survival time was 47 days from the date of diagnosis. Median age was 8. The most common presenting sign was seizure activity. Median survival time of dogs treated symptomatically was 35 days compared to CCNU therapy of 138 days. When I put this talk together, I did a quick search to see what I could find for animal models for brain cancer. And this is a classic chart of what I would find. And what's missing in this chart? They're talking about mouse models, they're talking about rat models. There's no pet models in this chart. This is what we should be considering. Companion animals are what we call pet dogs and cats. They have many desired characteristics that fill the gap between in vitro and in vivo studies. Spontaneous tumors in companion animals are a unique and underused resource as models for human cancer biology and for translational cancer therapeutics. Naturally occurring tumors in dogs have many clinical and biologic similarities to human cancers that are difficult to reproduce in other animal models. Pet dogs in particular are an appealing source for translational cancer therapies because they're considered a highly predictive model for efficient drug development for humans. The integration of pet dogs with cancer in clinical trials is of great value and importance in developing and testing new cancer treatments that'll benefit both humans and dogs. The American Vet Med Association has a clinical trials database. This is open to the public. Anyone can look for this. For pet owners, this is a great place that they can look to see if there's any trials occurring in their state that they may be able to enroll their dog in. This is a picture of a dog that I anesthetized that had intracranial surgery. We touched on this discussion yesterday. In my opinion, brain surgery for cancer in dogs is really invasive. Dogs have these masseter muscles, which are these chewing muscles. They're in the cheeks. When you think about pit bulls that can hold on, they have these cheek muscles. They also have muscles on top of their heads that are usually about 2 inches thick. And so in order to get to the brain, you got to get to the skull. In order to get to the skull, you have to remove a couple inches of muscle. So it's one of the few procedures where when I was recovering my brain surgery patients, I said to myself, is this really what we should be doing? And Piotr mentioned it yesterday. Minimally invasive techniques, in my opinion, are something we really should be considering and performing. In planning for external beam radiation, these are CTs where this mask is built for the dog's head for planning purposes. When the dog comes back for radiation, they'll have that mask fitted to them and they'll get treatments every week or according to the treatment protocol. Here's a dog that acted totally normal, but if you're a neurologist, you'll notice the dog has a head tilt. This dog had a head tumor, a brain tumor. Here's some radiation therapy. There's a dog anesthetized underneath that blanket. This is a dog that I was prepping for surgery. We call this a cranie stand. This is a piece of equipment that's utilized by the veterinary neurosurgeons to immobilize the head and keep the head still while performing brain surgery. This is that same dog after surgery. The dog had to be taught how to walk again. We are performing a brain cancer clinical trial in dogs at Johns Hopkins University. All study protocols are approved by the Johns Hopkins Animal Care and Use Committee. This is an ongoing trial to assess the effectiveness of yttrium-90 Therasphere delivered IA to slow or reverse the progression of a hypervascular brain tumor. Inclusion criteria includes a hypervascular intraaxial brain tumor greater than 1 centimeter on MRI, restricted to one side of the brain. The dog has to be at least 1 year of age, weigh more than 10 pounds, and the owner has to be willing to understand and sign a consent form. In terms of the timeline, we perform MRI first to identify the tumor type and location, followed by Y90 therapy. After Y90 therapy, we do a PET scan to verify the location of the therapy and also calculate dosing. Follow-up MRIs are performed at 1, 3, and 6 months post-treatment. This is our first clinical trial patient. This is Billy. She's a 9-year-old female spayed Boston Terrier. In late December 2018, she started circling to the right at home. Owners didn't do anything about it. Then in early January, she had her first seizure, and she had several seizures after that. They brought her into a neurologist who recommended a head MRI at Hopkins. We performed a head MRI, and we found a highly vascular mass effect of the right rostral brain. This dog ended up enrolling in our clinical trial, and she underwent Y90 therapy on January 31st. She did exhibit side effects of the therapy for about 2 weeks after treatment. Here are some of her images. The top row are T2 flare images, bottom row are post-contrast images. The left column are what Billy looked like before we treated her. The middle column are what Billy looked like, her images at 1 month post-treatment, and the right column are her images at 3 months post-treatment. Billy is doing fabulously. This is a picture that her owner sent me last week. They are thrilled with how she's doing. She has 0 signs of a brain tumor. This is just a single case. We're still enrolling patients, and we don't have enough data yet to discuss results yet. In terms of advantages and disadvantages of clinical trials in pets, I could spend an hour just talking about that, but I just want to mention a few things. Cancer in dogs is more similar to what is seen in humans. Canine clinical trials can be performed in a shorter amount of time and for considerably less money. Dogs have an accelerated aging process. Cancer is a leading cause of death in dogs. Cancer incidence in dogs is 4.5 times what we see in people. Dogs respond similarly to humans, and they develop drug resistance and metastasis just like humans. Some of the disadvantages: it's more expensive to do dog studies than it is to do mouse and cat studies, mouse and rat studies. We need the same equipment as we use for people. And we still need to follow the traditional guidelines for human clinical trials. So this is a typical flowchart of what we would look at for clinical trials in pets. And I often get investigators that come to me and they say, I've got a therapy, and they want to jump to a phase 3. They want me to get patients with a certain type of disease, and they want to try drugs or a therapy. And we have to back up. Has that drug ever been tried in the species? Do they know what dosage they want to use? So we do follow the same guidelines that are followed in human clinical trials. Yesterday, Monica asked, how do we make things better? And in conclusion, I answered that one of the ways we can do this is by incorporating veterinary clinical trials into research institutions. Pet owners want to be a part of well-designed and executed clinical trials. They are thrilled to be part of these trials. And if we tell them that we can possibly advance human medicine and or veterinary medicine, they want to be a part of this. Veterinarians understand the importance of clinical trials, and now I'm trying to demonstrate to the research community the tremendous importance in veterinary clinical trials. So the answer to brain cancer may be walking right beside us. I want to thank all my colleagues who have helped me with my work, and I'll be happy to take any questions.
Thank you very much for the talk. Are there any questions?
No, that was spectacular. I was unaware it was taking place at Hopkins, so it's great to see, and I hope that Neurosurgery will be collaborating as well with you. One thing I know when we looked years ago at pet brain tumors was, or in terms of doing clinical trials, was that, at least my understanding at the time, was they have a much higher incidence of spontaneous regression, which made efficacy studies a little difficult to interpret. Is that true in terms of natural history of some of these gliomas in dogs and so on?
I don't think that's true. In my experience, I've never seen a brain tumor spontaneously regress.
Thank you.
Do you know what the particle size is for Theraspheres?
There are a few. Yeah, I can look that up for you. I don't know off the top of my head.
Where it looked on the imaging slices you showed, there weren't any stroke lesions that I was able to see. Did you, if you look through the entire sequence, did you have any ischemic lesions in the brain?
Mm-hmm.
Yeah.
Yes.
This radioisotope can be visualized in PET or SPECT, and if so, you did it, or?
Yeah. Yeah.
So
following.
but you haven't shown the images. Okay.
I have a kind of an offbeat question. Some people have PET health insurance, I've heard, right? And I'm sure it's expensive. It's you say brain tumor is so frequent. Is that covered? And what is the standard form of treatment?
So there is pet insurance. Only about less than 3% of the pet owner population have health insurance. So it's very minority. And one of the issues we have with performing clinical trials is in human medicine, when you put a human clinical trial together, insurance will usually cover standard of care. So our dogs needed to be in a hospital after therapy.
What is the standard of care for brain tumor in general?
So it depends. Our dog's actually capable of going home, but because this is a clinical trial and we want to know exactly what's going on and we don't want to miss any side effects, we're having them hospitalized. So it depends. If you're doing brain surgery, of course, those guys have to be in the hospital for a couple of weeks.
Okay, then I'll take over the moderating session. We have Jaji, also known as Kevin Liang, who previously was with our group at Johns Hopkins, is now at the Janelia HHMI Research Campus in Ashburn, and he will be talking on intravital two-photon microscopy, state-of-the-art, and prospects for clinical applications.
Thank you, Jeff. I'm Kevin, and I want to thank the organizers and Merrick for inviting me. It's good to see so many old friends here. So it's my great pleasure to be here and tell you about the work in Janelia that I did using a two-photon imaging, two-photon microscope to image the mouse brain. Also have some thoughts on the potential clinical application, but it seems very too ambitious, so preclinical application. So yeah, before we talk about two-photon, let's first look at what's going on in the conventional microscope. So the excitation light comes here. It go through the object lens, illuminate the sample. Then the emitted light gets collected by the camera. Then we get images. So this works perfectly as long as the sample is super thin, and you can get amazing images even by the conventional one photon. However, it won't work very well for the in vivo brain imaging because, first of all, the brain is highly scattering. This is how it looks. The mouse brain already put a cranial window, glass in here to image it. So it's scattering. Just imagine in a foggy morning, you try to see the trees in the distance. It's really hard to see them clearly just because the light cannot travel straight. Another thing is the absorption of the light, because people have done this. We found that these visible light can be absorbed horribly in the live tissue. So what they found that tissue optical window is 600 to 1200 millimeters. That is actually the infrared. That's the best. Now those visible light. So what happens is that if you try to use this to image the mouse brain, you see that first the light got absorbed, then it gets scattered. So it's really a smear. It's exactly how you find it in here. So this is a GCAM calcium indicator in the mouse affected valve. Then image with this conventional one photon. You can see there's something going on here, but it's very cloudy. It's hard to see the structures in here. So it's like looking through the tofu or cheese. The scattering, absorption, and homogeneity, that kind of screwed up the resolution. So it's really hard. It's not possible to image the live brain that is beyond 100 micron or even shallower. So to explain two-photon macroscopy, let's first look at this Janowski diagram. Fluorophore has two electronic energy states. One is S0 is the ground state, and then S1 is the excited state. If you use the blue light that is energy high enough, then you can excite the fluorophore from ground state to excited state. That will be internal conversion, then eventually it goes back to the ground state, giving off some emitted photons. And here are the green photons here. So for two-photon excitation, you use 2 photons of half the energy of the blue photon here. If the 2 photons arrive at nearly the same time, then they can do the same thing as the blue light. They can excite the fluorophore, then internal conversion, they emit green photons. The tricky part is that these 2 photons have to be absorbed at nearly the same time, within 1 femtosecond. That's actually 10 to the power minus 15 seconds. So it's really short. That actually becomes the actual, the greatest advantage of 2 photons, because just imagine, because the likelihood of coincident absorption of 2 photons of the molecule is so low along the illumination whole path that the visible light can only be emitted from the focal point. Then you get rid of the scatter light from autofocus. This can be best illustrated by the image from Berkeley. You can see this is 1 photon along the light path. You got all of the autofocus light that just contribute to the background. However, for these 2 photons, this excitation is confined to the focal point. That's why for 2 photons, you collect all the light from the field view. That all contributes signal instead of background. So that's actually nicely addressed the scattering issue that I mentioned in the first slide. And also because 2 photons use this infrared light, so it's also addressed the absorption issue. So that's why 2 photon has been widely used since the invention in the 1990s for in vivo brain imaging. So here just my data, show you what it can do with 2 photon in the live, all live mouse. And we can use it to do morphology. This is a layer 5 neuron in the neocortex of the mouse. You can do time lapse. Here is so I use lasers to damage the cell. So these are microglia. They all get labeled by GFP. You can see that after you damage the cell, the other cells can process, and we can see the dynamic process of clear how tissue repair. And we can do even longer. Here, just a minute. You can see we can also do a few days. Yeah, these are adult bone cells migrating in the olfactory bulb. So I don't have time to dig in the biology stories here. These are because it's like about relevant to this conference. If we can use 2 photons to look at the blood vessel dynamics. You can see here I use a dye to stain the blood vessel in here. Also the cells, this is more likely red blood cells. It's migrating slowly in here. Then you can really look at what's going on in here at very high spatial and temporal resolution. And also you can image the function of the cell depending on the sensor you use. In this case, I use a calcium indicator. Then you get neurons express it, then image the brain. Then you can show them out some grading. Then you can analyze the data to see which grading is preferred. So this all 2 photon can do many of these things, many things. Next, I'm going to tell briefly about what I have done in Naji's lab in Geneva when she was still in Geneva. Now she moved to Berkeley. How we push the limit to photon imaging at the 3 aspects: the speed, scale, and depth. By speed, I mean the 2 photon volume rate. I mean how fast we can image the whole brain instead of just to get 1 layer of brain, because in the brain the neurons are 3D structure, so it won't help much if you only get an X1 plane, XY plane. So this is a conventional rig. You can see that 2 photon laser goes get a gobble is like do the scanning job, then it goes through into the objective and converge into one focus. As I showed you before, is the point focus, which we call Gaussian focus. So it just do the raster scanning for 1 plane. This is how you get one plane of image. This is called 1 frame. To get in depth, in the 3D, you have to scan at Z. However, that's the part that slows down the speed if you try to image the whole well volume. So you can see the frame rate is how fast you can get one frame. That could be fast, but this scanning could take a long time. So it's slow and sensitive to motion. So this is what happens if you use a Gaussian beam. You can see it's scans like this, which is very slow. This is what you get from this sparsely labeled neuron. So you get a little bit at each one plane. For the whole of volume is slow. Then just imagine, well, in this case, we extended the focus of the Gaussian beam at Z direction. So we like stretch this point. Now the advantage is that we don't have to go through the whole procedure along Z. Now we just do one scan and we get projected image of the whole volume. But in this case, the volume rate is the same as the frame rate. Then we can image at fairly much higher speed than these just one Gaussian beam. So this is what we use. It's called a bezel beam. And we using bezel beam, we can do really like things that people never done before. You look at this cell. This is a cell, a very big cell in layer 600 micron deep. Usually what people do is that they can only image this part or this part, this part. It's really hard to get a whole picture of the activity through all these whole neurons. But now we can do it because we use the Gaussian beam. We just get a one shot of image, then we can get a whole structure of this neuron, project the image at the image that's fairly high enough to look at the activity itself. Also, we can use the bezel beam to do blood vessel imaging. In the brain, you know that blood vessel is like they branch a lot. Then if you only look at one brain, it's really hard to see anything going on here. So this is Gaussian, the conventional one. You can see that 100 micron deep of the brain. The frame rate is 2 Hertz. So volume is only 0.02 because we get 100 sections from 1 micron to 100 micron. So this is a projected image of this stack. If you want to image faster, you use the bezel beam. We can now image faster at the frame rate of 2 Hertz. So you can now really see everything in here, these structures, and you can image faster than that. Because this frame rate you can change, but whatever you do, you can just get a much faster volume rate compared to using the Gaussian beam. So then about the scale, that means how big we can image, because if you only image one single neuron, that won't help much. If you want to image, like see the interaction with the neurons activity, or blood vessel, like in a bigger picture. So we can also make this really huge cranial window. This is 1 millimeter. You can see this is like a 5 millimeter, 4 millimeter in this case. It covers quite a few multiple cortexes. This is a visual cortex, somatosensory, and a lot of other cortex in here. And we can express GCAM6 calcium indicator in there that image their activity. We can also do across hemisphere in here. You can see this across the two sides of the hemisphere with a calcium indicator. Now we can look at the neurons from different part of the brain. They're across. So here, this is a large cortical area functional imaging of these 1.5 millimeter, 3 millimeter, and 600 micron deep volume. So we can all see activity of these neurons. That's a lot of data generated. So about how deep we can image, because as we talked before, because of the scattering problem in the brain, it's very hard to image super deep. Beyond 1 millimeter is not very, it'd be very super difficult, because just imagine if the focus is so deep that you can almost get nothing from here. It's just a noise. So there's indeed a limit for the two-photon imaging about the depth in brain. So to resolve the issue, people have found out that using the gradient index lens, which can converge light into a point in here, just to work like a lens. So what happens is that you just insert the lens into the brain where you want to image, then image on top of here. It's kind of like reusing it as a relay lens. Of course, it's called minimally invasive imaging, so you don't get too much damage in here. But the thinner, the better, of course. But the thinner, maybe you had a smaller field of view. So this is my data in here. So we try to image the hippocampus, the CA1 area. So I implanted the green lens in here. Now you can see this is a wide field image. Again, because it's wide field, so it's poor resolution. then we can use two-photon imaging, just the image through the lens is the same mouse. You can see that these are the same exactly the same field of view. You can see this, these stacks. The resolution is great, but again, if you use the Gaussian focus, the volume rate is very slow, so you can't image all the cells as one shot. Then we add the bezel beam to this green lens imaging, turning this Gaussian point focus into the bezel beam. Then image the mouse. You can see in here, in this case, we use the 1 millimeter diameter green lens. Then you can see this from 0 to 55 microns deep neurons. The color indicates how deep they are. Clearly, they are not in the same plane. So to image them, we can use the bezel beam. Now we can image them at a very high rate. Also, the resolution is pretty good. You can see, actually, we can see the result of the genetic spines in here. So, okay, this is what I did. Then next, I'm going to talk about the perspective, the potential clinical applications. As I talked to America and computer, we have this idea. Actually, Mir is very passionate about the idea of using this green lens to image the brain structures. So here is just the brain size from different animals, from rat, cat, dog, sheep, pig. In here, human is super big. So if if we have, think about if we those companies now do have the longer green lens. In this, for example, in this case, it does have this very long green lens. This is 3.6 centimeters. If you put it here, so it's actually pretty big, and you can see that it can actually give us access to most of those brains, except the human brain, because it only kind of penetrates only half. But for pigs and other like sheep, they can they are long enough to go to anywhere of the brain. So that gives us the the potential to image them. Just imagine if you have, for example, pig brain implanted, then do whatever treatment in there. But now you not only you can image them under fMRI, but you can also use two-photon imaging to look at very high spatial and temporal resolution and see what is really going on there. So it's like a transcale imaging platform from MRI to two-photon imaging. That's the green lens just bridges the gap. Another thing that I want to mention is a more recent paper. They use two-photon to block the blood vessel, then to like block, because these blood vessels are like burning blood to the cancers, so it can also be treatment. That actually reminds me some data that I have. Just sort of break the blood vessel with a laser, then we can just monitor what's going on here. In this case, the microgear just try to repair the brain. So I just want to show you to prove that it is really possible to block the blood vessel using laser, and for shallow ones at least, that can be used as a stroke model of therapeutic to animals. So the take-home message is that the microscopists are actually pursuing the micro two-photon imaging in terms of
I can't make that.
like C,
I can make it this week, but not
I
next
think
week.
the
I probably will be away. I'm not
very attentive on this point, on these advances, and see if there anything that can be utilized. So what we think of now is that this green lens might be the whole promise to be combined with the MRI or the other clinical imaging paradigm to provide the better resolution. It's not additional results, but can give you more insight about this mechanism and what's going on. So thank you for your attention.
Thank you, Kevin. Any questions from the audience? I have one on that Prisma tricolor thing of the challenges of the two-photon microscopy and clinical applications. One thing I think you didn't mention is the fluorescent dyes. I'm not an expert in that. I know there's one dye, indocyanine green, that surgeons use with an enzyme or a substrate that's cleaved by caspase to do superficial surgery, especially of the peritoneum, if they can't feel it. What about development of approved dyes and things, if this effort is being applied clinically?
Oh, yes, that's actually something I intentionally not to mention here because it's just imaging like the equipment part. So yeah, definitely it's possible to develop new dyes. You know, we can put some fluorescent molecules that can. That's definitely possible. I think. Yeah, that's something. It also includes some sensor, but it didn't. I also involved in a lot of work using the sensors. For example, these GCAMs or exon targeted sensors. So sensor is another big field that we are actually pursuing. Actually, in one of the examples, I showed the layer 5 neuron in here. These are actually dye development. So I collaborate with Luke Levis, and he developed new dyes that is brighter than rod means, and we can just use this like a combination of genetic encoded dye and the sensors and the dye. So you first express the dye in the neurons, but you cannot see them. So there's no background, right? And then I inject the dye, then it can stay in the neurons. So that's a good one.
Okay, thank you. Then we close the session. Thank the speakers again, all three. And then I'm not sure there's a coffee break. Is the keynote speaker showing up? Let's just go straight. And then we need to switch chairs, I think. Right? Oh, still we switch chairs? Okay, so I can go. Yeah, okay. Yeah. That's what I'm actually. Yeah.
Okay, so now we are coming to the next part. Now we have the keynote speaker. We are lucky that we have at least one keynote speaker because the one for yesterday, because of the private reasons, so his mother worsened suddenly, and then he needed to stay in England, so he couldn't come. Luckily, so we have the Sean with us today. I'm sure that he will deliver as always an excellent talk. Sean is a professor of neurology and director of Stroke, newly formed by him, Stroke Institute at the University of Texas. He's a world-renowned expert in the treatment of neurological disorders, focusing on stroke. And I think he was always, actually, even being neurologist, he was always fascinated with all this imaging. So we discussed for many years, and then we thought it's really great to have a neurologist that will probably speak for the imaging, to adding as much imaging as possible to really be informed, making informed decisions. So thank you very much, Sean, that you agreed to come to us, and then floor is yours. And
well, thanks, Marek. Thank you so much. It's great. I'm really grateful to be able to present on this topic. Marek and Pyotr, asked me several months ago, to think about a talk on the use of imaging and how it's truly advancing our approaches with regards to treatments for patients with neurological disorders. I'm a strokeologist at this point, and have been really focused around stroke for the past more than 10 years now. So a lot of what I'm going to talk about is very much focused on stroke. You've had already a lot of material, a lot of great materials been presented in the area of stroke and vascular disease. So I hope that there's still some areas here that I'm going to show you that you haven't seen yet. And it's really just been an amazing opportunity that they've given me to really go through the literature and think about where we have opportunity and the vision that the organizers of our meeting have in thinking about imaging and where it's going to advance our care. I think is really on target at this point in time. Just these amazing breakthroughs that this conference has been focusing on. So there are already a lot of established uses with regards to neuroimaging and thinking about how we treat patients, I would say. And I've just listed a number of them here that I'm not going to talk about, but I think it's very important to acknowledge in the clinical world, we have to, I think, give a lot of acknowledgement, particularly to our surgeons with regards to the treatment of epilepsy, where I think it's become very individualized and a critical use of imaging. And one can go down this list overall, and I think that one can make the argument that these fields are really advancing, I think, pretty well with regards to the concept of using imaging to guide treatment. So what I'm hoping to talk about is how imaging has become truly established, particularly for acute stroke, but it's moved not just from acute stroke, but now in using imaging for stroke prevention as well, and then talk and speculate in going further down these topics around the future role of neuroimaging in the areas of rehab, stem cells, dementia, chronic inflammation, and then hopefully this will come across as a cohesive talk overall. So in acute stroke, I think everybody understands this. I think at this point it's very clear that the most logical and most important treatment that we have, of course, is reperfusion. And the whole concept here is we have a patient that's presenting with an acute occlusion, a large vessel occlusion. We're either going to give them a thrombolytic agent, that's TPA, or we now have very effective devices for thrombectomy with clot retrieval. And so you've already heard talks on this. I'm not going to belabor the point, but this is truly a very highly effective approach. And then this was the original graph we all saw many years ago on the whole concept of time of brain, that the faster that we can treat somebody from the onset of the stroke, the higher the likelihood that they're going to have an excellent outcome, as shown on this y-axis. The odds ratio for an excellent outcome at 3 months compared to on the x-axis, the time after the onset of the stroke, and how that line is going down. And about that treatment for patients with stroke, we can at this point say that it was really occurring in unselected patients, simply having a CT scan that showed whether the patient has a hemorrhage or doesn't. And so, these types of CT scans that we've been looking at over time has been very important to us. If we see early ischemic changes, that's great. It helps us in our diagnosis and going forward. But I think we might say that this is a very straightforward approach in patients. And where the field is moving to, clearly, we can see here is with regards to advanced imaging. And, this is where, the field is at and where it's continuing to move forward. When we look at work by Greg Albers and many other scientists in our field and actually characterizing a imaging pattern or an imaging profile of patients where we have salvageable brain, this is where we've had opportunity to expand our treatments to a greater number of patients. So for those that don't know this work overall, this has become now part of standard clinical practice. I get these images on my phone for every patient that comes through our emergency department and undergoes imaging that goes through CT scan, CT angiogram, CT perfusion. We get these readouts right away that go to our email. So as defined here, in a patient with a target mismatch, we get readouts here, and the pink area is cerebral blood flow that's less than 30%, regional cerebral blood flow less than 30% compared to the contralateral hemisphere. This has been shown to highly associate with tissue that's going to die very quickly, and has now been classically defined now as a ischemic core, versus an area of hypoperfusion
where there's areas here that potentially are salvageable. And this is a classic pattern of a patient that would benefit from reperfusion therapy. In this patient who was successfully reperfused, the infarct is very small and really corresponds to the area that was initially seen on CT perfusion on scan, versus somebody else, who has, again, a mismatch pattern who wasn't successfully reperfused, and the damage then actually has evolved to encompass the same area as what was shown initially on the CT perfusion scan. So, we're in this time period where the question has become, how many more patients are there out there? Which of these patients and in what setting can we actually find that there's benefit for reperfusion therapy? And, with these articles that have come out recently, Q3, as well as Dawn, we definitely are in an era where this type of imaging, advanced imaging, is helping us with regards to identifying more patients that can be treated successfully and achieve excellent outcomes. So, this has led to a number of questions in our field with regards to how big can an infarct be and still actually there could be potential for benefit. That's a big question in our field, and one in which many investigators are taking up, because what we've learned so far is that there are excellent candidates out there for thrombectomy who have small core infarcts with large areas of hyperperfusion. Well, what about patients that have larger core infarcts? And how big can the infarct be before we can say that it's futile to engage in thrombectomy or thrombolysis for that matter? And I'm demonstrating to you here, one trial gotten off the ground from an international study that's being led from our center called SELECT2. Our PI is on the Siraj. Sites are in the US, Canada, and Europe. Large trial that's asking that question of patients that have larger infarcts, as shown on non-con CT, or as shown here on the perfusion scan. This is an infarct with a size that is almost 90 cc, but there's a very large area of hyperperfusion. Is this a patient that might benefit from thrombectomy? And that's the next question in the field. And it's that many investigators are asking and posing this question and are engaging in clinical trials overall. But the other side, to this question with regards to how many more people might benefit and where the field is going is, well, what about thrombolysis? Is thrombectomy to be effective for many of these patients? Would thrombolysis also be important and also be a successful treatment? And this is a question that's been evolving over time. We take our lead, first from Mala in Germany, who used MRI to select out patients who might benefit from thrombolysis in those patients who wake up with a stroke. This is a very common scenario in the stroke patient population. Patients who wake up with a stroke, we don't know exactly what the onset time is. Many of us, including myself, have a hypothesis that these strokes occur when they wake up, and that is the onset time. And I think some of the data supports that hypothesis. And so in the first article on the top here, they had used MRI to select out patients based on a mismatch between DWI and flare. And then, we saw the EXTEND trial finally get published in the past month. And that was clearly, another study that shows there are certain patients out there with small cores of infarct and large areas of hyperperfusion that could potentially benefit from thrombolysis. And in the EXTEND trial, I'll just note here, because the paper's fresh, we just reviewed it ourselves in our center, that, in the study overall, these are patients that were estimated overall in terms of the time from stroke onset. You can see here the breakdown, 4.5 to 6 hours, 6 to 9 hours, of those patients who awoke with symptoms. The majority of the patient population is really patients who woke up. And so, I think that's an important point about this. The other important point about the characteristics of these patients was that a majority of these patients also had large vessel occlusion. So some might say, well, a lot of these patients went for thrombectomy, and they benefited probably from thrombectomy, but this study was started in 2010, way before it was shown that thrombectomy could be effective for patients with large vessel occlusions in these unknown time periods. And so many of these patients that were enrolled in the study did not undergo thrombectomy, as we understand it. And so it's become a question of to what extent does thrombolysis work for these patients that are waking up with stroke. And the next big point to raise here is if we look overall at the ischemic core size, it's pretty small overall versus the median perfusion lesion volume is in the 70s. So again, the take-home message is from an individualized treatment perspective, if you have patients with small core infarcts with large areas of hyperperfusion, potentially can benefit from thrombolysis and from that. And I think that in field, will continue to be a question that's going to be pursued more. As we think about that, not just the large vessel occlusions, but how about patients who have N2 and N3 occlusions and further? How many of these patient populations might benefit if there is a mismatch that's found on imaging? And this, for those that are not fully familiar with how we look at efficacy in the EXTEND trial, they looked at the disability score of modified Rankin scale, where 0 is completely cured, 6 is death, and there's a range of scores here on disability. The patients that received TPA in this patient population compared to placebo, there was a higher percentage of patients that achieved excellent outcomes compared to placebo. So we've moved into an era here where we're still, very focused on time-based decisions. The onset of symptoms is what drives our treatment decisions, but it's changing as time goes on to a point at which now we're talking about a physiological clock rather than an actual clock, a physiological measurement of salvageable brain tissue, where we're using imaging-based decisions in highly selected patients. And this is a more precise way of treating patients as we think about precision and precision medicine, precision health. A big question is, how many more patients are we talking about are actually going to benefit from thrombectomy or thrombolysis in these more selected patient populations? There's quite a bit of debate and controversy about this. How many more patients are we talking about? And then I think another important point is that our systems of care throughout the world they're not prepared yet to identify all of these patients who potentially might benefit with salvageable brain tissue, and then to treat them rapidly. These are two separate points overall. Just having some really important discussions with Dr. Yabadal about this and thinking about this in other countries like India, that we need, and then I would say this as well in the United States, patients presenting to community hospitals don't have the opportunity to be evaluated with advanced imaging. And so we struggle enough as it is at our university hospitals to have access to these types of technologies. And this is a big question for us in the field is, okay, well, there are more patients out there potentially could benefit. How are we going to identify them? What kind of technologies can we advance to be able to find these patients and to have them that they can actually benefit? Another area that is coming up from the ground, from the graveyard, because of the success of reperfusion and finding patients that could benefit with salvageable brain tissue is neuroprotection. And for those that have been in the field and have watched the field of neuroprotection completely, rise and fall, it's interesting to see it come back up again. And so for those of you that don't know, that the whole concept of developing neuroprotective agents is based on the idea that it's possible to develop drugs, approaches that can intervene on the specific pathophysiological mechanisms that are activated in cerebral ischemia. The neurons that are undergoing cell death with very active biochemical mechanisms like glutamated cytotoxicity, calcium overload, free radical mediated mechanisms. Many different agents have been developed to intervene on these different pathways. And when you think about more than 50 drugs that have been taken forward from in vitro studies, animal models, clinical trials, and we don't have any agents that have actually been found to reproducibly improve outcomes on phase 3 clinical trials when it comes to enrollment of acute ischemic stroke patients. That involves over 20,000 patients, millions of dollars spent by large pharma that have withdrawn from this area overall. And even despite advancements that we've had in clinical trials in which the neuroprotective agents would be implemented in the field, in the hospital, in the ambulance settings before the hospital, have we not found that these drugs work. And of course, there's many different reasons why that may be the case, but having the ability now to image salvageable brain, has brought back neuroprotection in some very potentially specific ways that have been covered in one of the last DARE meetings that many of us and many of our colleagues have attended. And the overall concept here is it's possible that we could extend the treatment window, specifically in patients that undergo reperfusion therapy with TPA or with thrombectomy. And while that's an intriguing concept and is being studied in some patients, we also should also indicate that that shouldn't dissuade us from still considering and really emphasizing the point that we don't want to delay TPA administration. And where I think that there could be some very exciting opportunity could be patients that are at outlying hospitals in the community that are identified as having large vessel occlusion, that have salvageable brain. They got to get out of that hospital. They got to get to a thrombectomy capable center. In the U.S., those transfer times are estimated anywhere from 90 minutes, 2 hours, or even several hours. Perhaps these patients might be excellent candidates for neuroprotective therapy, something that could help to slow down infarct progression while they're en route to a thrombectomy capable center. But the point here is that neuroprotective agents are not likely going to work in patients who don't get successfully reperfused. And that's where, the intriguing concept of thinking about how these drugs could be tested is coming into play. And I've listed a few other possibilities because you had some talk about intra-arterial therapy and thinking about neuroprotective approaches. So what do we need now? Well, there's a lot of different questions when it comes to thinking about it from I would say some precision health, from the perspective of personalized medicine. We need CT scans to be able to tell us if we've got salvageable brain or not. I'm not really sure that community hospitals are going to invest in getting CT perfusion. And so this is where machine learning and deep learning are starting to be looked at in many different ways. Is it possible to be able to use, for example, the CT angiogram, which is often commonly available at community hospitals, to actually be able to identify tissue which is ischemic or is at risk? Is there a way to actually identify salvageable brain tissue on those modalities alone? And there's a lot of work going on in this area, including at our center. And it's fascinating as well to see how MRI is becoming miniaturized, and I'm really curious to see where that field is going to be heading. It's really interesting to see. I almost showed some pictures of these portable, smaller and cheaper MRI scans that are being developed in different places, and how that might be part of our future overall, and whether there'll be investment there to come up with approaches for patients that are in the outlying facilities to identify more patients that might benefit from reperfusion therapy. So I wanted to move on now to stroke prevention, because from the acute stroke side, it's become very clear that we need imaging to guide our treatment decisions. But stroke prevention as well has changed, and we do use imaging now to help guide our treatment decisions about how to prevent a secondary stroke. And so, we all know, of course, that aspirin is one agent, which has been consistently recommended to be given to our patients with acute ischemic stroke. An antiplatelet agent has effect to reduce mortality, to reduce overall risk for another stroke. And that's been the case for decades, but we use imaging now to determine if the patients actually have intracranial arterial disease, because we do have clinical trials which have actually advanced our clinical practice with regards to what antiplatelet agents we give and in what approach and for how long. And so it has been important to use imaging now to guide our decisions in stroke prevention. These are just images taken of representative examples of intracranial arterial disease, left MCA stenosis, a basilar stenosis, and right MCA stenosis. And the concept here is looking for patients that have atherosclerotic disease. And I'm going to take my lead here from the man who hired me, Jim Grata in Houston, who put together an excellent grand round talk and taken some material from his slides here. But I think the concept here, and what he's emphasized, I agree here, is that we do have enough data now to personalize secondary stroke prevention. If patients are found to have intracranial or even extracranial severe atherosclerotic disease, there are clinical trials, which I'll talk about in a second, which emphasize from the results here, both the Sampras and Walker trial, that we should actually give dual antiplatelets, aspirin and clopidogrel, for 90 days in these patients, and it has to be done quickly. very quickly within the first few days to have an impact on this disease. This has a very high incidence of subsequent stroke. So to have an effect, we have to give these agents quickly. And then some very recent trials, the CHANCE and POINT trial, have come out. Different patient populations, but somewhat of a similar method. The patients who have mild stroke, NHO scale scores of 3 or less, or high-risk TIA, they also benefit from dual antiplatelet agents compared to monotherapy, but for probably the treatment duration should be a short period of time because of the risk of bleeding overall. So we see most likely from these trials that the greatest benefit probably within the first few days after a stroke to really reduce the risk of having a second stroke or having the first stroke after TIA, especially in patients who you actually do imaging and find that they've had multiple infarcts. But this is probably not the case for patients that have just had one lacunar infarct. Probably dual antiplatelet agents is not the way to go. That's not an effective approach, and that's one single agent is probably best. And the intriguing thing as well is that among all of the factors that play roles here, of course, in disease, age, gender, ethnicity, they seem to be far less likely important compared to the presence of cerebral arterial disease when making decisions about who benefits on dual antiplatelet agents versus monotherapy. So this is a graph of the Sampras versus the Rocket trial. These were randomized controlled trials of patients with intracranial arterial disease. They were randomized in the Rocket trial. They were randomized to aspirin and Coumadin. In Sampras, they were randomized to intracranial stenting or to dual antiplatelet agents along with optimal medical therapy. And, you know, when Simon Chartaverdi put this paper out, it was really very striking, comparing the cumulative probability of having a primary endpoint of vascular event or stroke in this stroke patient population. And you see here that compared to the Wasset trial, the Sampras study shows that there's a significant reduction early on after stroke if you place these patients on dual antiplatelet agents compared to being on aspirin or being placed on Coumadin. But overall, the graph also shows that there's pretty high incidence of stroke in this patient population. And then this is a summary data of the CHANCE and POINT trial. Again, these are trials that have randomized patients with mild stroke to TIA, to dual antiplatelet agents, or to aspirin alone. And the first striking point here is that those patients that are placed in dual antiplatelets versus monotherapy, the opportunity is really at the early stages after stroke to reduce the risk of a subsequent event. In this time period, the first few days, is really what was found in the CHANCE trial, and the same data were found as well in the POINT trial as well. And then what was important as well from the POINT study, as you can see here, is that the risk for bleeding starts to go up over time in these patients. You can see it past 30 days in patients that are placed in dual antiplatelets versus an aspirin alone. And so the data that came out from these studies indicates that it's important to be placed on dual antiplatelets for patients with minor stroke and TIA, but probably not for a long period of time, probably 21 days rather than 90 days overall. But again, imaging has been very important here, even in this patient population. Who are the ones that truly benefit the most? Well, what they have found here is that in patients that are found to have just, for instance, a lacunar infarct, this graph shows that there's really actually no difference between the groups that receive dual antiplatelets versus aspirin alone, versus the patients that have multiple infarcts. These are the patient populations that actually benefit the most from dual antiplatelets versus a single agent in of itself based on this graph up here. And so it's been extremely important now to us to be able to have imaging obtained on our patients, MRIs, also getting angios, whether it's MRA or CTA, in all of our patients that we hospitalize, because we actually now make more personalized, individualized treatment decisions for these patients. As I move forward now on this continuum now into the stroke recovery world, now I'm getting far more speculative, but this is an area, if there was ever one that needed more personalized treatment approaches, it's in rehabilitation and recovery after acute neurological disorders. And so I want to just make a few important points here overall. And I think, the literature now has reached the point at which we can confidently say that white matter tract imaging and understanding the injury to white matter tract is important when planning a program of therapy and care, for patients that have been impaired or disabled from acute neurological disorders.
And the prototypical example is the corticospinal tract and its importance to motor outcomes. And so I do believe that based on what we now know from studies, that the degree of corticospinal tract damage affects motor recovery and probably response to therapy as well. And that a very severely damaged corticospinal tract, I'll put out as a question to you, do we really think that PCOT is therapy actually going to be helpful? I put that out as a question. Do we need another strategy for these patients? Recovery in patients with reduced integrity of the corticospinal tract probably very much relies upon other pathways as well. And I'll give a few points around that and show a little bit of data. And then I'll leave this particular section to talk about white matter imaging, talking about how it potentially could guide stem cell clinical trials and potentially stem cell treatments in the future. So what I'm showing here is this is some work on tractography provided by my colleague in our stroke institute, Mohammed Haq. This is a patient who had a stroke and the infarct is shown here. And here in relationship are the corticospinal tract, showing the infarct touching upon, enveloping the corticospinal tract, and this patient had a significant hemiparesis. And the part of the point here is that it's really a figure to summarize overall what we're learning here, that lesion location really does matter in thinking about recovery after acute neurological injury. That the location and its relationship to white matter tract associates with the severity of the deficit. It's predictive of recovery, probably even better than the initial clinical severity of the patient, and that it probably should drive personalized treatment protocols overall. This work and this point, I think, was very eloquently shown in a study that was done by Dr. Schlag in Boston with colleagues as well at the Medical University of South Carolina, in which they put out this paper looking at the relationship of infarcts to the location of the corticospinal tract and to the extent to which the infarct actually enveloped or involved the corticospinal tract. And so they show here overall the blue is the infarct, the red is the corticospinal tract, and in this patient you can see here the corticospinal tract is involved by the infarct, and they came up with a concept called weighted lesion load. How much the corticospinal tract is involved, how much the infarct itself, the relationship to the actual corticospinal tract. Here you can see here this is a big stroke, and what they were actually examining was clinical recovery of the motor, the impaired arm on the Fugel-Meyer upper extremity score here. They're also looking in a quick step for compared time points in the acute setting versus the 3 months. The lower the score on the Fugel-Meyer, the more impaired the patient is. The patient showed really no improvement, very low score overall because of its involvement of the corticospinal tract. Compared to another patient, comparable size of the infarct, but in this particular patient, it had spared a lot of the corticospinal tract, and this patient made a very nice recovery, went from 11 up to 55 on the Fugel-Meyer score. And this is a patient with a very small infarct, but unfortunately involved the corticospinal tract and did not have much recovery on the scale. And so I think this kind of work has really been pivotal for understanding that, and I would wish that we actually could have imaging done on our patients when they come in the hospital so that we can actually see the extent of the involvement of the corticospinal tract in thinking about motor recovery and motor outcomes. This is another example, a bit more extreme overall, of a patient of mine who had a stroke. This is 3 months after their stroke, right MCA stroke. A lot of the cortex was spared, but unfortunately a lot of the deep territory was involved. And unfortunately, when we did tractography on this patient, and we seeded, from the pond, trying to go up, unfortunately, we don't get much of a signal. And we tried, to look for the tracks by doing tractography in a number of different ways, feeding different locations. Overall, we see the corticospinal tract fairly nicely on the other side. And this patient is hemiplegic, no movement at all, no finger extension. And so, a big question I think in the field is, unfortunately, the question arises, would therapy work? Would physical therapy, occupational therapy, with the conventional modalities that we have for this type of patient, any intensity, would it work for this type of patient? Or do we really need to be thinking about a different strategy?
overall. And if we think about it and then look overall, we do see that there's signal here. Fractional anisotropy, was looked at here in the ponds, and there was signal. So it's a disconnection syndrome more than anything else. There still is a corticospinal tract to some extent in the patients down below. And the question really becomes, what else can we do for this type of patients in the future? But it has to be something different than our conventional rehabilitation therapies. Another point is that it's not just the corticospinal tract that likely we need to be paying attention to when it comes to motor outcomes. It's very influenced by work that I just recently saw presented by Professor Hummel in Switzerland. It came from a talk in Finland where he presented this type of data overall, showing that the connections between the premotor cortex, the ventral premotor cortex, and the motor cortex are actually important when it comes to motor outcomes in our patients overall. And so, this here is showing from some of his work here, those actual connections between the M1 and the premotor cortex. And in this study that he had done with his group overall, what he had found was that in patients that actually have impairment of the corticospinal tract, the degree of their motor outcome is very much dependent upon the connections between the motor cortex and the premotor cortex. So overall, in patients that have the integrity of the corticospinal tract, which has been compromised, is measured on fractional anisotropy in the range of 0.6, where 1 is normal, 0.6 shows quite a degree of impairment. These patients are in this zone here. And in this graph is showing expected residual motor output. The extent or the degree to which patients can improve is very much dependent upon the integrity of the connections between the motor cortex and the premotor cortex. However, in patients that don't have much damage to the corticospinal tract, those are these patients here. And actually, it turned out they do not rely upon the connections between the premotor cortex and the motor cortex. So there are differences depending upon the extent to which there's damage to the corticospinal tract. But this overall supports the hypothesis that there are areas, secondary motor areas, which are involved in recovery after stroke. We know that's the case. And I think this has true implications, as Dr. Hummel has mentioned, around therapy in and of itself. Brain stimulation is a very common modality that's being examined to be able to promote recovery in patients with stroke. And it may be for that type of modality, perhaps that should be directed more to the premotor cortex in patients that have impairment of their corticospinal tract rather than to the motor cortex. And then as I come into this next area here, for those of us that are very interested in white matter spectrum imaging, it's becoming more and more interesting how it could be used. This is a patient of ours that was enrolled in one of our clinical trials, treated with bone marrow-derived cell therapy by an intravenous administration. And the patient with a left hemisphere stroke, and this is 1 month going all the way up to 24 months. You can see here that the thinning of the corticospinal tract for 3 months. We know that there is delayed Wallerian degeneration of the corticospinal tract in patients after the onset of injury. So this was not surprising. What was surprising is that we saw the signal come back over time. And this is just one patient. We did analyses on other patients in other ways. Here's another patient with a different stroke in which we looked at the level of the pons, in which we see here, we're looking at fractional anisotropy. It's normal on the contralateral side for blue signal. We only see red here because these are contaminating fibers that are not the corticospinal tract. And what was interesting to us is there's another patient that over time, from being enrolled in our stem cell trial, we see the signal changes over the blue over the ensuing year. So again, another patient that suggests the possibility that we're seeing the corticospinal tract come back. Again, these are not randomized controlled trials, and there could be a number of reasons why we see the signal coming back. But here's a patient enrolled in a traumatic brain injury study that received bone marrow-derived stem cells. This is corpus callosum, a normal person. And then we have a patient who had traumatic brain injury at 1 month versus 6 months. They did not receive stem cells. And here's a patient at 1 month to 6 months who had received stem cells. In our study, we see here quite a bit of preservation of fibers in the corpus callosum. Now, it's become a question of how to do this in a quantitative fashion. and we've been looking at that in a number of different ways. This is a graph showing how we've measured the global changes in white matter volume in patients who received stem cells versus those that did not. And overall, what we can see here is that in patients that in our adult traumatic brain injury study led by my colleague Chuck Cox, we can see here that from 1 month to 6 months, we see this is the amount of reduction overall in white matter in the cortex versus in patients who had received bone marrow-derived cell therapy. Quite a striking difference, but there's not anywhere the same extent of ongoing degeneration of white matter in these patients. We can quantify in a completely different way. We can quantify looking at fractional anisotropy at the level of the pons of the corticospinal tract. And I show here that in patients in the control population in traumatic brain injury, 1 month to 6 months, we see a reduction overall in the integrity of the corticospinal tract. But in those treated with bone marrow-derived cells, we don't see any actual reduction overall. So we are starting to quantify our data in finding that there appears to be structural preservation in some capacity. Now, we don't understand the mechanisms behind it, but I think what this type of data is leading us towards is that we could use white matter imaging to determine potentially in the future when to treat, depending on the degree of injury, what are the treatment goals. In fact, our phase 2 trial that Dr. Cox is running in adult traumatic brain injury is looking at imaging endpoints as primary endpoint overall. To what extent do we see a treatment effect on structural preservation in contrast to clinical outcomes necessarily being the primary outcome? Still needs to be important in phase 3. Another potential question we could use imaging for will be, well, which areas of the brain are more responsive to this type of treatment in the future? What connectomes or connections do we think could be preserved better than others? We could see that maybe as part of our future. And it's clear that we're going to have to get more into network connectivity analyses to better understand who's going to improve clinically from these types of approaches, motor outcomes, but as well as cognitive domains, as well, particularly in patients with traumatic brain injury. So moving from there now, and continuing now to patients with chronic disease and neurodegeneration, and I only have 5 slides left. Tried to spice it up just a little bit here as a stroke neurologist. What am I talking about? Alzheimer's disease here. But I think it's just really important since, if we're going to have a talk about imaging and how we're advancing personalized medicine, these have been clearly advancements in our field to be able to image amyloid as this beautiful example of PET-MR shows the amyloid in the neocortex. But tau imaging now being available to us as well, showing tau intensity on PET in the neocortex as well. But what we've also learned is that many patients with neurodegenerative disorders caused by Alzheimer's disease are really mixed disease. They harbor a lot of cerebrovascular disease as well. And I think it's important that we are thinking about, and many people are raising this question, it's not just the amyloid and the tau, but they also have vessel disease. And, a lot of these patients have cerebral small vessel disease, at least that's what we learn about, that's what we hear, but the question is, well, what exactly is cerebral small vessel disease? And in this respect, this is where I link this back up to stroke again. There are many different types of cerebral small vessel disease, as shown here in this beautiful review that was done in the Journal of Stroke, a Korean journal, and I'll just show some very quickly review. This is white matter hyperintensity. Many people will recognize this in our patients. Many patients with Alzheimer's disease have white matter disease. This is another example of enlarged perivascular spaces. And then here are the prototypical examples of microbleeds. This in the subcortical area, most likely due to hypertension, leaky small blood vessels, versus microbleeds occurring in the cortical, subcortical zone. This is best seen in cerebral amyloid. And it's important, I think, again, using imaging, we're going to need to better define what we mean by patient has cerebral small vessel disease, whether that's as a cause for dementia or because we see this in patients that have neurodegenerative disease from Alzheimer's or other disorders for that matter. And the interesting thing about this, is that there's a lot of overlap between Alzheimer's and cerebral small vessel disease. And we clearly, at this point, see literature indicating that small vessel disease contributes to Alzheimer's disease. Severity is directly linked to the network disruptions that occur in the brain, and that vascular risk factors are also the same ones for Alzheimer's as well. So a future for Alzheimer's disease, speaking from a cerebrovascular perspective overall, that is it possible that our phase 3 trials of anti-amyloid treatments, I know not to say fail because they're not really paying attention enough to these patients with small vessel disease? It's certainly possible. They think they do a good job of trying to exclude patients that have vascular dementia, but that's not the same thing as patients who harbor cerebral small vessel disease. I'm not saying that these patients have vascular dementia. I'm saying that many of these patients have small vessel disease, and that there's a coexistence of the two. And I'm not sure that the clinical trials are paying attention to this factor overall, and that a more potentially successful therapy for AD is going to have to take this into account. Multimodal imaging, both PET and MR, looking at small vessel disease, I think is in our future when we think about this overall, that as we learn about everything else, it's all about patient selection, and that there's a lot of heterogeneity when it comes to the etiology of neurological disorders like dementia, neurodegenerative disorders. So in the last bit of the talk, I just wanted to speak very briefly on neuroinflammation. It seemed like if I'm going to get a chance to speak on this concept of personalized medicine, neuroinflammation, we of course, many of us know in the room that this is an important factor that drives many different processes and is an important factor in neurodegenerative disease. It's not just an important factor in neurodegenerative disorders, but we also know that CNS inflammation mediated by microglia is very robustly activated after traumatic brain injury and stroke. And that's mediated principally by microglia. Many see this as M1 phenotype. That's a little bit simplistic to call them just M1 microglia, but I think it's at least been a helpful description for us in trying to think about how to do some of this work overall. And I'm just showing some work here, again, from the laboratories at UC Health with Scott Olson and Chuck Cox and several of our other colleagues, that when we do imaging overall, we know that PET imaging has evolved to actually look at the binding capacity to this translocator protein, CSPO, that's in the outer mitochondrial membrane of microglia. And that PET imaging can be used to visualize, I'm going to say microglia, or maybe I should say more immune cell activation. Well, we first wanted to know whether that approach is valid in animal models in neurological disorders like traumatic brain injury and stroke. And so in this work here, we show here this is just control of animals, and this is animals these are animals that have undergone traumatic brain injury. And what we're showing here is that there is indeed this binding, this TSPO binding that identifies microglia in rodents. And of course, the PET imaging I'll show you in a second. But indeed, you can actually see this type of labeling in rodents in traumatic brain injury, the controls versus the actual labeled animals here. We do a close-up of the thalamus in these animals. We see very robust labeling overall. And the reason why this is, I think, from my standpoint, very interesting is because microglia are a potential target for stem cells. We find a lot of interesting literature and a lot of studies showing that stem cells can have an impact on microglia. So the human studies, I think, are getting more and more interesting, and then I do think this has some implications overall for personalized medicine. So this is a study that came out in the Annals of Neurology, in which they had imaged patients with PET using this ligand, PBR ligand, that can bind to this very same target within microglia. And from the perspective of looking at density and binding activity, normal would be down in this range, and the highest activity would be up in the red zone. And you can see here quite a bit of high density in these PET images, and these represent different patients. And you can see here in particular in the thalamus, these are patients with many years after traumatic brain injury that there is evidence for a chronic inflammation that's occurring within their brains. So, we've been starting to study and looking at PET imaging in our patients with traumatic brain injury as well as in stroke. And it's with the same concept, PET using a radiotracer drug with PBR imaging that I've spoken about. And what you can see here is that in a healthy control, overall, in PET imaging, blue is normal and looks pretty healthy overall. But if we actually take a patient with traumatic brain injury or stroke, we see that you can see the yellow color up here, and very different overall compared to the pure blue. And then there's quite a bit of high intensity, as you can see here in the subcortical structures. And just to whet appetite just a little bit, I only have, at this point, we only have data on comparison of one patient treated with stem cells versus one patient who was not treated with stem cells. And so you can see here the staining, I should say the enhanced density, indicating increased immune cell activation in the patients that didn't receive stem cells versus the patients who did receive an intravenous administration of bone marrow-derived cells. Same approach as bone marrow mononuclear cells. Quite a difference between the two overall. And again, this is small samples, one versus one. But this is where we're going overall in our field of potentially looking at PET imaging that can visualize the potential target of stem cell therapies now in patients. And then we can visualize, and one can think about how imaging of this sort could actually be used in our future, that it could actually help us in thinking about choice of therapy, what immunomodulatory approaches we might want to think about for our patients. The dosing could also be very much be helpful for us to figure out, as well as the frequency of treatment could be another area where PET imaging of this sort could actually help us in our future. I wanted to end this in a very speculative fashion here because obviously this is only the beginning and we have a lot of studies to do to know whether PET imaging of this sort is really going to be helpful to us in our future. But this is where I hope our future is going overall with regards to molecular imaging. And with that, thank you very much.
Thank you very much, Sean, for this beautiful talk and very inspiring. We have time for some questions.
Yes, sir.
Either open or close. What are your thoughts about that?
Yeah, I didn't go around because I think there's so much expertise in the room around that. Well, you know, for me, closing the blood-brain barrier has been something I've been leaning more towards because of my concern that of the role of the peripheral immune responses after injury. And I say that with a caveat, knowing that there's good and the bad with regards to immune cell trafficking. But overall, I've been very influenced more recently by studies that are, you know, showing that immune cell trafficking is an important factor that is driving a lot of the secondary injury after stroke and traumatic brain injury. And so I guess I would be very interested to see whether they're trying to stop that flow in some way, whether, you know, trying to selectively modulate the blood-brain barrier in that fashion, you know, would be helpful. So that's, you know, where I side at the moment, you know, with regards to the BBB.
Thank you.
Very nice talk. I have what is your opinion on chasing clots in the medium and small vessels? Right now, the thrombectomy devices that we have are more likely to actually cause damage than actually provide the therapy. And the second question is about rapids and the thresholds they are using. What is your experience with that? Because the CTP perfusion goes into the cloud and they come to you, but you have no control over their.
Yeah, well, I mean, obviously you raised the question that I think, you know, my endovascular colleague is probably going to be even better to answer with regards to advancing the devices further and further into the distal vasculature. I mean, when you asked that question, I immediately started thinking about, you know, the articles that came out after the initial TPA trial that were finding that, you know, what are the vascular lesions that truly actually respond? And we found out that indeed it actually was proximal occlusions that didn't respond very well. And I experienced that, patients with, carotid T occlusions or even M1 occlusions, stem occlusions, didn't do very well when they were TTPA. Some of them did, but it was really those patients with distal occlusions, M2, M3, and going further that time. And so, I think that lytic agents are a good agent for those more distal occlusions. So it's going to take a lot of work, to, I think, be convincing that devices are going to be superior. But I do believe that there's quite a bit of advancement that's going to come in the field over time. I don't know how far, down that vascular tree, where that risk-benefit ratio is going to be shown, and as time goes on, I'm really obviously fascinated to see, whether I think the data is already showing. We don't have a classic randomized control trial for M2 occlusions per se. The data is already seem to suggesting that at least for some patients with M2 occlusions, that thrombectomy would be effective, maybe potentially might be better than thrombolysis. We don't have any definitive RCT yet overall. And then rapid, so this is the downside, I guess, of thinking about clinical care and using clinical decision tools to help us in letting the computers decide for us whether we're going to treat or not. These were visions that many of our leaders had 15, 20 years ago. The computer would tell us go or no go with regards to treating patients. And so that's part of the drawback. We have to accept that or not. And many of my colleagues, my colleagues that I think of in my own center as well, are looking at other thresholds and other types of software as well to see if there's a better, overall approach and algorithm that can be developed to better optimize the selection of patients. So, in my opinion, we're only at the beginning. That we're going to have a lot more work in which there's going to be a commitment to actually trying to optimize that selection process with other thresholds, other softwares, other analysis. So I think that question's spot on about where we're at right now in the field.
Sean, very quickly, you said that for the neuroprotective strategies to be successful, we have to have effective reperfusion, which is definitely key. And you also showed that the patients are assessed for reperfusion at 27 hours. Yeah. Do we have early evidence immediately after thrombectomy about the reperfusion, not recanalization, because on angiography under thrombectomy, we probably can force the perfusion and be maybe happy about the reperfusion. But from the preclinical studies, we have some evidence that immediately after stroke, when we think we reperfuse, actually the parenchymal reperfusion is not that effective.
So the question is, do we have evidence of
how early after thrombectomy or thrombolysis patients were assessed for reperfusion?
Yeah, so the clinical trials vary quite a bit, in answering this question, and I think it's a great question because it's not clear. I think, at least in my reading of the literature, with regards to, obviously there's reperfusion based upon Dickey scores, but the parenchymal reperfusion that you're talking about afterwards, I think is a real interesting question. I was reviewing some of the literature about this, overall, and that to me is not so clear.
There are reasons for the reperfusion to be incomplete or none, edema, vasospasm, other.
Yeah, so that's a great point that you raised.
So let's thank Sean again for a great talk. I think now we deserve a 2-minute break. complex connection because we are streaming. I think we record. Here, is this recorded or only live stream?
No, this is two things. The one is it is a live stream. It is recorded, but after that, an speaker
reject or
approve. So this is it is like without the approval, there's no way that it will be placed somewhere.
But you store it in conference.
No, this is outside. Yeah, this is this Neurosurgical TV. So are they here? They are in Miami. Yeah, they're in Miami. Yeah, and yeah.
What are they trying? Be interested to work with. I would be interested for them to do research.
I'm sure they will be very interested.
What do you know what they're trying?
So the point is that this video. So this is actually the one other guy that is like a pushing forward, and he thinks that at some moment he will be in position to charge someone. We'll start charging, but now he's still on the level of development. So wait.
I would love it.
Yeah, I think I would love it.
And it's a very professional service, so far it works for us very well.
So I'm like, so just to like just to broadcast and this all etc. This is something that like we can do like ourselves. All software this is available across the point is that we have already like for example so like here you have already like a lot of people like a registered that's what being sent to you. But now to the webinar. So this is like a they're using this like a base of people from all over the world, and then surgeons from all over the world to kind of to get to them. But if, for example, again, yeah, so this is where I attend. This is really I'm like having this. I really love. I don't think so, but I really love to wake up at 7. Like I wake up and then come to 7.
For clinic, it's normal, but for scientists, that's terrible.
No, it's
we don't have ale to też, w ogóle nie problem z czyli? So it's not transmitting.
I was saying. Nie ma. A nie jest. Nie, tam jest okej.
No właśnie, teraz to odłączę. To tutaj przechwytuję, ale
a to jest twój laptop?
To jest mój laptop. Zawsze go przechwytuję. Jest, good. So, computer. Yeah, we will need to have a both USB and HDMI. You will have Mac with USB-C, this type of connection. So your talk is on. You if you want to check something, you want to it will there is a delay. You have the split, so it's a few seconds delay. Can I your paper to take that 2 minutes? Take 1 minute. Take 24 hours if you like. So we have this connection. So it's a little bit more complicated because this one wouldn't allow us to do it. Yeah, if that would be possible at all to load it to the computer, it would be much better. How do I get back to the beginning? So the fast way to do it, you can scroll or you can go exit through so that we put it out of the show. Like so. And again, there is a delay when it disconnects. So when it's just so many ways. You're right, it's calling me. Everything is going happening at the same time. Is that delay? Yes. Everything is delayed. Should be, yeah. Is it all good? Right. I sent the email. Email? Okay. I will open now the email. Meeting. Tak. Wiesz co jesteś? To... Wiesz co, to tak. Johannes wyjdzie na zewnątrz i conference center this is guest sekunda, Mirek, który ostatni też. Tak? No wiesz co, jestem in the middle of something. Johannes wyjdzie na zewnątrz do ciebie i przyznaj się, dobra? Jak to podamy? Did you get the hotel? That is not nie ma jeszcze? To tam twoje. Czekaj, to jest tam, dobra? To jest tam, poczekaj. So Miki will be waiting for you at the hotel. So you could take me with you and Allah? I have to take a flight. Thank you so much. Thank you. Have a great pleasure. I hope to see you soon. I just have this key. We will need your key for a few more minutes. Okay. So download. You'll send. So it's downloading. One file. This one. So I will post it here. Oh, trying to organize cancer. Yes, so, yeah, I have a talk about, but we still have cancer. Oh, so not this one. Okay, okay. So thank you very much. I think we are done with it. Here. Unplug. So how deep is the talk? So it's downloading. Yes, that will be great. So now we can put together. It's still downloading. So I don't know. Can we use the Steam? Wait, because now I have everything else already here. Maybe it will come. Yeah, like, you have your Steam? Because they like emailed me and it shows download. It's not good. Maybe there's a slow connection. Oh, yes, it is. Unable to download attachment. So that's fine. No, I don't know how much it takes. You have good travel on the city. Good still. Okay. Oh my pleasure. So we will be able to join tomorrow for our experiment. Right? 10 o'clock. Final, and we will open it right away. Yeah. And so unplug from the computer. I basically is opportunity. Yes. So now to be tutaj podłączamy. Tu już podłączamy. Thank you very much. Thank you very much. I will mention on the business doing them good out there and not that's very I'm looking out. Yeah. So now one more thing we have to do is there's a little file. So I have to yeah, here. That one right there. Okay. So, we'll just check it.
I don't know how you put it. It's there. Yes. So they will go here now, and from the beginning, and then now it's come up and for it to connect there. You have a presenter view, and you will control the microphone. Okay. That's good. All good? Yes, all good. Strawberry. Oh, God. The
So I think we can continue with the second webinar. Well, it is my great pleasure to open the second webinar of this conference, which is going to be broadcasted live via the Neurosurgical TV across the globe, covering the broad topic, technological advances ranging from blood-brain barrier and intraarterial chemotherapy to the novel approaches of the therapeutic brain delivery and new strategies to overcome problems of conventional health delivery. As the first speaker, we have Dr. Newell from the Oregon Health and Science University in Portland, USA, talking about the blood-brain barrier in brain tumor therapy, intraarterial chemotherapy.
Thank you. And I have to tell you that the co-author ought to be Mary. I got the slides back 3 times and I tried not to put too many slides in so there's time for questions. So brain tumor therapy, delivery and efficacy. One problem that we all know about is the delivery. But the other problem is we got to deliver something that kills the tumor and doesn't kill the brain. And that's a tough combination to deal with. Long-term disease control is possible, even using standard chemotherapy in chemo-responsive tumors, such as CNS lymphoma. And we'll show you some of that. But what about glioblastoma and other non-chemo-responsive tumors? We need better agents as well as better delivery. IV administration results in low CNS delivery. We all know that. Effective treatment requires penetrating the blood-brain barrier to reach the perivascular and diffusely infiltrated brain parenchyma. So how do we deliver chemotherapy to the infiltrated tumor? This is a slide by our neuropathologist, Dr. Wiltshire. Pink is the IBA1, the macrophages, and that, as we heard at the end of the last presentation, macrophages, macrophages, macrophages. 40% of primary CNS lymphoma are macrophages. 40% of glioblastoma are macrophages. So that's a big word. And here, the brown is the CD20 for primary CNS lymphoma. And perivascular disease is very infiltrative, and the vasculature is involved far distant from the main tumor bulk. And so IV chemotherapy does not effectively treat this. Now, I think this is an important slide. Heterogeneous permeability of the blood-brain barrier. This is a model of hematogenous brain metastasis where we inject the human metastatic tumors in a new rat up one carotid artery. And you can see there's this big tumor and this big tumor. This is with AIB, amino isobutyric acid. And this big tumor here takes up the unidirectional flux agent AIB very little, whereas this one takes it up a lot. It's consistently inconsistent. And quantitative autoradiography shows this very nicely. And that over here, there's some cells, some tumors that are very leaky. But there's a lot that are barely more leaky than normal brain. And that's what we have to deal with. It's like what sank the Titanic. It's not the iceberg that stuck up through the water. It was all the iceberg under the water that we can't see. And this is an old slide, 50 years old, showing that lanthanum between two endothelial cells stops at the first electron-dense tight junction. And that's where the blood-brain barrier is. We don't use the word blood-brain barrier anymore. We call it the neurovascular unit. And we can improve delivery of chemotherapy with an intraarterial route of administration. And I'll show you an example on a couple of pediatric tumors. It shows that when the tumor is really leaky, as it is in pilocytic astrocytomas, you don't really need to open the blood-brain barrier. But first, let's look at osmotic opening with intraarterial chemotherapy after intraarterial delivery. Here we have IV versus IA, taking methotrexate, which has a molecular weight of about 500. IV is more to the gray matter because there's more vasculature, but just giving it intraarterially into the internal carotid or into the vertebral dramatically increases delivery. And there's, even in the very leaky tumor, IA is better than IV. So you can do it both into the carotid, into the vertebral, and even in a leaky intracerebral tumor in rat, intraarterial will improve delivery over intravenous. Intraarterial platinum chemotherapy and unresected pilocytic astrocytoma. We've treated a few of these that we get away from the pediatric neuro-oncologist, but we've been pleased that the few that we've done have generally done very well. There's a modest complication rate. This is a young boy that we first treated when he was about 7 years old. And he was treated with multiple chemotherapy regimens, but one was carboplatin, etoposide, and Cytoxan. And despite that, in a couple of decompressions and some focused radiation, he was rapidly losing vision in one eye and completely lost it in the other eye. And I like this case because we took the exact same drugs, carboplatin, etoposide, and Cytoxan. And because we gave it intraarterially, we don't do area under the curve. And gave 30% less drug and got a dramatic response. This went to that, and there it is. And this boy I saw about 5 years ago playing soccer. He's now in college. So carboplatin just given intraarterially versus IV at a smaller dose had a dramatic long-term response in this young child. Now this is a tumor that none of us would have thought was a pilocytic astrocytoma. This is a 24-year-old woman who we gave 9 courses of carboplatin and melphalan, and then 2 courses of carboplatin alone. There was some hypersensitivity to the carboplatin and some hemorrhagic cystitis, but nothing substantial. And there is this ring-enhancing lesion biopsy, clearly a pilocytic astrocytoma. And there is sequential, and she's now, I think, 7 years out with absolutely a normal scan and no neurologic evidence. Just intraarterial carboplatin-based chemotherapy. Now this was a 13-year-old, I think, when we started. This is now a lawyer. She had a big cystic tumor which was at an outside hospital, was taken out, but we were very concerned that this may be involving some of the veins. So we shrank it with intraarterial therapy monthly for the times 12 months. She's now 28 years old and a practicing lawyer. And this hasn't changed in more than 10 years. The median progression-free survival was 31 months. The median overall survival was 70.8 months. So that was IA platinum-based chemotherapy. And now, intraarterial alone is better than nothing, but in older patients, even with blood-brain barrier disruption, we don't do real well in patients that are more than 75 years old. So here's the age range of 17 patients who received IA, because we don't do disruption in patients over 75. The KPS was about 50, and the mean number of treatments was 2.6. Three patients had a complete response, and 2 patients had a partial response. And here's the survival. Now, the survival is 0, 50, and 100 months. So there was some reasonable increase in survival with blood-brain barrier disruption, but we're reticent to do that in people over 75. Safety of intraarterial therapy. Number of patients is 48 patients. The number of intraarterial chemotherapy infusions was 206, carboplatin based, and there were 2 focal seizures and not much else. But if you combine intraarterial with blood-brain barrier disruption, you can do better. This is a slide from Dr. Stanley Rappaport, who wrote the textbook on blood-brain barrier. But the intraarterial mannitol was discovered by how many people are radiologists? The radiologists were studying angiography between 1945 and 1948, and they used a hypertonic iodinated solution and found that when they did this in rabbits, if they injected the contrast for 30 seconds or more at a rate that replaced the blood volume, they got an opening in the blood-brain barrier and the brain turned blue. This was basically forgotten. It was published in Acta Neurologica Scandinavica, which is still a published journal. And you cannulate the carotid up to about C2-3, or the vertebral is about C6-7, and you inject mannitol. It can't be 20% mannitol. It has to be 25%. And you have to make sure it's warm because you can get crystals at 25%. And you inject it for at least 30 seconds and just beat the blood pressure. And you can see when you do that, the tight lanthanum goes between these 2 endothelial cells. Here's the blood vessel to the abluminal side, because when it shrinks the endothelium, it opens the blood-brain barrier for about 30 minutes. And this is a slide from Dr. Rappaport's book. Here's the intravascular component, osmotic shrinkage, and the solutes that you're trying to deliver, which can be as large as herpes virus, which is 300 nanometers, can be delivered. You can't deliver cells, and you can deliver viruses up to 300 nanometers. And that's osmotic blood-brain barrier disruption. So it's really quite simplistic. I mean, it takes about 4 minutes to get puncturing the femoral artery to having a catheter in either the carotid at the level of C6-7 or in the vertebral at about C2. So there's the catheter, contrast agent, and up into the basement. And here we have the carotid. Now, barrier disruption improves delivery to the brain over IA or IV. So as you can see here, with methotrexate, which is the main drug for primary CNS lymphoma, you can see IV, IA, IV with blood-brain barrier disruption, and IV with intra-arterial disruption. And it goes up about 100-fold, not 100%, 100-fold compared. So if you gave 5 grams of methotrexate IV, you'd have to give 500 grams of methotrexate intravenously to get the same level we're getting in the brain. The rest of the body just sees normal level of methotrexate. Basically 3 grams per meter squared is what we use. And if you want to deliver viruses or IgG, the barrier closes pretty quickly. So as you can see here, time after barrier modification, you need to get big molecules in the first 5 or 10 minutes. But it dramatically increases delivery up to 100-fold for up to 2 hours in small and large animals. And we originally, before we did patients, and I choked to tell you this, but we worked it out in dogs. We heard about that, but I have a dog, so I'm not sure I could do that. So let's look at an example. This is primary CNS lymphoma. Looks like a meningioma, except it's adjacent to the ventricle. So there's a lot of dense tumors that are leaky right there. So you see that that black band? That's dense tumor with an intact blood-brain barrier. And in fact, in primary CNS lymphoma, that's just the tip of the iceberg, because the lymphoma is all over the brain, no matter what the MR or CT scan shows. And the next day, we injected mannitol into the carotid artery. We got good opening in the anterior and middle cerebral artery circulation. The tumor didn't double in size. It's just this black band enhanced. And the cortex, which has much more capillaries than white matter, has more white contrast from the iodinated contrast we give after the mannitol to document the blood-brain barrier opening. Or we can do it with radionuclide scan. IV blood-brain barrier disruption with the technetium glucoheptanate. So how do these patients do? Well, we started this in 1979 when I was still at the University of Texas Southwestern. And we did it based upon having done small animals, large animals, substantial amounts of molecular biology, cell biology, and did the first patient. And our purpose was to avoid radiation. I was declared a heretic for not giving CNS lymphoma whole brain radiation, because that was the definitive treatment. And you get a little bit of longer survival, but you get horrific dementia. And so in these patients, this was published in the Journal of Clinical Oncology. In the standard risk patients that are less than 60, with the Janowski greater than 60, that's those 47 patients. The median survival, this is without Rituxan, was 10 to 12 years. That's without antibiotics. And we did neuropsych testing on every patient before we treated them, and after we did it, had a year, and up to we've done periodic testing up to 30 years, and we have 4 or 5 patients that are between 25 and 30 years of age. One's an orthopedist in Arizona, one's a tax lawyer, Bloomfield Hill. We had no patients lose cognitive function. So immunotherapy in combination with BBB improves the response in patients. Based on our laboratory studies, we have 3 animal models of primary CNS lymphoma. In clinical efficacy with monotherapy in our rats. CNS lymphoma used frontline was added to increased delivery with blood-brain barrier disruption. And so here you see no methotrexate-based therapy, 149 patients, no monoclonal antibody, yes monoclonal antibody. Overall response went from 81% to 92. Complete response went from 57 to 75. But the overall survival went from 37 months to 61 months. And all of the other parameters were the same in both groups. Now, what's the safety? Since 1979, we've done 4,000 disruptions in 268 patients for a total of 2,134 courses of treatment, 2 disruptions a month in the course. The adverse event in these 4,000 disruptions, 4 patients showed ischemia on MR, which was not seen clinically, but it clearly was a small embolic phenomenon from those 4,000 catheter procedures. There were 4 adverse events due to iatrogenic lineage flow, which we fixed and sped up the rate of infusion of the chemotherapy. Focal seizures were common because methotrexate is electrogenic, but we rarely see any seizures. They're generally just a focal seizure. There were 2 deaths in 30 days, one from a brainstem stroke and one from a fulminant. So in conclusion, intraarterial platinum can safely and effectively treat chemosensitive tumors such as pilocytic astrocytoma. Even using platinum, where the platinum is given intravenously, and blood-brain barrier disruption can safely be performed with appropriate training. There's nothing fancy or complicated. This takes a little logistic coordination between 3 or 4 different departments. Here's our group. It's been primarily funded by the NIH, which are 2R01, 23 years and 35 years. VA Med Review, which is renewed for the 40th consecutive year. More recently, we've done a little bit with companies, and we've had some help from the philanthropy. So there's our room, one window, and one of my fellows gave me this picture. So I've tried to show just a few slides, because lots of people hear all kinds of horrific stories about blood-brain barrier disruption. And so I'm more than happy to take the attack, tell you what I know. Thank you.
So I think we can proceed like yesterday with panel discussion at the end of the webinar session. So I'm inviting Dr. Henry Bram, a neurosurgeon from the Hopkins University in Baltimore, who is going to talk about novel approaches to therapeutic brain delivery.
Thank you very much for the opportunity to share some of our work and our journey through this field. This meeting is a follow-up for me of the meeting that was in London 3 years ago. And I know that when Monica spoke to me about joining it, was, a lot of our colleagues and friends that we met there resulted from those presentations and those discussions. And I hope that today, that in the last 2 days, yesterday and today, and those staying on here in Baltimore, that it leads to more collaborations and more new sort of synthesis of approaches. And this meeting was very, very exciting and very productive, and it's led us to, you'll see, to some new collaborations and new work together, and I hope that we continue along those lines. I have the work is funded by many sources, philanthropy, NIH, and so on. And also, as you'll see, companies play a critical role in making these things come into reality. Very proud that the work that I'm presenting is really not singular, but is so much the collaboration of so many people. Most of all, my own department. This is from a few weeks ago.
in front of the, I'm sorry, I don't have the little room on top of the dome there. But this is our Department of Neurosurgery, which is very devoted to understanding the brain and spinal cord and finding new methods, both drug delivery and of improving treatment. This is our lab group that I'll be presenting some of the work from as well in a more informal setting. When I look at brain tumors, I really look at both the opportunities and the obstacles that have gotten in the way of making progress. And certainly, when I started in this field, when I finished my residency in 1984, the area was quite dismal. There were many systemic treatments had been tried, no benefit. The FDA had not approved any new treatment for brain tumors in over 20 years. And the median survival for glioblastomas, malignant gliomas, had really not changed. It was measured in a few months, and almost everybody was dead by 2 years. And many people, when I first came to Hopkins, counseled me not to consider this as a field because it was such a dismal area to work in. And so the question was, could anything at all be done to change the outcomes for glioblastomas? And but now when we look today, we have many new treatments, gliadel, Timidor, Avastin, dramatic improvements in imaging and surgery, ICU care, medical care, Gliosite, Novacure. We've seen more than a doubling of the median survival in the last decade, from 9 months to over 20 months. In many more, and it's more common to see long-term survivors. We never saw that, virtually never saw that in the past. Now it's fairly commonplace to see people 4, 5, 6, 10 years out. And the excitement of what's available today is extraordinary. There's so many new things, and we'll touch on that. So the question now in 2019 is, given the extraordinary pipeline of new approaches, new treatments in the laboratory and in clinical trials, how do you choose? How do you decide where what you're going to devote your career to, what you're going to expose your patients to, and so on? And how do you look at how patients benefit? So when we look at the barriers to new treatment, I mean, at first it's just fresh ideas and good ideas. And then when you have an idea, and it's a surgeon, radiologist, neurologist, we see nature in its raw state, and you get ideas this could be improved. So we go to the laboratory, we test those ideas. Then we go to clinical trials, look at safety, then efficacy. Then we go through regulatory processes. Then reality is we start to go into how these things are paid for, who pays for them, and whether companies support them or don't, and other things which I never thought of in the past, but the reality. And then there's the clinical judgments for peers as to whether even something that's been through all this rigorous testing, whether it gets adopted universally or in a high impact way. So let's just look at therapeutic implications. Beautiful talk by Ed Newell, who has been one of my inspirations all through my career. And, Ed and I know that my brother Stephen worked with Ed at the National Cancer Institute in the, I guess, mid-'80s or so. And when I looked at, all the things that looked promising in the lab, the question became, were they even getting into the brain? And, is it possible that things looked so promising in the lab and then they failed clinically? Was it possible that those drugs, those therapies weren't even getting into the brain? So we started looking at this from our first NIH grant. We looked at the clinical effectiveness of new cancer therapies, and we said if there were better delivery of agents to the target sites, that we could improve the outcomes. And one solution that we looked at was we're using controlled release polymers. This slide is a drawing from Ian Sook, our artist, and it summarizes about 20,000 publications in our field of drug delivery to the brain. And you can see the different areas that, first, of course, we know, here we go. The blood-brain barrier itself, what gets across lipid soluble small molecular weight molecules, we can coat the molecules, work on, receptor sites. Beautiful work of Ed Newell and others on opening the blood-brain barrier. We can selectively and, or diffusely open the blood-brain barrier with a variety of different techniques and let things get through.
to work with catheters, first with Omaya in the 60s, and then later at Oldfield and many other colleagues with convection enhanced deliveries. We directly deliver large molecular weight substances into the brain. And then the work that we've worked with polymers, starting with Gliadel and then more recently with microchips and many other technologies that you're hearing about at the meeting. But can you line the surface with these slow release agents? And what we started in this area, and at the beginning, I went up to my friend Bob Langer, who he and I had worked in Dr. Hopkins' laboratory as students, and said, what controlled drug delivery method? There was no way of doing it at that time. And he was looking at polyanhydrides, which were very interesting because in the 1950s, there was a lot of literature about them in the textile industry, and actually Japanese literature about using them for clothing. And there was a lot written about that in chemistry and how, it could be molded in different ways. But it actually turned out to be a failure because what they found to their horror was that when they made clothing and someone went out in the rain, it dissolved. It disappeared. So that didn't have a big market. And for about 25 years, there was nothing written about it. But then looking at that, those were the ideal characteristics of what we wanted to put into the body. We want something that could hold a drug, have a good matrix, and would dissolve as it was exposed to the brain. So that work progressed. Bob Langer developed that in his team at MIT, Cover Science, and many other. And we put together a group, and I think that's so important. This is from our first NIH grant, really crossing disciplines. Neurosurgery, Mark Saltzman, who at the time had just joined the faculty as a chemical engineer. He's now the chairman of biomedical engineering at Yale, looking at pharmacokinetics and modeling. Mike Colvin was professor of oncology, pharmacology, later the director of the Cancer Institute at Duke. Mark Chasen with the company, and then Bob Langer and his group. And we basically did preclinical studies, safety, drug distribution, efficacy, worked with the FDA, took it through a variety of animals for safety and efficacy and drug distribution, and brought it into clinical trials. It's a very simple concept: take out maximal tumor and then line the surface with a drug-impregnated polymer and let it release at very high concentrations over a period of time. And this is from a review article in the 90s that Bob Langer and I wrote. But what we found as we developed this work, and I think it's true of every new development, every new innovation, is that it was rejected. It was pushed back on. And it was interesting, as we started speculating what is it that, we're trying to overcome, it was very interesting because we always got accolades for our work. Everybody says, good science, it's really beautiful work, but it'll never work. It'll never actually do what you're trying to do. But the reasons that we kept hearing about why it was definitely going to fail kept changing. And so the early years, as you can see here, and I think this paradigm is true of every innovation, is about, well, the polymers, you couldn't get a biodegradable polymer, you couldn't get something that would be safe. There was enormous amount about, are you kidding? You're going to take a toxic chemotherapeutic drug and expose it to the brain. They're so dangerous drugs anyway. How can you put it directly in the brain? So we did safety studies and showed that was okay. Then it was that it wouldn't diffuse far enough, but we showed in rats, rabbits, and then eventually in monkeys that you can get log orders of magnitude increased concentrations over a 30-day period versus the 14 minutes that the IV drug lasted, the half-life. And then the drug wasn't the best drug, but that's all that was available at the time. And then once we completed even the phase 3 studies, the company that was supporting it went out of business. They were bought by another company. They weren't interested in drug delivery. Very small market range. And there's only 14,000 new cases a year. They weren't interested in the business side of it. So we thought, oh, we have phase 3 data. Everybody will be pushing down our doors to take that. Nobody was interested. And big pharma, big companies, little companies, we all said the FDA will never approve it. It's too complicated. The chemistry is too complicated. So a small startup, Guilford, did take it on and did get FDA approval. Then the issue became, who's who's going to pay for it? Things that I never would have thought of as a scientist, or, and it's expensive. And we had to eventually we had to petition Congress and the CMS to set up a new DRG so that it would be paid for by Medicare, and then the insurance companies followed. But things that I never would have thought of as my residency training that would be necessary in order to push the innovation forward. And then so on. The story continues. But where are we 23 years after the FDA approval? It's used throughout the world. 17 countries have approval and over 1,500 academic and medical centers. Interestingly, when you talk about companies, it's passed through about 10, 12 companies in terms of who's producing it, who's making it. Whereas I've been fortunate to have stayed at Hopkins a long time, about my year stayed at MIT, but the companies do keep changing. So when we think of the idea of targeted brain therapy, we really break it down into three different areas. One is delivery of effective agents and work like Eddual and our work with Gliadel and work with convection enhanced delivery are just three examples of how you deliver to the brain. The question is, what cells are you trying to treat? Is it the cancer cells? Is it stem cells? Is it blood vessel cells? The immune system, and so on. And then the other targeted therapy is which patients get what. And that's clearly incredibly important, especially as we get more and more specific therapies and more expensive therapies. We need to be tailoring the therapies to the individual people. So just to finish with the Gliadel for a moment, this is our current approach. We do maximal tumor resection. We coat the surface with Gliadel. We treat with Timidar and radiation therapy. And with that, we've seen median survival go from 9 months, which didn't budge for decades, but now it's over 20 months by many groups and many different sites. This is a meta-analysis of published papers about 2-3 years ago by Chowdhury and Newton and Ryken. What they looked at was 62 papers of prospective trials using Gliadel in a controlled prospective study, 3,162 patients with high-grade gliomas who received chemotherapy wafers compared to 1,700 without it. And in their meta-analysis, what they found is that that it was statistically significant improvement in survival, median survival of 16 months versus 13 months. All of that is good, but it's good. We're proud of it because we made a difference. But on the other hand, we don't fool ourselves. I mean, even going from 10 months to 20 months, it's still a horrific disease that is taking people at the time of life. The reason that it's encouraging is not the 10-month improvement of survival, but it's that the approach works. The idea of taking things from the laboratory into the clinic, back to the laboratory, back to the clinic has made a difference and does make a difference. And I think that's the key point, and that's what keeps us going and really has inspired us to look at so many different avenues. So the real answer comes, well, we need more effective agents. And we've looked at a lot of things in our laboratories, and as you know, we've published a lot, we've looked at a lot, and this is just actually a very short list of the different drugs that we've looked at using our approach with the control from these polymers. So you say, why do we look at all that? What came out of that? Well, this group here in yellow were all the ones that are in clinical trials. So our purpose is not to just look at things and write papers about them, but it is to test them and get them into clinical trials. So it's a long process, but that's been very, very critical. And I will mention one, and I know that Dr. Rahman is going to speak about this. I'll just show the paper because it's just accepted and just came out within a few days ago. But this is a direct result of the last meeting. And it's a collaboration we have with our colleagues that put together, and this came out of the last meeting of this group. And I'm very proud of that. And it's a different type of polymer system, looking at different drugs, and it's very encouraging. I'll show you very quickly another example of some innovative ways of where we're moving forward, and that's that combining microchip technology with the polymer technology that comes from John Santini, Mike Seema, and Bob Langer at MIT, and they're forming little microchips with multiple wells. And we've looked at them with biodegradable polymers, that you can make microchips from. You can see here the example. You can make multiple wells and cover them with polymers, which then can be released either electronically, remotely, or in relationship to different pH changes or other things. And so we looked at these biodegradable polymers, which release chemotherapeutic agents, showed that they were effective and release biologically active drugs at will at different time sequences. Basically, it's a pharmacy on a chip. We looked also recently in a paper of PNAS with intracranial microchips for breast cancer, metastatic breast cancer, using drugs that wouldn't be used otherwise, like Taxol. This work has gone into humans, so our work is still in animals, but in it's a group again with the Santini group and Michael Sema and Bob Langer on releasing parathyroid home run in patients and showing that it is safe and that they can effectively release therapeutic drugs. Where I'd like to finish up with is that where our excitement is right now is really exploring the role of the immune system in combination with these delivery approaches. And our inspiration came from this from a patient of mine, Richard Polhaber, who is 39 years old. He had been the administrator for the neurosurgery department here at Hopkins. And then he left that job, went to Sinai, he was driving home, had two small kids. He had a 3-year-old and a 4-year-old. He was driving home. He stopped at a red light. He had a grand mal seizure, and he woke up in the hospital. And he had no previous illness. He, had an MRI. It showed a glioblastoma. He transferred to Hopkins. We operated on him. The pathology was a glioblastoma, and I say that over and over again because it's been reviewed about a dozen times to make sure that it really was a glioblastoma. But to make things worse, when we treated him this 91, it sort of broke everybody's heart because we all knew him so well and we would be dead in 9 months. And so he got treated with BTNU and cisplatin, 3 cycles. And then he unfortunately got infected after the chemotherapy. We had gone through probably the funnel sinus and removing it. And we tried to treat it conservatively, but we had to take out the bone flap. We took out the bone flap and cleared up the infection. But he kept coming back to me. So he had gone back to work and he was trying to function whatever time he had. But without a bone flap, you could just see his brain, pulsating, and he couldn't really interact with people. He was a young kid, and he kept saying, "I can't work because everybody stares at my head when I try to work." And he said, "When are you going to do cranioplasty?" And I said, "Soon." And I kept thinking, "Oh, so the last thing I do is going to die in a month or two anyway. I can pour foreign material in, and he's just going to get infected again, and he's going to die anyway very soon." So I kept trying to stall and he kept being insistent. So we did the cranioplasty November 1991, and there's been no disease present in the last 28 years. His kids have grown up. He's actually now retired. He has grandchildren. He's neurologically perfect. And so we look back and said, like, what went on here? That the only thing that's different about him is the infection. I mean, the treatment is the same that we did everybody else. So did the infection cause this tumor to go away? Cured to progress 28 years? So we thought about what to do with that observation. And we thought about affecting all our patients. And, that might not fly so well, although there have been neurosurgeons who tried that approach and it didn't end well for them. But we did start working with our colleagues, Drew Cordell, who's an outstanding immunologist. Reed Thompson was a medical student, and he began working with Drew. Reed is now the chairman at Vanderbilt Neurosurgery, but showed that paracrine cytokine therapies really very effective against brain tumors. So we could harness the immune system against brain tumors. Another study with Justin Haynes, who was a postdoc in our lab at the time, now is a professor of biomedical engineering at Hopkins, looked at polymer microspheres using interleukin-2. And we saw that we could really get results, stunning results, that in B16 melanomas, for example, where we never saw, it was uniformly fatal to these animals, that if you treated with these interleukin-2, microspheres that we could see cures that we never saw before. So we're very encouraged by this whole area, synergistic chemotherapy, and so on. Fast forward, Mike Lim, who's gone to medical school with us, worked with Drew Pardell, trained in Stanford for his neurosurgery residency, and he came back and began working in the immunology area. And I told him that I sort of didn't want to keep writing papers about the immunology of brain tumors. And I was citing him that we really need to get moving with clinical trials, but that was what I, would hope he would accomplish for us. And Mike began looking at checkpoint inhibitors and particularly their synergy with radiation therapy. This turned out to be one of the most cited papers in radiation oncology on the synergy of checkpoint inhibitors and very tactic radiosurgery. And had a lot of very promising data. He's leading multiple clinical trials in checkpoint inhibitors in brain tumors right now. But one of the questions we began asking is, here we are, we're putting all this, literally as a society, billions of dollars into immunotherapy. And we're also treating with chemotherapy and radiation therapy. Are we actually working against ourselves? Does it make sense what we're doing? And so we went back to the laboratory to explore that. And the question we asked is chemotherapy beneficial or is it detrimental? And this is again a diagram of how we, look at these things that, we use local therapies that are destroy locally, although they are also very good at, they break up the cancer cells, and so they're good for antigen presentation. Systemic chemotherapy kills everything, kills white cells, kills the bone marrow, as well as cancer cells, and, so on. So we began looking at that. The results are published in Science Translational Medicine. It's anti-PD-1 anti-tumor immunity is enhanced by local and abrogated by systemic chemotherapy. And the results were very, almost surprising. And this slide just summarizes that the data is published, and there's much more, but I didn't want to put 30 slides on one graph. But if you look at the controls, they all died about 21 days, and that's typical with our laboratory. If you took BCNU alone, systemic BCNU, or you took checkpoint inhibitor alone, you pretty much got this graph. If you took, and you saw no synergy between systemic BCNU or Timidor, we did experiments with Timidor and with BCNU, and whether you added checkpoint inhibitors or not, you got about the same benefit of survival and the same number of long-term survivors. On the other hand, if you did local chemotherapy with either BCNU, like Radiol, or with Timidor, and added checkpoint inhibitors, you actually saw much higher median survival and many more long-term survival. And so this was encouraging that you saw synergy that you didn't see when you looked at either one alone separately. So that's interesting, because that would say, gee, you should use local therapy with the checkpoint inhibitors. But the real question is, if you take a look, and this experiment was done, look at the survivors, and do they have immunologic memory? Because we are treated with immunotherapy. So the question became, is immunologic memory affected by local versus systemic treatment? And these results were very intriguing. If you look at those animals that with the checkpoint inhibitor at the long-term survivor and re-challenged them, you saw no tumors. If you looked at the long-term survivors from intraperitoneal BCNU and you re-challenged them, by day 7 you saw the tumors, and by day 17 they're close to dying from the tumor. If you looked at the animals that got systemic BCNU and the checkpoint inhibitor, same as with the BCNU, there's no immunologic memory. The animals re-challenged, they died from the tumor. On the other hand, if you took those that got the local chemotherapy and the checkpoint inhibitor, this group here, not only was there longer survivors there, but when you re-challenge this group, it looked just like the ones that had gotten checkpoint inhibitor itself, which is that they had immunologic memory and they rejected the tumor when it came back. So that was very encouraging. And, we concluded that immunologic memory is lost with systemic chemotherapy and immunotherapy, but not with immunotherapy and local chemotherapy. So we designed a clinical trial with Bristol Myers and Arbor Pharmaceuticals, we funded, and we're negotiating with thousands of lawyers that are involved in getting started in clinical trials to see whether in people what we found in the laboratory is going to work. And if so, it'll make us rethink the whole approach we're going to take with immunotherapy. So let me just finish on just a few examples of emerging technologies that are coming along that are very exciting to us. One is that beautiful work by Bert Vogelstein's group and Chetan Bedagawa in our department is the first author on the first paper on liquid biopsies that circulating tumor DNA as a way of both designing therapies as well as diagnosing tumors. And Science Translational Medicine said that that is the most cited, highly cited paper that they've ever published. This one. And it's interesting that in brain tumors, it's the least, you see the least number of them, probably because of the blood-brain barrier, that the circulating DNA may not be getting in there. So a study that's currently underway, and I think been discussed with the MRI guided focused ultrasound system, is of sort of rattling up those tumors, opening the blood-brain barrier, and then testing to, disrupting the blood-brain barrier. You can see here a thalamic tumor, treating it with the focused ultrasound. You begin to get blood-brain barrier disruption there, and then testing the bloodstream to see if that increases the amount of DNA fragments that then can be used both for diagnosis and ultimately for designing individualized treatment. So that's very exciting. That's a joint grant between Chetan Bedagawa at Hopkins in our department and Graham Woodward, who's now the chairman of neurosurgery at the University of Maryland. Another thing is we look at, as we look at material science and so on, we look at some of the problems that we see with the craniotomies themselves. And this is work from Dr. Gordon, who is an incredibly brilliant plastic surgeon that works very closely with us. And he and Judy Wong are set up a whole cranioplasty research center as well as a clinical center. And you can see here that, an example of a person with required neuromodulation, instead of putting brain stimulation in the skull and then leading down the battery pack in the chest. And all that. Why not use the skull space itself for the neuromodulation of the battery itself and not have chest implants and so on, especially as the bone erodes and causes all sorts of skin problems. So they were able to design cranial implants with integrated neuromodulation. And that was published as the first in man example. Another example of a shunt. Now a shunt is taking fluid away, but it's the same for distributing drugs. It erodes through, it pushes up. So again, why not use the skull itself as a material there and implant the shunt in? And you can see this is the first in man of where that's done. Instead of shunting on the outside and pushing out on the skin and sometimes even eroding the skin and getting infected, integrating it into the cranioplasty itself. And then most exciting in an earlier stage, not yet in man, but work that Chad Gordon is doing with Judy Wong and with John Weingart in our department. He's using it for convection-enhanced delivery and for microchips that can be implanted into the cranioplasty to deliver drugs. And you can see that they, it's the wrong direction. But, so the idea here would be that you could put drugs into a microchip, which then is fused into the brain, and you could control it externally, which drugs are released at which time. But all sort of moving forward in terms of how we're working with drug delivery. Another example is this is Miko Feldberg working with Chad Gordon is translucent or somnolucent cranial implants that you can then do ultrasound, focused ultrasound, diagnostic ultrasound right through the skin because it's transparent and that they show that is an effective way. And here's the pump-assisted medicine delivery capability, some of the applications that Chad has come up with in his various patents on that. But it just shows how we're sort of evolving as to how to use these sort of ideas and technologies to improve outcomes. So just to conclude, these improvements that we've seen are very encouraging because they really show a difference, but they're just the beginning. And there's so much more coming in the pipeline. None of this would have been possible by working in isolation. It all comes from collaboration between colleagues across disciplines, across institutions, across the Atlantic, and people working together to solve these incredibly difficult problems. I think in the future, for brain tumor therapy, rather than rushing into surgery and then thinking about what to do, is we would probably reach a point that we either with liquid biopsies or with direct biopsies will first study the tumor, its biology, then do the surgery, maximum resection, maximum treatment in the operating room with whatever implants are appropriate, and then design the best therapy for that, whether it's blood-brain barrier disruption, whether it's conventional delivery, polymer, or systemic treatment, but designing for each individual tumor first in the best possible therapy. And then observing not just with our ways we currently do, but of course with molecular markers, both in the bloodstream as well as with PET scanning and so on. And then at recurrence, again, studying the tumor rather than just treating it, so we get that targeted individualized therapy. I think that in 1921, Walter Dandy urged that we use scientific accuracy for diagnosis and for treatment. I think the diagnosis was coming along a long way, and I think we're making progress. Thank you very much.
Thank you very much. So now we are coming to the last talk in this session, and then we'll have a panel discussion. So the excuse me. So the next talk is by Mark Sawaden from Will Cornell, New York, and the title of the talk is Strategies to Overcome Barriers of Convection Enhanced Delivery CED for CNS Tumors.
Thank you very much. I first want to start by thanking Dr. David Walker for the kind invite to participate in this meeting. It's always wonderful being in the same room and under the same roof with like-minded individuals in a domain that usually seems very desert-like. And to share this session with two arguably the pioneers in drug delivery, insofar as I knew as a resident growing up in neurosurgery with Dr. Newell and Dr. Brem, is a real honor, and I value their work and look to them as mentors in the field of novel ways of enhancing drug delivery. I'll say that I listen, and as I've gotten pulled into this realm of drug delivery rather than neurosurgery, I feel inherently strongly about any of these platforms that are being discussed as being highly powerful means for achieving a goal. But I think as neurosurgeons and oncologists, as we move into the realm of clinical trial work, I see that there's the potential for great missteps with regard to merging the therapeutic platform with the disease entity itself. And that's a concluding remark I'll make later on in a moment. You know, I was inspired when I left fellowship by the work of Dr. Oldfield, the late Dr. Oldfield, when he was contributing toward this idea of enhanced drug delivery utilizing convective forces in the parenchymal compartment of the brain. I'm not going to go into the background much, and Dr. Brem was inspirational in his chronology as he looked at a 25-year continuum from the laboratory to the bedside. I'll say that when I had this, what I thought was an ingenious, maybe a stupid idea of using convective enhanced delivery in the brainstem, it was something that I would have said, would maybe take a year or two to get into clinical work. And I started that from around the era of 1996, 1997. And it took about 16 years before we felt confident enough to move it into a translational platform. There are a lot of hypothetical, I think, ideas that I had about why brainstem. I'll say that as I listen to these talks about GBM and supratentorial malignant glioma, DIPG or diffuse intrinsic pontine glioma is a beast and the beast of the beast in pediatric neuro-oncology. But I'll say as I look at what's been done with GBM, I find this logs more difficult from the standpoint of mechanical and drug delivery stresses that you're putting on yourself from the standpoint of accomplishment. So, the pontine glioma, somewhat restrictive, non-metastatic at diagnosis. We're not incurring a lot of tissue damage from surgical extirpation, necrotic centers, et cetera, And these were important features from a hypothetical standpoint about the translational capacity with CED in the brainstem. Others took this rapidly into the clinical realm to explore this option as a therapeutic drug delivery, both for DIPG and other disease processes in the brainstem. And I'll say that those 4 anecdotal case reports, without going into this push for translational work in the realm, I couldn't make much sense out of whether or not it was safe. It was really difficult, if not impossible, because of variability built into approach, device, chemotherapeutic agent, rate, volume, disease continuum, and the list goes on and on. So it was literally impossible to decipher whether or not this would be a safe endeavor. So when we launched our phase 1 study at Memorial, it was really designed to look at feasibility. Can we do this in a safe maneuver? And I had to take off this hat of a neurosurgeon with a desire to help these kids. It was more in the realm of, is this platform of CED jeopardized by kind of a highly variable way in which we're applying it towards certain diseases? So ratcheting back from the standpoint of volume, dose, the number of kids we would be treating, et cetera. And it was painful in the sense of this slow, gradual, iterative process. But that's where we started. And it was very simplistic, and that kid would get standard therapy. After external beam radiation therapy, we would give 1 administration of the radioisotope. And again, this was quite challenging. And there was a lot of, I don't want to say naysayers, but critique about taking these kids after only what we call disease holiday and treating them when the disease is at its lowest volume and tumor burden. It was a one-time injection at this interval here. A lot of it was neuroimaging. They would be on evaluation for 30 days and free to do what they or their family chose. One important aspect of this in the translational component, I was very vested in some conjugated toxins. We were working with irapastin and Genius and conjugated immunotoxin therapy. This kind of fell upon our lap at Memorial because it was already being used for CNS relapse neuroblastoma kids in the intrathecal compartment. So there was an IND that we cross-referenced. But the beautiful thing about using this 8H9 molecules, a murine-based monoclonal antibody directed toward the B7H3 epitope, is we could image it. So we could get real good dosimetry data by using PET scan. And this turned to be extremely important from the standpoint of the validation and the convincing from the standpoint of whether or not we would push forward. The continuum or the workflow was very simple in some ways. A lot of this was surgical planning from the standpoint of a supratentorial route. We can discuss the details at a later point. Safety, safety, safety. We would do this in an MR environment using a platform where I could do sequential imaging every step along the way. I live in the world of neurosurgery and trajectory planning and know well enough that accuracy in some of the domains we use are not satisfactory from the standpoint of a phase 1 study of this magnitude. Catheter deployment, when we first started, the first 3 or 4 dose levels were done in the intraoperative magnet, monitoring dosimetry. Then we transitioned into a ICU setting with an implantable flexible catheter in place, and then drug infusions at variable times depending on their assigned dose level. As mentioned before, the isotope would allow us to do PET MR and do real dosimetry. And that's not just how much radioactive substrate were we administering, where is it not going, how is it affecting the rest of the body, et cetera. And that became extremely, extremely important. We reported our preliminary results last fall. And I think the most important things to draw from that publication, that early experience, that we still have not reached what we would consider to be a dose-limiting toxicity, either based on volume or radioisotope dose. Lesion to whole body absorbed dose, So there have been a couple references made already this morning about the inefficient nature of systemic delivery and single-digit percentage pre-drug extraction in the parenchymal compartment. We're routinely getting between 9 and 1,500 times the systemic dose in our lesion or in our area of interest. So essentially the inverse of what we give with IV administration. The volume of distribution that we've reached on the current phase 1 study. So this is, again, a target from the standpoint of can we encompass the tumor with a single injection and a single catheter? Volumetrically, the answer is yes. Routinely, it's yes. So we're getting really good distribution volumes. And I'm going to come back to volume as a parameter of, or a gauge of therapeutic success in a moment. In a phase 1 study, and I'm going to get into this idea and this difficulty, really difficult to extract whether or not there is clinical benefit, but certainly we don't want to hurt these kids in the process, and thus far we haven't. And if we compare it to any other cooperative group study, we're doing substantially better based on median survivals in the range of 9 to 11 months for most cooperative group studies with kids with DIPG. And our interim analysis are updated with data that we're even doing better than that as we push further along with dose escalation. I think the gripping thing for me is you invest a career, a number of years, and millions of dollars of investment that you go after from the standpoint of supporting this type of work. You look for anecdotal evidence and you try and take off your biased hat and say, are we making any progress? I would say that, especially on the latter dose levels, we're seeing or unseen what intuitively looks like regional control of disease. This one well after 6 years.
Hi, Dr. Zane. I'm doing real good.
This one well after 3+ years. You look at the pontine segment in the area of treatment, and I've been quite impressed with the potential for regional control. And it's a common theme that I'm seeing with certain dose levels. Then if you really get into the weeds and try and extract whether or not there's some common theme here in the kids who might have done better versus those who have not. This is a Kaplan-Meier plot based on dose level, and there's this idea that maybe higher dose level would work better. But I can tell you in looking through the variables that might affect that, it is all over the place from the standpoint of tumor volume. Again, we're prescribing a certain dose based on a child that comes to us at a certain point in time with no understanding about the other variables that I'm outlining here. And those are tumor volume, prescribed dose, the volume of infusion, distribution, etc. So to try then to look at trends become exceedingly difficult. And this is the barrier part of the talk from the standpoint of how do we utilize this information to design maybe a better therapeutic trial looking at response or not. It's well known that with DIPG and most malignancies, after induction radiation therapy, you see a fairly good, DIPG is pretty phenomenal as far as the amount of reduction in tumor volume insofar as we can measure with an MRI scan. So it would make sense that if we get it at this nadir, there's less tumor volume, smaller target, maybe we can encompass more tumor. It makes perfect sense. Little bit of work that has been done by our groups and others, what is that target volume if we're going to look at tumor after radiation therapy? You can see it hovers somewhere around that 12 to 15 cubic centimeter mark after radiation therapy. But again, an example of the difficulty in a phase 1 study of extracting clinical benefit information. These are 2 different patients on the same dose level, one with an estimated tumor volume of 10, the other with 40+ cubic centimeters of tumor volume on the same dose level. Doesn't make much sense to try and extract clinical benefit from that at all. And come back to tumor volume in a moment. So why not ignore it? Why not just flood the whole brainstem? Why not just flood the whole cerebral hemisphere and the whole supratentorial or infratentorial compartment? Lots of reasons why, but even in this particular individual, you can see the variable demand that would be put on it. Same patient, but if we segment out the brainstem over 44 cubic centimeters, tumor volume is best we can estimate somewhere about that 16 cubic centimeters. Same patient, same dose level. What is our target? What makes most sense? If we go to the more universal approach toward getting the whole parenchymal compartment and ignore the tumor margin, there are concerns that have to do with toxicity. There are concerns that have to do with tolerance as we
triple, quadruple, or even more the volume of infusion. Cost containment, certainly when we're dealing with radioisotopes, this is an extremely expensive venture. And it probably differs depending on the therapeutic molecule. Cytotoxic agents, viral-mediated viral therapy that has this idea of self-propagation, much, much different from the standpoint of our target, I would expect. And this is something that needs to be thought about. And then establishing and monitoring where our drug is going has been a real challenge for those vested in the idea of any form of local drug delivery. The path moving forward in clinical trials has been co-administration with a surrogate tracer in the gadolinium and MR realm. This is work from Russ Lonser and Chris Bankowitz. This real-time idea of imaging your therapeutic substrate is real, makes perfect sense. This is an example of one of our patients treated, the green outline being the tumor margin, the red being our delta T2 signal relative to baseline after infusion. You can see real vibrant signal change without tracers. And the work by John Sampson at Duke has been phenomenal from the standpoint of trying to validate T2 signal change relative to actual spec scanning. There are inherent problems with all of these. There's no question there is. As you get into the idea of using all of these in a differential format, as we have been doing on our trial, you get some homology of the morphology and the contour of the distribution. This is just one example of gadolinium, PET scan, delta T2, all superimposed on each other. And a plot, if you start to look at these differing aspects of monitoring drug distribution, it is variable. 30% thresholding for PET versus 50% thresholding for PET. This becomes a little bit of a moving target, a little bit frustrating from the standpoint of trying to understand whether or not we're accurately monitoring tumor distribution. The PET image obviously has a huge advantage. It is molecular. In the spatial resolution, it lends a lot of desire beyond what we're able to do relative to MR. Obviously, our target should be not just distribution, but is that distribution enveloping the tumor mass. If you have drug on, or you have tumor on one hemisphere, drug on the other, and they represent equal volumes, that does the patient no good. So these need to merge in a direction toward unity. These are, again, examples, good and bad. Intersect as best we can monitor, all the inefficiencies built into monitoring tumor volume, drug delivery, 93% in this individual versus 25% with that overlap being outlined in green. So if we're to be, and we should be, self-critical, where do we do well? This is just a quick sample of our latest dose levels. These are all rate adjusted, not dose adjusted. So same volume, same dose. We can do really well with encompassing a lot of the tumor, single catheter, single volume of infusion. We get really good distributions. However, if you start to look at why in those versus others, common sense to say that smaller tumor we can target with equal volume. We don't do as well with larger tumors potentially. Again, smaller relative to the mean after radiation therapy. This is well known to anybody in the world of direct drug delivery. There's a fairly linear correlation between what we administer and unit of what we affect. We have found that to be true, and that hovers somewhere around the 2.8, 3.2 slope. So if we increase volume, not hard to imagine that we're going to increase distribution. The last two patients treated on our highest dose level yet with volumes between 6 and 8 single injection. And you can see there between 30 and 20 cubic centimeters. So, and again, same clinical profile from the standpoint of tolerance. These are the maps we generate. This is kind of our distribution volume based on delta T2 signal. There's our overlap. There's potentially tumor not being treated. These are images at time 0. I don't know what happens at 12 hours or 16 hours or 3 days, but nevertheless, that's our immediate snapshot. So can we do better? The short answer is yes. This is the patient with bidirectional catheters going through the diencephalon en route to the pons. Professor Gill was here, still here. With regard to multi-port systems, multiple catheters, and it makes sense. More catheters, wider distribution, overlapping fields. What is that threshold? Unknown. That's certainly what we've seen with a single catheter. I haven't felt inclined yet. Catheters with directional capacity. Inject in one direction, change orientation, inject in another orientation. the group at Cleveland Clinic. Multi-port systems, these are on the market, these are available. Again, this directional capacity for sculpting your tumor itself. I think that one of the things, Chris Bankowitz, his name has been mentioned a couple times, a phenomenal individual from the standpoint of developing a lot of these platforms. So this idea of computational modeling, using DTI imaging, rates of infusion, volumes of infusion to build a computational simulation of what you expect to achieve. This has been validated in the basal ganglia. We've got a large cohort that we're working on validating this in the pons now as well. So integrating it into the preoperative planning becomes very, very enticing as we see here. This is our PET scan overlaid on the predictive model here in red, and then the actual delta T2. So no question, this idea that you can use these algorithms are probably representative of what we expect to see post-infusion. The other thing is the idea of using a surrogate tracer versus your therapeutic molecule. It makes great sense during the infusion. There's no efflux, there's nothing being sieved into the ventricular system. This plot over here is a patient treated with an oncolytic virus with co-infusion of gadolinium. And if you look somewhere around that 18-hour mark, there is no more gadolinium. So what I'm going to call the pharmacokinetics of CED is lost after a couple of hours. This is an example of one of the patients treated in our trial. This is a whole body PET from time 0 to 8 days, the overlaid PET scan on the MR. So clearly at 8 days, we're still seeing therapeutic molecule insofar as the degradation or the decay of that isotope. So clearly between gadolinium and an actual therapeutic substrate, there's some discordance if you go hours beyond the infusion. And this becomes problematic from the standpoint of scheduling. Prolonging exposure doesn't make great sense. Again, phase 1 study versus phase 2, I'm going to come back to that idea from the standpoint of design. Prolonging exposure, single injection doesn't make great sense to the oncologist. It depends on the agent, of course, but it would be simplistic to think that you're going to achieve much with GBM or DIPG with a single therapeutic administration. Jeff Bruce at Columbia with topotecan, implantable pumps, he has this currently open for continuous or long-term infusions. You've heard to some degree about polymers and the idea of impregnating chemotherapy within delivery vehicles for prolonged or controlled release of administration of drugs. Again, gets around this idea that you need to do repeated injections if you have a controlled release polymer in a different format. Kathy Warren, who really waves the flag, who was down at the NCI with regard to pharmacokinetics of delivery of therapeutic molecules. You can see on this plot here work we've done together with systemic administration versus local drug delivery or CED. But most importantly, it's not just a single snapshot. This is longitudinal over time. This becomes really important from the standpoint of designing schedule. I think we flip a coin a lot. Should we do this every 2 weeks? Should we do it every 4 weeks? Should we do it every 3 days? It's really arbitrary without these type of real good pharmacokinetic monitoring systems. And then you go into the realm of, if we can see the drug, then we can design better clinical trials. However, there are few, if any, therapeutic drugs that are available that allow us to see this in real time. We partnered with groups to label therapeutic substrates that we're interested in for the disease process. We're not limited to just one drug. An example of one of those with panabinostat, you've heard about it from HDAC inhibitor. Every time we do this, you got to go back and look at bioavailability, bioactivity, test this against your catalog of cell lines, et cetera, do the in vivo modeling. So this becomes extremely laborious from the standpoint of taking a great concept, I want to see the drug, and translating that into something that makes sense. The effort there is huge. You heard from Dr. Newell, elegant work with regard to how do you interplay the potential interstitium and the endothelial membranes. I think none of these stand alone, whether it be MR-guided focused ultrasound or breakdown of the blood-brain barrier, manipulation of the interstitium. These are so incremental and take a lot of effort to plug into these types of clinical trials. I think as neuro-oncologists, certainly we need better thoughts about how we're going to do this in a much quicker, iterative way. And the other thing I'll say, and the last thing I'll say about the design of these, and entering into the clinical realm. And I remember having this conversation with Jim Markert, who's in Alabama, who works a lot with viral oncolytic therapy. This idea that we're looking at overall survival is so remiss with local delivery platforms and direct drug delivery platforms. We're treating these in a regional domain. We're not treating this tumor in a systemic way, where we expect the same concentration of drug to be universally affecting that tumor. We've got to be a little more smart about measuring in early phase clinical studies whether or not we're doing some type of benefit. So these conventional approaches in looking at overall survival, survival at 12 months, event-free survival, are extremely catastrophic when we're trying to measure efficacy in these early clinical trials. So we're looking at other things. Can we look at regional control, patterns of relapse? Can we use the contour of a very anatomically defined area where tumor definition is really hard to define? So we're putting some emphasis, as others had, to look at anatomical domains as a measure of success. Of course, the neuroradiology literature is replete with novel ways of looking at tumor response monitoring through MR spectroscopy, through perfusion, et cetera, et cetera. So these become extremely enticing in a regional map. And we can look at small voxels and apply that to where our drug therapy has been given. Molecularly defined agents, so labeling agents that have affinity toward the tumor, so we can do quantitative molecular imaging and get a readout of tumor burden, not just the morphology. Is something that we're very excited about. You've heard about liquid biopsy as it applies towards certain CNS tumors. This is kind of a very enticing area in the world of DIPG as well. So I'd say that as we design these trials, we've got to let go of the convention, start looking at regional response monitoring if we're going to measure any efficacy in this type of milieu. And the last thing I'll say with regard to one of the problems is this idea of regional therapy. I remember at a recent FDA symposium, Kathy Warren, who I value her being the last good up, said, well, this is silly. It's not a regional disease. It's highly infiltrated. Things can be held for GBM. These metastasize late in the course of therapy, well established and shown time and time again. What I'm enticed by, however, is you put the parallel on something like medulloblastoma, where if we gave up with very good surgery and didn't prophylax the CNS, you'd be still the same we were 50 years ago with regard to poor survival. And this example that I showed that well over 3 years, fairly good regional control. And about 2 months after this follow-up, closer to 40 months, she comes in with this MRI scan showing disseminated disease, biopsy proven in the spinal compartment. She's still doing well, but nevertheless, can we focus on local control as an endpoint for something like this? So say that I have no reservations looking at the power of these types of drug delivery platforms and trying to harness this in a thoughtful way. We can do this safely. There's no question in my mind within certain parameters that we've tested and others have tested. This idea that we can get drugs, avoid systemic toxicity is real, and we can do this safely is powerful from the standpoint of pushing forward. As I mentioned before, the sculpting, the demand, these are currently in process right now with regard to what can we accomplish. And I think that we can probably do a better job based on what we've been doing in the phase 1 study. And if we start to see, hopefully, some regional control, I think this raises the question as to rethinking the paradigms the way we treat these. So what I'd love to see is this convergence of thought. And this nice review that was written back in 2017, looking at everything that's been done in the supratentorial compartment of malignant glioma in adults. Not much different from the standpoint of sentiment you take out of this. You always see these types of anecdotal responses based on imaging characteristics. We can do it safely. Patients are tolerating it. And there's no benefit in overall survival. I mean, it's logical as to why we're not seeing benefit in overall survival, at least within some domains. So as we push this forward beyond these barriers, as you go from feasibility to optimization, agent selection is going to be a biggie. You can hear that time and time again. But I also think that these types of therapeutic endeavors open up a huge avenue from the standpoint of agents that were certainly off the table before. understanding the tumor biospecificity, receptor status. What are we using, and can we start to parse out which patients are good candidates or not? The reason we chose not to do this in the phase 1 study is because we didn't want to contaminate our toxicity reporting with upfront therapeutic endeavors like biopsy. As low as it is, it's still a potential risk. But I think in a phase 2 study, without question, that's going to be done. Treatment volume, maybe we cap it. We're going to be really disciplined about this. We don't take all comers. So we're going to stop at certain volumes that we know we can overcome and cap it at a certain volume. And that's very enticing as we design this phase 2 study. We need to determine whether or not we're encompassing tumor. And I think that being very objective about this, if we're not getting 90+% of that tumor coverage, they shouldn't be looked at from the standpoint of response or not. Same thing with coverage. Frequency of administration, again, we're going to have to think of ways, but more importantly, define how frequently. Not just can we, but when should we be redosing? And the last that I feel very strongly about is this idea of response monitoring and going away from conventional oncology parameters and looking at specifically regional response monitoring. So with that, I'll close and thank you for your attention and the invite.
Thank you very much for a fantastic session, which was really an effect of the collaboration because some speakers were invited by me, then Dr. Brem by Monica, and then Dr. Walker invited Dr. Sawayden. I think that normally we should go now for the panel discussion, but the lunch is waiting for us. So we need to have, I think, like 15 minutes to grab our food, and maybe in 15 minutes we will start. Fun. Yeah.
Should be fine. However, we just predict Taking MI and no, if you this will be to connect it. Is there any way we can transfer? So if we use it, we cannot process. We have a need for HDMI, so it's possible we could transfer the code that we could This is USB-C. You don't have USB-C. Yeah, this micro DDI is we have it, but again, it is not to HDMI, so it's not right. It's not right. It's cool. If you want, we can have this.
Safe and
Thank you. Okay.
Hello, Merrick. Can you hear me? Yeah, we just, hello, Merrick? Oh, good. Very good. Okay, that's better.
Okay. Okay.
That's better. Okay.
Um,
And you're going to pass that mic around to everyone that speaks, right? How are we going to do that?
Sorry, I'm not able now to do. Okay, I think let's now start, and then I will look at that when we'll go through the
no problem.
questions.
No problem.
Today we have really great honor to have the three giants in the three different fields, and I think this is something that we really want to learn how they different, how they are the same, and then how they can combine trends and or they could be one after another in the path to the treatment. So I think that we should start from the questions from the audience.
Okay.
Thank you all. And question for Dr. Brem. I really enjoyed your talk. So I remember a number of years ago, I went to a talk, and someone was talking about, you know, the stuff that you did with Bob Langer and the wafers and so on, and he talked about, I mean, the issue was not just getting the drug locally and in high enough concentrations, but and in a controlled release manner, but there was also the issue of penetration, that despite, you know, having a drug there and the strategy being, you know, very well kind of approach being, you know, very appropriate, that, you know, the drug was being released and so on over a long period of time in adequate concentrations, but it simply wasn't moving far away through the interstitium to getting to the targeted cells. And I was just wondering if I noticed that you didn't address that specifically. I don't know if that truly was an issue, but I just wanted to know kind of your thoughts and maybe respond to that. And again, I'm not saying that this is fact. I'm just saying that's how it was presented to the audience.
So drug distribution is a critical issue in any pharmacokinetics and any therapy for the brain in particular. And all three of us spend most of our careers finding ways of maximizing that and optimizing that. I think that if you look at the early stages of, you know, our work, nobody had any tools for measuring penetration and drug concentrations. And in fact, you know, I think the reason a lot of really good drugs failed was because nobody knew if they got into the brain or didn't get into the brain. It wasn't measured. And so I think that if there's any contribution, it's focusing on that issue. I think as far as the pharmacokinetics itself, I mean, people bring up all sorts of issues. I mean, we published very extensively. I didn't show a lot of data here. We published very extensively about pharmacokinetics at point release and drug release with controlled release polymers. And the bottom line is the 3.8% carmustine wafers release 4 centimeter distance from the point of the initial source for a period of 30 days. And the half-life of BCNU in the bloodstream is 14 minutes. So you have log orders higher concentration penetrating the distance that we think that glioblastoma is, you know, more than the distance that is necessary. In other words, an umbrella that's larger than this. So why do people fail? Why do they recur? I mean, that's the, you know, unending issue. There are a few cells that are distant to that then proliferate. Do they get resistant to the drug? There's no cancer that is effectively treated with monotherapy. So if you take gliadel, which releases carmustine, and you test in isolation, you uniformly see an improvement in survival, but ultimately, and I can't find an answer on my Apple. But it uniformly, you know, fails. But breast cancer is not monotherapy. Lung cancer is not monotherapy. So I do think that part of that is drug resistance and understanding the heterogeneity. The earliest papers that we had on pharmacokinetics talked about 1 millimeter or 2 distance because of the difficulty in quantifying the radiolabel.
I think those are the numbers that
So
were
those
given.
papers that are, thrown back over and over again. So there are papers in monkeys and, that show the 4 centimeters and that's very expensive pharmacokinetics. So the bottom line is, I don't think that's the rate limiting step. Certainly some degree of less cell moves across the midline and are very expensive. Most of them occur within 1 centimeter of the initial tumor, and we know that we're flooding that area with drugs. But I think one drug is enough. It's the real one.
Thank you.
Maybe I will follow up on that. I was interested whether you can use the microchips, the biodegradable microchips, to sense in a way what is going on this interface between the resection cavity and possibly infiltrating tumor. I can imagine that, for example, metabolic changes could be read out, from the vicinity of the tumor, giving you information what type of recurrence you are facing actually at the time you see the tumor, or even allowing to tailor the second line therapy, for example.
I think those are great ideas. And the microchip in its first description was looking at both metabolic, like for example, they released insulin. They had enzymes that were sensitive to different concentrations of glucose, and if it hit a certain level of the enzyme being activated, it released the next well, which had the insulin in it. So there are very clever ways that you can design these microwells that will metabolically be triggered. And the parathyroid hormone, for example, is calcium levels. It can measure the calcium levels and then release as the calcium levels start going up and shoot out parathyroid hormone. So whether we can apply that to malignant brain tumors, there are pH differences and so on, but I'm not sure that we're there yet, that we understand it well enough. We do have ways today of measuring, drugs, in animals certainly, and in people of really measuring concentration with microcatheters and so on. So I do think we have a good sense of drug distribution when we look at these new therapies. And I think it's critical that that be included in the science.
So I have a question about the convection enhanced delivery and maybe actually some discussion about the two approaches from Stephen Gillies yesterday. And Mark, is this comparison of the multi-catheter approach and the single catheter approach. Could you just use one catheter and push a little farther and achieve the same, or multiple catheters are necessary?
I wish I knew the answer. Yeah, but I think it's, I applaud the fact that individuals, whether it be convection enhanced delivery or IA therapy or direct administration with biodegradable polymers, these are so overlapping in so many ways. And many of the questions that are posed to us, as you just heard, depth of penetration, these are valid issues. And it's Professor Gill, and so I really respect the work he and his group have been doing from the standpoint of a very asserted effort to encompass more of the tumor. It makes logical sense. It's the right thing to do. I don't quite understand yet what the demand is going to be. And I think that, and I kind of made some reference to it with regard to the degree of tumor overlap. If you put on the thinking cap like a radiation oncologist, it makes perfect sense. Right? If you encompass more tumor, you should treat more tumor effectively. I think a lot of that's governed by what happens after deposition of your agent. We don't have a really good understanding what happens after time 0. Once that gadolinium cleared, there's truly interstitial forces that continue with pressure gradients, concentration gradients. I don't know what that distribution looks like at 24 hours and 48 hours and 2 weeks out. I think the agent plays a large role in that. A bioactive substrate that adheres to a cell receptor versus a self-replicating viral vector versus an inert cytotoxic agent. Those kinetics are going to be vastly different. I'm convinced they're vastly different. But I honestly don't know what the target treatment is, and I do think that it's going to be variable based on the agent you're using. So those are unknowns. Insofar as the kind of the guttural idea of encompassing more tumors, sure, more catheters make sense. But I do think what I'd like to do is push a little harder and understand what the limits of a single catheter are. Maybe it's 2 catheters, maybe it's 16 catheters, I don't know. But I don't think we as neurosurgeons have challenged ourselves in a very disciplined way with what can be accomplished with less. So I think that's the platform that we're running with. This is also, I'll say, is, again, going back to this idea, do I want to build a phase 2 study and look at clinical response and really challenge whether or not this therapeutic platform is working? Or do I want to just do this in a very tempered, calculated way, not to endanger the platform of one of these therapeutic modalities? We were talking at the break with Dr. Woodward. As you roll this out in your clinical domain, one has to be very, very conscious of the idea of threatening the platform because we didn't cure glioblastoma, because we didn't cure DIPG. The likelihood of that happening is so incrementally small for many reasons that all of us know. So, my mission in this has always been to demonstrate safety, demonstrate to the neuro-oncology community that we can do this safely, that we can start to get distribution volumes that are at least enticing. And now I think we're at that phase of optimization. So I watch what Dr. Gill and his group is doing with a lot of hope. And I do this with a lot of guidance. And I'm sure he'll say the same thing. And I don't mean to digress. That's a number of times I've picked up the phone and called Chris Bankowitz, and who's a functional neurosurgeon. What do I do here? How do I do this? What device should I be using? Is this safe? How can I fix the catheter? How can I extract the catheter? There is no platform. There is no reference manual. So it's a small community. And so I look at this with excitement as individuals are doing something different. The last thing I'll say, and I'm sorry to make this a diatribe, but I'd be interested in your comment. These types of environments are amazing for us as individuals to come together, not just from neurosurgeons, but oncologists, radiation oncologists. Not just in concept, practical ways to enhance what we're doing, smart ways. What have you learned that didn't work? What do you wish you had changed? Having these conversations with Professor Brem, who there is no convergence from the standpoint of technical issues, but I've watched what he's done in 15 years, and there's so many parallels as far as steps that you might take, right or wrong. I'll close with that. And if you want to say anything, Professor Gill?
Thank you very much. It is a complicated thing, and we don't understand really what happens with fluid that we push in the brain and can be conducted away by nearby vessels and all sorts of things. I think what I've learned over time is that if you push too hard down a catheter, essentially you're distributing your drug down a pressure gradient, and there's a point at which the pressure at the tip of the catheter to achieve a reasonable degree of convection becomes enough to start disrupting the tissue locally. You start then inducing side effects in patients, which are dose or treatment limiting. And I think, and I don't know exactly what the formula is, but I think I feel much more comfortable putting a lot more catheters in and doing it much more cautiously. And yes, you've got to have a pressure gradient, but it doesn't need to be too steep because you'll start causing problems. And for repeated delivery in the brain, as soon as you start creating a vacuolation at the tip of your catheter, that'll preferentially expand. And so, again, I'm going in the direction of putting more and shaping the volume by putting more in. And I think it's possible to put quite a lot of catheters in quite safely, done in the right way. So that's fine. Thank you.
I can just add one other thing, and it goes back to the first question as well. The the real, to me, the real formula is there's no one formula, no one solution. There's no one method, whether it's blood-brain barrier disruption, CED, polymers, microchip. They're all techniques. And I think where you start from is what's your therapeutic agent, what's your therapeutic target. It's very different if you're dealing with a brain stem of a child than if you're dealing with a frontal lobe, big fungating tumor. Where I looked at this field in my work with Bob Langer and now with Jordan Green, is the question always becomes, if I say I want to put something to a polymer, I say, well, that's simplistic. What is it you're trying to do? What's your release capacity? How long does it need to be exposed for? Do you need 15 minutes? Do you need 15 hours? Do you need 2 years, which can be done with, there are ways to release over that time period. Do you need bursts? Do you need continuous infusions? And then figure out what, we've spent our lives developing techniques for how to deliver it, but they're just tools. So for some agents, you should disrupt the blood-brain barrier. You should get it in the blood. For some, it's 1 catheter, 10 catheters, whatever's needed. For some, design your infusion method based on, or maybe oil, like Timidol. Maybe a pill was better than that if it worked. So I'm not married to any one technology. It's just a matter of, what works and what is really necessary. Now, for example, with Jordan and I were talking about, with what we're learning about immunotherapy, we may be going about it all wrong. It has nothing to do with it, whether it's a catheter or a polymer. It may need to be delivered locally and then give the systemic boost to the immunotherapy. Those are the fundamental issues. And then what technique we use, you just trial and error and make sure you look. I think when I started in this field, nobody was looking. They tried drugs, they gave it IV, it didn't work, they moved out. The drug's no good. And we should be way, way, way beyond that. Now it's choose which technique is better.
I have a question about the CD. There are some animal models now that it's enough that you overexpress PDGF. It's like you have no genetic mutation, nothing. It's just you have more PDGF. It's enough to produce the tumor in mice, for example. So it means that just dysregulation of microenvironment is enough, at least in mice, to make a tumor. And then when you are putting the catheter inside the tumor and then you start the bulk flow from the catheter, it goes outside. So then this microenvironment, which is not good inside which is from the inside tumor, maybe it goes from the tumor. It goes to the, I would say, healthy tissue, which is just next to tumor, and then by that way, maybe I would say infect the environment with this, for example, increased number of PDGF or EGF, and actually starting transforming the cells like a normal cells, which are outside of the tumor, and then that would be like this satellite, like a metastasis. Is it some research on that, for example, that someone, for example, check what is the concentration of PDGF, for example, in the tumor, and what's going on before the procedure, and then what's going on during the CED? If this is if, for example, it really changes, because that's always scared me to take this bad microenvironment and then push to the normal brain. That's why we work more on the intraarterial. But this is what is your opinion on that?
Dr. Brem is shaking his head like he knows the answer, so I'll give him the mic in a moment. But again, going back to the therapeutic molecule becomes crucial here. The ideal scenario, what we all want, is a targeted therapeutic approach that spares normal cells, right? So whether it be PDGF or EGFR or B7H3, that is the holy grail. If you can define something that is so specific that you spare normal cellular substrates, whether it be endothelial cells or microglia, ideally that's what we want. So going back to what Professor Brem was saying about these are all tools. And I think it also depends in large part what you're going to deliver. You can easily envision that, again, using a radioisotope, it also has immune modulation associated with the receptor status. But you can easily imagine that once you exceed therapeutic safety, that you're going to endanger a lot of normal substrates in its path, right? So cell specificity, mechanism of therapy become extremely important. Extracytoplasmic, extracellular versus intracellular, these are big areas of unknowns. But I think so much of this is focused upon the therapeutic molecules you're using and its degree of specificity before you can make sweeping comments about this is not a good platform because we worry about off-target effects. You did want to say something.
Thank you. This was the greatest, or I'm not saying everybody didn't present well, but I enjoyed this session. You guys did a phenomenal job of probably getting maybe more clinical, and I related more to what you guys are doing and the whole support that the team is getting to get cure. I have two questions. No,
I know we can stop right at that point.
I have two questions. First, from the first presenter, I'm bad with names. You spoke about the first patient, one of your patients who you gave intra-arterial chemotherapy and they had hemorrhagic cystitis. It was intra-arterial. I just want to know the doses that you were in this patient that would also cause hemorrhagic cystitis, which anyway intra-arterial, the dose modification. It wasn't related. So
Hemorrhagic cystitis was due to the chemotherapy, not to the routing.
No, I understand. I understand. The dose that you give in arterial is almost equivalent to the ones that
I
you give.
give less intra-arterially than pediatric neuro-oncologists get intravenous.
Yeah, that was my question.
30% less, but it has a dramatic response, as you saw.
No.
It lasted 15 years.
Yeah.
Kids still doing fine.
No. The question wasn't about it not working, about the dosage. If we're getting hemorrhagic cystitis on that, it was because the dosing that I was asking about, not the response. The second question probably will be the issue of targeted treatment. We always talk about targeted treatment, and they are phenomenal, but apparently it seems these targets are everywhere. Year 2 was the target for breast, but it's in glioblastoma, it's in esophageal cancer and gastric cancer. It seems as if these targets, which we initially target, end up being everywhere. How much are these targets really targets? Because at the end of the day, you give cetuximab, the patient has a rash. It seems as if these targets are really a target, but almost like we're targeting a target that is everywhere, especially for giving systemic treatment. I'm not sure how much are these target treatments.
Well, but
for probably the other presenter.
So, if you're asking if targeted therapies are real, I think we are at the tip of the iceberg of targeted therapies, and we're seeing with our molecular biology colleagues like Bert Vogelstein, our department, Chin Betagawa, we're designing individual therapies based on overexpression of genes that in the individual people are unbelievably powerful. We have patients who are end stage, everything failed, they're progressing, we map out the progression, and then we infuse a very specific inhibitor for something they're overexpressing, we see very dramatic responses. So I think the idea that it isn't useful, I think we don't know how to use it yet fully. And I also think it's not broadly applicable. In other words, because one person gets a beautiful response, the next person, it can be irrelevant to, unless they're overexpressing that gene. So I think we're just, I mean, to me, it's only in the last 2-3 years that we've been seeing those kind of responses. But I'm very optimistic about it. But it's not going to be broadly available. It's not going to be for everybody. We're seeing IDH1, inhibitors in fusion being very dramatic responses. But we need to see large scale. We need to see how consistent it is, and we need to be smart enough to know which patients to use them for and which patients not to use them for. When we only had one drug, when we only had carmustine and CKU, and now Timidar, we use it for everybody, for everything. And it works for some people and it doesn't work for a lot of people. If that's all you have, to just shoot it anyway. But these other drugs are too expensive and don't make sense.
I don't think I have much more to add, but listening to your comments, I wasn't clear exactly, but you're asking of off-target toxicity as it gains, I guess, the exposure to the systemic circulation potentially. I always tell my preclinical laboratory that I'm highly interested in agents that have been left on the shelf because of systemic toxicity, that were dose-limiting toxicity agents that had very good biological relevance. Those are the ones that I love to think about and incorporate. I was looking at the slide you showed of the platform of agents that have been, that would be my dream to go back to pharma and say, what agents did you abort because of systemic toxicity and failed regional therapy? Those two ingredients, which are so counterintuitive, just because of the powerful nature of regional concentrations with nearly negligible exposure in systemic circulation, are very captivating to me. So I don't know if that answers your question, but I see it as an appealing feature of an agent that has been aborted because of systemic toxicity.
Sodium, are you using sodium thiosulfate in your pediatric oncologist? I mean, what you do is you give a dose of platinum that will give you tremendous kidney and ototoxicity. But if you wait 6 hours and then get sodium thiosulfate, you go from 80% ototoxicity to 50% hearing aids to 0. And that just came out in the New England Journal. I mean, so one way to play the game is to give doses that are toxic, like methotrexate, and then rescue. And sodium thiosulfate and N-acetylcysteine are very successful, not only to prevent the ototoxicity, but the nephrotoxicity. And substantially interesting is thrombocytopenia and mucin vein cytopenia. So doing things like we've been doing for decades, methotrexate and leucovorin, is very helpful.
Am I allowed to ask a question? One of our panelists. So I'm curious from the standpoint of the biodegradable polymers. Can you speak on how important contouring is? Based on your response to the question about depth of penetrance, it seems to me that it wouldn't necessarily be important. But one of the things I've always been intrigued by from the standpoint of applicability is those tumors in the cisterns and the subarachnoid space that we can do a really good job with gross total resection, but the microscopic residual embedded in the cervicomedullary fissures and the folia. I know that there's been, and I think some in the audience, with hydrogels and other contouring agents. What do you think about the idea of these that have a greater capacity to contour to these types of spaces?
So, there are polymers that can contour and can go to any shape, and you can almost put them in liquid and mold them into shape. I don't know, in the brain, we've not put a lot of stock in that. Certainly for glioblastoma, we have a cavity we line it. We don't cover every, it's not like surgery cell that you lay on and cover the whole surface. You just sort of space it around. And you assume that with the, massive modulators of drug that's being released, saturate the whole area. Some of these corners and spots, certainly anything that goes in the ventricle, we're very hesitant. We've been very hesitant to put any physical implant, because if it goes into the ventricular system, plugs it, then you can have, constantly sort of so although we've never seen that, we worry about it. So I think that you could design things, but I think with the current, very limited number of problems we have,
use more just another way so we can get a high enough concentration. But there's work to be done. I mean, there's tons more.
I have a question for Dr. Newell about the mannitol blood-brain barrier disruption, and you showed the catheterization in the more proximal carotid and vertebral arteries. So say your target is more, yes, correct, but still, correct. But this is my question. So what, my question is, if you had a more localized target in a specific vascular territory, would you consider a more selective distal catheterization to reduce the blood-brain barrier disruption to the whole hemisphere? So if you only had MCA or
This is where you get a
question.
You get a partial response. Our statisticians look very simple. And Brian was in the you get a partial response, even though you really don't. So we're only treating patients. So we have I don't see any malignant primary brain tumor, any metastasis is a local disease. I think, in my experience, I'm not talking about pilocytic astrocytoma, because I think you can really hit them with localized HR2. And I also think chemotherapy is not dead, because especially pediatric neuro-oncology, they've got targets that they're doing spectacularly well, identifying and characterizing. But the efficacy of those, especially to get a complete response, I think has been pretty modest. So I think all malignant, high-grade gliomas, breast, lung, you don't treat the whole brain, you're not going to win.
I have a question for Dr. Newell. And what's the optimal timing for drug delivery after blood-brain barrier disruption? Do you do it immediately after money? Yeah. Just how long do you inject money so often? 30 seconds.
And if you inject 15 seconds, you get no blood-brain barrier.
Okay.
You have to completely replace the intravascular blood with mannitol for D 25.
So it's quite a huge volume of fluid.
It really depends on anesthesia. You use isoflurane.
Yeah.
One kid, he had 14 cc per second.
Yeah.
For 30 seconds. That was 300 cc per 30 seconds. And, but if you switch to focus, you only have to get 2 to 5. You get much more consistent. But you don't want extra. That could be you want good distribution. Yeah. You regulate the amount of you get good but not great. So if you get a great disruption, you can get enough to after this.
Yeah. And how do you assess the disruption?
Immediately after the install, yes. We don't use MR because we're also in the minority. We did a dose response to we did a dose response after dawn in 0.1 to 0.01 point we use this after medicine. The animals that control the sample only got that. They will have 20.5. And 25% that have 30%. 21 is 50%. 22 is actually 5 doses. 75 include dose doses. So we're very often get. But high demand contrast is very safe. You can correlate that very directly to the drug that we do. So that answers your question.
Yes, thank you very much.
Just a question. In some small children, that volume of mannitol will be a significant nephrotoxic problem and could precipitate renal failure. I remember when.
Never done anyone less than 50 than 18.
Okay.
I don't know about what.
I'm thinking about a patient we had. I mentioned to you she was about 3 years old, and I ordered the mannitol from the pharmacy, and they did a calculation, and they came back and they said absolutely not. You know, that's going to destroy the kidneys in this child. And we adapted it. We used a lower dose, but I'm wondering, in these kinds of cases, we obviously want to be able to treat all of our patients and offer them this. Is there an adapted formula that you know we might be able to reduce the dose in a small child?
You could reduce it to 20 seconds without any problem. But if you go below, that's the absolute minimum you have to do for 30 seconds. You can probably go from 30 seconds to 25 seconds. But I've not seen, I don't, maybe the same mistake, but I don't know that, well, we just don't treat kids less than 15. How old was the kid you were talking
3. She was 3.
And we several of the kids who were 3 were pretty small because pain was on the radiation and both on the radiation. But we are now, we use sodium sulfate to protect the hearing and the kidney. And we had one kid, what's the name of the kidney that I mentioned to you?
Some nephrotoxic syndromes.
Chemotherapy. Yeah. The sodium went up to 170. I just about choked every time. The kids would feel right through it. But I normally, I really would not say treat kids with fine. When you have kidney problems, then the sodium is important. I never had a patient. It only lasted about 45 minutes. Generally, kids really tolerate it. It's extraordinary.
So I want to follow up on what Mirek just said before about the PDGF and other factors, so the microenvironment of the tumor. So far in oncology, the focus was practically on destruction, damage, destroy tumor cells, and it has been difficult. So do you think there is a space to consider strategies on normalizing the microenvironment, delivering drugs instead of destroying brain tumors, maybe stabilize some molecular pathways? Is there any effort in that direction? All the panelists, if you know of such efforts, since these destruction-based approaches are so challenging, and is there a room to consider these molecular strategies, understanding the molecular signature of the microenvironment and trying to stabilize something that is driving proliferative disease?
So it opens up the door to a whole very interesting area of research. One is that we focused on the cancer cell, and we have chemotherapeutic agents, radiation, and ways of killing cancer cells, and yet all the malignant tumors, the glioblastomas, keep coming back. So we looked a number of years ago with Vescovi in Italy and Francesca D'Ameco and Alex Levy at the stem cells that are in these glioblastomas. And so it's very interesting. You can take stem cells from GBM patients, and you can treat the stem cells with a differentiating agent that are very innocuous. They're used in spine surgery. They're FDA approved, and you can reverse them from being glioblastoma stem cells, and you can shut them down. So part of thinking, and that's just going into clinical trials, is maybe, again, we have it all wrong. I mean, yes, you have to take care of the cancer cells, and there are ways to do that. We sort of know how to do that to various degrees of success, but you always fail because you've got these fairly well differentiated stem cells that are not responding. They are not affected at all by temozolomide or BTNU or radiation therapy because they're not really replicating. They're just sort of spitting out, or they are replicating, but they're not sensitive to it. But a differentiating agent shuts them down, and maybe that's exactly the same sort of approach of like, here's a way of turning off the group of cells that stop the recurrence. So that's being tested clinically. It's just going into clinical trials, I believe, on the West Coast. And that sort of approach is very attractive in combination with these other, as if we're just learning.
So again, using some of these chemoprotective agents to protect the normal tissue and differentially kill the tumors, I think is a very exciting direction. I mean, for instance, in children who get gram-negative sepsis, aminoglycosides are life-threatening, but they're incredibly nephrotoxic. But the fact is, the final point of injury is free radicals, damage to normal tissues by free radicals. So if you can make the free radicals less in where you're treating the tumor, you're not affecting the chemotherapy. If you wait 6 hours, the damage to rapidly dividing cells, but you can protect the normal tissue, which is not exactly what I'm saying. But I think doing chemoprotection along with such modest the doses, you don't have to give high dose chemotherapy when you use nanoparticles. The brain is 100 times. Yeah, you'd have to give. We give 3 grams per meter squared of methotrexate. That's the equivalent of 5. We give a constant dose for the first pass. That's the equivalent of 5 grams in kids that are over 13. And to get the same dose in the brain that we get with 5 grams, you'd have to get 500. So the rest of the body, the kidneys, the cochlea, the bone marrow, we protect them with these chemoprotectants, which are incredibly safe.
Saying something I shouldn't. Yeah. Conceptually, it's lovely. This idea of forced commitment is wonderful, and I think it holds great promise. So again, it doesn't have anything to do with the route of delivery, but this is more for the biologist. Listening to the conversation, however, and putting on my pediatric neuro-oncology hat, and I always will say we have cured medulloblastoma at a very, very good clip, 70–80% survival, 3 years, 5 years, knowing nothing about the molecular profile, before Michael Taylor and Stefan Pfister did their wonderfully elegant work. Not to discount it, we want to reduce morbidity with treatment, so risk stratification will become important, but we can cure cancer with cytotoxic therapy, and we've demonstrated that. We do it with medullo, we do it with germ cell tumor. The concept works, right? How to do it in a less toxic way. You don't dose escalate every patient. You don't wipe out the bone marrow. The selectivity of these agents have been governed by a very important feature in the CNS, and that's mitotic activity. Again, the brain's unique in that. That's why we see the bone marrow and the hair follicles. The intestinal mucosa gets disrupted. But you've got an inherent signal in a lot of these highly malignant tumors in the brain that we can capitalize on. And the same thing's happened with radiation therapy. I'm not saying these aren't without risk, but I will say that they have great, great value.
Hello, Merrick.
Just some more.
Merrick, we have a question from a med student.
Yeah.
Okay, go ahead, Abraham. Go ahead, Abraham. Go ahead.
Great. Hello?
Yes, go ahead, Abraham.
Can you hear me?
Yes. Can you hear Merrick?
About different methods and technologies to deliver drugs, and mostly we're concerned about
wait a minute.
barrier and what's wrong in preventing effective therapy. So I want to have your thoughts in the era of immunotherapy. What is the role of the blood-brain barrier and of these technologies that we discussed?
We think a little chemotherapy in the checkpoint antibodies. We have a protocol. It's going to open that. You see that one too. We think the blood-brain barrier is very important. Checkpoint antibodies. The current primary treatment, which normally doesn't do very well, we have a 50% complete response rate combining Pembro with CD20 antibody. Complete and durable response, 50%. So there's a Prakash on body in our group that we've got CTEP to sponsor that as a national program. And there's no chemotherapy, immunotherapy, primary, non-AIDS primary. The function of the antibody is there is no systemic in primary CNS lymphoma. It's only the CTEP. But if you get it into the brain, it doubles the survival over blood-brain barrier with this chemotherapy. Went from 30% to 60%. And for patients that are under 70, our statistician says that our median survival is no CD20 end of 12 years. And we're predicting that with CD20, both during blood-brain barrier disruption and as maintenance, it looks like we haven't gotten there. It looks like we're going to have an 80% response. And no dementia.
Related to the blood-brain barrier question, you mentioned that you saw a big difference between isoflurane and propofol.
Tremendous.
Do we know do we know something about the mechanism for that difference, and could that have a relation to?
Isoflurane gives you a lot of vasodilation, where you don't get that. There's a paper in Anesthesia and Analgesia where we looked at blood pressure, PCO2, rate of mannitol, 20 versus 25%. And the big winner is switching from isoflurane to propofol.
And so is that on the outflow end in terms of, is that because of the capacitance increase on the arterial end, the outflow, the venous side? Because I mean, I imagine the capillary is
We're more
what.
advanced than that. We just took all the parameters. I mean, if the PCO2 is too high or too low, you know, there's a tremendous difference in vasoconstriction. So we like the PCO2 between 27 and 30. But if you do that with focus on, you can use one-fifth of the dose of Miroslaw. I can get anesthesia, and I'm happy to send it.
Yeah, I'll look it up. Thank you.
I would like to add one more question. In general, about the potential value of using direct drug labeling to make the therapy precise, especially if you go to more and more frequently used biologics. This is like in part also based on our research, but there was like a wonderful paper recently published with Dr. Sawaidena as a second-class author. I was in mice, but was shown that the small molecule, even given intraparenchymally, within 40 minutes disappears. So it's like how value is it? Whatever you do, if you do intraparenchymally, intra-arterially, whatever way, this 40 minutes probably will not necessarily will give that response if you're doing really the procedure. You're really doing like a procedure and just for 40 minutes. And then there was the big molecule which stayed for very long. And at least at this level of the development, should we put more effort on really direct labeling of the drugs? And then I suppose that there will be also differences from patient to patient. In one patient, the blood-brain barrier will be effective, for example, and they will kick out a drug within like 2 hours. In another patient, it will stay like 2 weeks, you know. So, and I think it's not only to get there, but to keep it there. Don't allow to get drug out, and then it's really no way to see if the drug is still. It's not kicked out without direct imaging. But obviously, it causes more cost. It causes like all the problems with introduction of such labeled drugs. But because all these diseases actually mostly are lethal, maybe we should take this effort and really grab it and make it really precise until really we get the good response and really have the precise drug delivery. What is your, probably Mark will be the first, but I think that probably all speakers could a little bit, panelists who could comment on that.
I think everybody in the room would agree that if you can in vivo, measure and monitor pharmacokinetics of a given agent, whether it be given systemically, IA, biodegradable polymer, or via convection enhanced delivery, or enhanced MR guided ultra, everybody would agree it's a very useful adjunct. There's no question. The 40 minutes that you mentioned, it's going to be highly variable depending on the agent, the tumor, many features. But I think the consensus would be that if we can determine in a patient-per-patient basis or with a certain therapeutic molecule what the pharmacokinetics are of that particular agent, that would be hugely beneficial as it translates into a clinical realm. Whether or not this has to be done for every agent and for every patient is an unknown. It's perfectly reasonable that if you have a small target, you can demonstrate preclinically that you get such a distribution. You can monitor pharmacokinetics either in vivo or not. I think the desire we want is to understand where that agent is at any point in time. And I firmly believe that without it, you can't design really good, reliable phase 2 or phase 3 studies, which are by definition created to look for a response. You can't do it adequately. So, I will beat on that drum as far as wanting desirable pharmacokinetics on every agent I take into a clinical realm. Not easy, as I've outlined, extremely problematic, from the standpoint of taking a agent and not interfering with its either bioavailability or bioactivity. So these are real features. I'm quite surprised that major pharmaceuticals haven't jumped into this idea of real-time monitoring. Maybe because with systemic delivery, they don't feel as if it's necessary. You can monitor in the plasma. But we know in neuro-oncology, insofar as treating tumors, that that's such a gross underrepresentation of what's going on in the brain. It's badly needed.
In general, but I think that probably biologics are the most sensitive to this problem. And then this is like still, if you're doing on animals, it's mostly they are very similar, and in human to human you have, and then like at a different age, different race, etc. So there's a lot of variability. So it's something that it's not necessarily possible to really model it on animals.
I can't agree more. And it's not just the animal versus the human, the tumor as well. I mean, we use biologics and monoclonal antibodies and viral mediated therapy, that you can't necessarily replicate that model in a preclinical animal model at all. Yeah.
Put a little paramoxicol, it's totally non-toxic, and you can see where the biologic is for at least 2 weeks. How much is there?
Forces could be useful, although what our study is showing that it's really giving the iron oxide to cells is changing their properties, especially if you need to inject through the catheter. They are more sticky. So PET labels, PET agents actually, where you can really label a very little, they are better. They are not changing that much properties of cells.
Are you talking about, there's Convidex, there's one that's not an SPIO, but there's some of those are very sticky, but paramoxicol has a special carbohydrate coating. To my knowledge, it doesn't stick to anything, except it's taken up by phagocytic cells.
Yeah, so then obviously you can look on the phagocytic cells, but how much it tells you about the drug biodistribution that you are giving. Biologics is not only cells; it's like antibodies are all of these groups of the dendrimers and all this a lot of stuff like antisense nucleotides, etc., etc. So this is like a huge group of agents, and a lot of them are really expensive, and probably adding the labeling to them will not probably that much add the cost. So that's
when you use it and inject it into the brain with a viral vector or other biologic, and then you sacrifice the animal at different time points. It's published in the American Journal of Pathology. The correlation between the paramoxicol histologically and by MR imaging was quite good. Less hemodynamic response.
I think we are 5 minutes after the time. I think that was no 5. Sorry, maybe you would summarize.
All right, so I would like to thank you, our panelists, for fruitful discussion, audience for interesting and intriguing sometimes questions, and hope to catch up for the next meeting with the topic. All right, we'll get started with the next session. Hello, everyone. Good afternoon. My name is Jordan Green, and I'm a professor of biomedical engineering and neurosurgery at Johns Hopkins. And together with Xiaoyan Lan, we'll be co-chairing this session.
which is Mini Symposium 7, Biomaterials and Nanotechnologies. And our first invited speaker is Marcin Krylewski from the Beckman Research Institute at City of Hope. And we'll be hearing about optimizing TLR9 targeted STAT3 inhibitors for glioma immunotherapy.
I would like to thank the organizers, Mirek and Piotr, for the invitation. And I'm becoming more and more involved with glioma, but I'm not really an expert in this area. So this is a fantastic meeting for me to start new collaborations, and I'm very grateful for this opportunity. So my lab is focused on cancer immunotherapy, and we have basically worked on a new type of molecules to disrupt tumor microenvironment. I think we are all familiar, and this subject has been raised already today, with progress that have been done with cancer immunotherapies that have shown promise in multiple indications, not necessarily in glioma yet. And this is basically related to several issues, but one of the most important ones is the fact of existence of very strongly immunosuppressive microenvironment in gliomas. And they are basically classified as typical cold tumor, like prostate cancers, for example, pancreatic cancers as well. And this classification that have been popularized by Tom Gajewski from UC Chicago is basically dealing with a number of T cells being present in the tumor microenvironment, which in hot inflamed tumors can be quite easily detectable, but in cold tumors, T cells are excluded from the tumor area or not detectable in the tumor at all, which is very common in case of gliomas, which have been shown multiple times. But this study from Stanford, published in Nature Medicine 2015, shows it quite nicely. Brain cancers in general show this much larger infiltration presence of monocytes, macrophages, and other myeloid cells compared to any other solid tumors, and of course blood cancers as well. The number of T cells that could be engaged by immune checkpoint blockade or other methods of immune stimulation is minimal. So it's very hard to overcome these effects. And the immunosuppressive microenvironment in glioma really depends on the secretion of a number of soluble factors, including IL-10, TGF-beta, by many of those myeloid cells, especially myeloid-derived suppressor cells and tumor-associated macrophages, as well as expression of ligands for immune checkpoint blocking molecules, secretion of enzymes like arginase or IDO, and the hypoxic condition. So what we have learned over many years, and that basically the work that have been done in the Huayu's lab, and it has benefited a lot from collaboration with Rupert Orr here in Johns Hopkins, was basically the work showing that transcription factor STAT3, which have been known for its oncogenic effect in cancer cells, is actually having this added effect, modulating microenvironment in many tumors by secretion of various protein mediators and also sphingolipid agents, which are able to activate STAT3 in multiple types of myeloid cells in the tumor microenvironment. And in this way, modulate their activity, basically preventing the dendritic cells from maturation, switching monocyte differentiation plots into pro-angiogenic and immunosuppressive tumor-associated macrophages, and also leading to accumulation of the myeloid-derived suppressor cells in the circulation as well as peripheral organs and often in the tumor as well. So these are just a few slides demonstrating these changes in primary glioma as well as recurrent glioma in patients from City of Hope, looking basically at the colocalization of a signal of phospho-STAT3 with a staining for M2 macrophages as well as microglia and granulocytes. And the evaluation of these slides was showing quite, confirming basically the results previously published with large numbers of microglia being detected in this tissue, but most importantly, by a very good correlation of STAT3 activity detectable in the majority of microglia present in these tissues, both in primary as well as recurrent glioma, and a significant number of activated STAT3 also in M2 macrophages as well as granulocytic and DSCs and granulocytes present in these tumors, reaching about 50% of these cells. So STAT3 is being there, and it's likely to operate, triggering immune suppressive effects in these cell compartments, not only in the tumor but also in circulation. So these are the staining done in collaboration with Christine Brown's group at City of Hope, looking at the percentage of myeloid-derived suppressor cells in cerebrospinal fluid from several patients which are entering CAR T-cell trials in City of Hope. There's a very significant population of granulocytic myeloid-derived suppressor cells, and those cells express high levels of arginase 1, which is a target of STAT3, and this is basically a mediator of their immune suppressive effect at T-cell level. So rationale for our approach is now focus on the left part, mainly is basically targeting STAT3 in a cell-selective manner in the microenvironment of glioma, focusing on microglia, macrophages, as well as granulocytic and DSCs, trying to switch the activity of these cells, reprogram these cells rather than eliminate them, from angiogenic immune suppressive functions towards immune activation, which can then trigger anti-tumor immune responses. There's also a benefit of targeting STAT3 in certain types of glioma cancer stem-like cells, where STAT3 is known to promote cell renewal of these cells. So the difficulty in targeting STAT3 is, of course, the fact that it's a transcription factor. So over 50 years of development of small molecules to STAT3 so far have not produced FDA-approved molecule. It's not an enzymatically active protein. So we turned basically to siRNA and more recently to antisense oligonucleotides to target STAT3 at basically level of mRNA. But we had to overcome the problem of delivery on these molecules, and we wanted to enter specifically myeloid cells in the microenvironment. And it turned out that the most effective way to do it for us is basically conjugation of these molecules with single-stranded DNA, which is very rapidly recognized and internalized by these cells, which express toll-like receptor 9. It's an immune receptor which can recognize the presence of unmethylated CpG motifs in this single-stranded DNA. So for targeting solid tumors like prostate cancer and glioma, we have focused on the use of antisense molecules due to the simple fact, which is known to most of you, that antisense molecules are traditionally stabilized by phosphorylation, and this kind of modification allows them to cross the blood and blood-brain barrier, which enables them to get into the tumor microenvironment. And this effect is further enhanced by conjugation of the antisense molecule, such as the STAT3 targeting sequence, with another piece of single-stranded DNA, which enhances the internalization and speed with which this molecule can target myeloid cells. So just to illustrate key properties of these CpG STAT3 antisense molecules, they have ability to penetrate myeloid cells of different types, including the monocyte-derived dendritic cells, antigen-presenting cells, as well as macrophages, but they do not enter T cells. And this is of benefit because STAT3 role in T cells is a bit more complex. It's in case of T cells, STAT3 is actually necessary for expansion of endogenous T cells, but it also correlates with activity of CAR T cells, as shown recently by UPenn in context of CD19 CAR T cell activity. What happens next is basically endosomal localization of this molecule, which happened within a minute, but the molecule is not entrapped in the endosomes thanks to activity of TLR9, quickly released to the cytoplasm. And that enhances a downstream effect on STAT3 activity. So STAT3 knockdown and decrease in STAT3 activity is accelerated for the CpG STAT3 antisense compared to the STAT3 antisense molecule alone. But the most important effect of this molecule that we can, to some extent, simulate in vitro conditions is basically the ability to restore T cell proliferation and T cell activity in the presence of those myeloid-derived suppressor cells, which are highly heterogenic and prevent T cell proliferation. And these effects cannot be reproduced by simple immune stimulation using just TLR9 activators, such as CpG molecule alone, or STAT3 antisense molecule alone. So really, these two components of the molecule create a gain of function effect, which is necessary to restore almost 80% of T cell activity in this immune suppressive microenvironment. Just to show efficacy of this approach, I will show you two experiments from a publication last year showing the efficacy of this method against prostate cancer, not gliomas, but similar to prostate cancer. There is a huge genetic diversity of type of gliomas as well as in prostate, where in these two models we try to basically illustrate the diagnostic effect of CpG STAT3 antisense on RAS-MYC-driven RM9 prostate tumors, as well as PTEN deficiency-driven tumors. So these two models are completely genetically different, but targeting STAT3 specifically in compartment of myeloid cells infiltrating the tumor and creates basically very similar efficacy, which allows for rejection of the tumor in over 50% of mice in the case of this RAS-MYC-driven prostate cancers, and even more of the mice in case of the PTEN deficient tumors. Importantly, in case of PTEN deficient gliomas as well as prostate cancer, STAT3 can play a role of tumor suppressor. So targeting STAT3 directly in cancer cells can be counterproductive, but redirecting basically STAT3 targeting to immune cells enables basically this long-term anti-tumor effect. And this is effect of intravenous injection of the oligonucleotide against tumors which have been localized in the bone. So a few initial experiments done in the orthotopic model of GL261 glioma that I would like to share with you show basically the potential of reaching a myeloid compartment in those orthotopic tumors using CpG STAT3 antisense molecules. We are looking at fluorescently stained CpG STAT3 antisense molecules. The intratumoral injection, of course, penetrates the microenvironment very efficiently. Intraventricular injection does it to significant extent. Over 50% of MDSCs as well as microglia are becoming penetrated by the reagent, but the effect is still detectable through intravenous injection of these molecules using flow cytometry as well as fluorescent microscopy, where you can localize the signal mainly in myeloid cells in GL261 tumors, and also confirm knockdown of STAT3 in this compartment. And again, combination of these two effects, blocking STAT3 as a transcription factor and TLR9 activation is necessary to trigger activation of microglia in these tumors, as indicated by MHC class II expression, CD40 and CD80 co-stimulator molecules. And this effect cannot be achieved by simply stimulating the microenvironment with just single-stranded DNA and with CpG motifs. So we have not yet tested the antisense molecules in IV setting against these orthotopic tumors, but we have done these studies before with first-generation molecule using sRNA strategy, demonstrating an extended survival in GL261 bearing mice, as well as release of the oligonucleotide by 2-photon microscopy into the tumor microenvironment. But we hope to improve these effects based on the very good efficacy of CpG STAT3 antisense molecules, the last generation molecule, in sub-Q grown glioma tumor setting, where compared to our previous results with sRNA, less stable molecules, the antisense molecules lead to rejection in the majority of mice, creating very strong anti-tumor effect, which is again immune-mediated and correlates with infiltration by CD8 T cells. So we hope to expand these studies later into clinical trials in glioma, but our first target for a first-generation molecule, the CpG STAT3 sRNA, which is a proof of principle molecule, is B-cell lymphoma. We will be entering the phase 1 clinical trial at the beginning of the next year, and there is a second trial planned in context of glioma with intracranial local delivery of CpG STAT3 sRNA. So far, the molecule went through 2 IND-enabling toxicology studies in rat and NHP models without demonstrating significant toxicities in this local setting, also due to the fact that it's a cell-selective inhibitor. We have the second generation molecule that is focused on targeting B-cell lymphoma, and this is an inhibitor of STAT3 at protein level. And finally, the new CpG STAT3 antisense molecule that is slightly behind the others, but we hope that that generates a potential for treatment of gliomas, especially in combination with new ways of delivery of this molecule into the microenvironment. So I would like to thank members of the lab involved in this work, and as well as our collaborators at City of Hope, Neurosurgery, the Department of Bernard D, as well as in immuno-oncology, Dr. Christine Brown, working on development of CAR T cells specific for glioma, as well as Karina Budi in stem cell biology department, and Amy Heimberger at MD Anderson. Her studies generated rationale for targeting STAT3 specifically in glioma microenvironment. Thank you very much. Yes.
Great talk, Martin. I wanted to ask, with this efficacy that you showed, extended survival, was this after single dose intratumoral delivery?
That has been CpG STAT3 sRNA. The old study is the multiple treatments with IV delivery.
So, do you think that with improved delivery, you could have a full effect?
I definitely hope so, because the effect will be enhanced by better penetration in the tumor microenvironment, and it could also have this ability to generate this two-pronged effect by at higher concentration penetrating into the compartment of glioma stem cells. That could be the differentiation generating effect.
And finally, if you only need to get to the tumor, or there is also peripheral effect that you need to act on both, because you said that there is the effect on macrophages or T cells maybe, so do you need also to have this on the periphery?
We don't know yet, but I would assume that our effect is an effect from within the tumor microenvironment, and it's supposed to generate basically chemoattractants, chemokines, and cytokines release that will drive in T cells into the tumor. So it does not need to start working in the periphery. It starts from within the tumor microenvironment.
Okay, thank you so much, Dr. Kotelevsky. The next speaker is Dr. Miroslaw from University of Pittsburgh. He is going to present magnetic resonance imaging-based guidance and monitoring of biomaterial implantation into the stroke-damaged brain. Let's welcome Dr. Moda.
Great. Thank you very much for the invitation. And I hope I'm going to tell you a little bit about a different delivery issue specifically for stroke. I'm not going to labor on this slide as stroke has been introduced in the conference. But what I want to point out here is that almost everything we heard about now was in terms of limiting the damage caused by stroke or modulating the acute response to stroke. But as you might remember, in terms of there was this discussion about that core lesion that is there from really early on, and there's nothing we can do about saving that. And it's about like 10 years ago that we started to think about what could we do in terms of that hole that is creating in the brain in the case of stroke, but the same would apply to glioma or TBI. What could we do in terms of a therapeutic strategy to basically replace the tissue that has been lost? And as I'm talking about that, I really want to start to distinguish certain kind of phenomena we see in stroke brain. And let me just see if I can make this work. So we're starting to think about a tissue response, a repair response, and a regenerative response. And the way we think about this is really that the tissue repair is in terms of these neural stem cells that come from the subependymal zone in the adult brain, and they start to kind of invade the damaged tissue, and they're trying to replace cells in there. When we're doing cell therapy, transplanted cells, in essence, we're kind of enhancing or supplementing that endogenous repair response. The tissue response itself would be things like microglia start to get reactive, astrocytes start to bulk up, they start to kind of migrate towards the edge of where the core is, and start to kind of seal off that excitotoxic liquid that is present in the tissue. So that will be the tissue response. And that's the typical thing that you're seeing in terms of stroke and kind of the host potential in terms of repairing the damage. And that repair response is essential if we want to regenerate anything. All mammalian animals have this kind of tissue response in terms of in the brain, endogenous kind of neural stem cells being produced in response to damage. What none of the mammalian species has is really when a tissue cavity occurs, none of them actually regenerate that tissue. There's only like lower species like the axolotl that have a capacity to basically bridge that gap that is being created in the brain. And it takes about a year for them to repair that kind of damage. So we started to look in terms of endogenous regeneration, in terms of trying to supplement a scaffold in that cavity that would allow the host cells to basically continue invading and integrating in a tissue, replacing the material, and then gradually depositing a new extracellular matrix and creating a new tissue. The other thing that we're started to explore, but I haven't really worked on for a while now, is in terms of transplanting neural stem cells and endothelial cells together in a co-transplant at a high density with some of this scaffold, and then we can achieve, like here, you can see kind of morphogenesis that happens when we're putting these two types of cells together, and they also create kind of a primitive tissue in that lesion cavity. What was the impetus in terms of starting this work? We really started out in terms of
thinking about other organ systems and what is being done in terms of repairing those. Steve Badalek, a collaborator of us at the University of Pittsburgh, he developed in the late 80s SIF, intestinal mucosa, derived bioscaffolds where they basically took the tissue, removed the cells, and then implanted that. And what they found is that that induced an inductive response where macrophages started to invade, they degraded the material, and as they were doing that, they were attracting other cells in that were from the host organ where this was implanted, and then gradually replaced, with the effect that this is now used in bladder surgery and damage. It's used in breast reconstruction, hernia. About 10 million people have now received these extracellular matrix bioscaffolds, and there's many companies out there that produce it. Mostly it's derived from pig, and the reason for that is because you can define the age when the subject is physically culled. It's easy in terms of procurement, in terms of getting through the process, versus human tissue. With human tissue, you might have the risk in terms of prion disease being transmitted or other kind of disease like Alzheimer's disease, because those proteins you will not remove from the extracellular matrix as such. So we started out with that and kind of we're applying perturbation theory in the sense that approximate solutions can be found by identifying solutions for related problems. So we essentially looked at what happens in the periphery in terms of soft organs, soft tissue replacement, and can we apply the same principle to the brain? And the first issue is really delivery. As you know, in terms of the brain is encased in the skull, and didn't think in terms of getting this in intra-arterially. So delivery is an issue. Structural support is what you need in terms of bridging that gap. You need inductive signals in terms of attracting cells in. The scaffold needs to degrade. You don't want it to be there all the time because it takes the space that the cell should be. You need vascularization, because if you don't have vascularization, things will die again, and we've done that experience. You needed a guided differentiation. What kind of cells do we need in that area of the brain? And different areas of the brain need different differentiation. We need to reduce the scarring, exogenesis in terms of connecting the new tissue with the what we call vascular tissue. And then eventually you need something that we think is rehabilitation in terms of training that tissue. This is different from the stem cells that we implant in some ways, in that this is really a tissue that is empty, and unless you're starting to have kind of rehabilitation and training, the synapses, they will just die away. So we're well aware of that. And for each of these, we have basically engineering strategies that we're trying to develop and apply. And each one of these perturbation parts really can be solved independently. The other thing that we're aware of really is in terms of the monitoring, that ideally in terms of making sure that these things happen and that we know that they happen over time in these subjects, we need to be able to monitor them using MR. So let's start with the delivery. When we started this work with PLGA particles, these are solid particles. We just injected them, and then in terms of like looking at the volume, and then said 20% of that volume we're going to inject, and the brain can tolerate that in terms of the space and accommodate it. And we made sure that these particles are not buoyant, that they're not sedimenting, and that worked fine, but it was not a complete filling of the lesions, and the PLGA particle degraded and then left behind a spider web in terms of tissue, big holes in it. So we started to think in terms of hydrogels. How can we deliver hydrogel to make sure that we fill up that whole cavity caused by a stroke? So we used MR that allowed us to see where the lesion is. It allowed us to measure the volume and define how much volume we need to inject. We set basically the injection point at the top of the lesion, sorry, the other way around, the injection point at the bottom of the lesion and the drain at the top of the lesion. So we use Archimedes' principle in terms of heavier, denser materials displace lighter ones. And as we're injecting this scaffold material,
it's heavier or denser than what is present there as a liquid, and it displaces it out through a drainage hole where we always have a catheter. And you can see here how that extracellular fluid is basically drained as we're injecting the material. So if we're doing that in terms of MR planning, in terms of where we're injecting, this is an image in terms of 1 day afterwards. And this is the overlay between the MR and the 1 day. So you can see we're really filling the defect with our bioscaffold here pretty narrowly. I mean, there's some errors here in terms of where we didn't completely cover, but overall we have a very good coverage. And importantly, we have a very tight interface with the brain tissue. And you need that brain interface if you want cells to invade, because if you don't have that interface, you're not going to get the cells to basically migrate across a liquid into something that you implanted. If you're doing this right, this is what you're seeing about 3 months down the line. So this was previously a hole, and we now have basically tissue that is growing within that hole. We have neurons, astrocytes, oligodendrocytes, as well as the vasculature that is forming there. But the neuron content is less than 7%. So that is at the moment an issue that we have, that we don't have enough in terms of neurons that invade, or we don't have enough neuron differentiation that is happening. So once we were happy in terms of the delivery, the next question we started to have is, why do we need to kill the animal at 1 day to see where the material is? And could we not find a way of basically visualizing the material and looking at it over time and how it changes over time? So that's when we started to think about what's in the material. It's full of a lot of proteins and molecules. And we started to ask the question in terms of, could we maybe exploit some of those for chemical exchange saturation transfer? And by doing that, finding a way of visualizing these in vivo non-invasively and monitoring what happens to them over time. We then broke down what is in that extracellular matrix, and we found that we get 2 peaks on the chemical exchange saturation transfer, one being from chondroitin sulfate and the other one for fibronectin here in black. And this was the point in terms of that we started to exploit, as the joint peak here in the ECM shows, in terms of visualizing that in vivo. This shows you what we get 1 day after we implanted the material, and this is the corresponding histology. So you can nicely see here in terms of the bulk of the material, as well as here the edge in terms of where some of it distributed. It maps up pretty nicely in that way. I should say we're using collagen 1 as a marker for the bioscaffold, because it's very high in this in the material that we're injecting versus what is present in the normal brain, and that allows us to distinguish the two. And in essence, what we're doing here with the CESS is exactly the same thing, right? So it's extracellular matrix. It's exactly the same proteins that are there, just at a much higher concentration. And if we're now looking over time, we're losing basically the signal of the extracellular matrix bioscaffold in these animals. This is group images, group maps of the distribution of the bioscaffold in 5 animals. The other thing that you're seeing, if we're injecting just vehicle, we also get a little bit of a response compared to animals that only have the MCO. And we believe that that is due to chondroitin sulfate being upregulated in a response to the vehicle injection that we're doing. So in some ways, it's useful that we can see where the material distributed and how it relates to the lesion. And it gives us some temporal aspect, but it's really insufficient in terms of monitoring the long-term presence and degradation of the material itself. By 7 days, fibronectin and chondroitin sulfate were reduced, and in the end, we attributed it to the fibronectin being lost within 7 days, and that's why we lose the signal on the test image. How does that biodegradation occur? It's essentially cells that invade, and the cells that are invade are the macrophages. You can see here in terms of the green is the bioscaffold, this is the host brain, and in red you can see the macrophages. They kind of invade along path into the material,
and they are the main cause in terms of degradation. If you ablate macrophages, you will not get degradation in peripheral tissue. So that way we know the mode of action for the biodegradation is macrophages. And that led us now to the next question in terms of could we potentially monitor this invasion of macrophages and relate that to the biodegradation of the material that we're seeing. For this, we injected a fluorine-based MRI contrast agent through the tail vein and getting taken up by cells in the bloodstream. We looked here in terms of how many cells in the bloodstream were labeled with a red version of that fluorine MR agent, and it's about 9%. We're now doing effects analysis just of that. You can see it's about 50-50 in terms of neutrophils and macrophages that are tagged using this approach, and about 5% are lymphocytes. If we're now looking in terms of visualizing that PFT compound using MR, we previously used the rare sequence, but others have used all these other sequences. And as we wanted to really maximize our sensitivity and specificity for the compound, we really put a lot of effort into comparing all these different sequences and optimizing them, looking at SNR in terms of how much SNR we get in each. And FISP was really the one that will now, if you're only doing like 5 slices as a coverage. When you're now doing 20, 30 slices, rare starts to be a front runner in terms of getting sufficient signal. The other thing that is typically omitted in these studies is really in terms of the separation between hotspots. So Jeff, I'm not sure if he's here, Jeff Bolton, he used to term this hotspot imaging. And the question is, if you have 2 hotspots close to each other, how big do these hotspots need to be and how far do they need to be apart that you can tell them apart? And that's what we did here with point spread function. We also optimized that in terms of imaging sequence. So once all that background work was done, we went ahead in vivo, and we're now looking at an animal prior to the implantation. You can see all these red spots here. That's the blood vessels that are filled with our fluorine compound. And that gives us confidence that we really injected the compound and it's present, available in the bloodstream. But you can also see that there's no response. This is 24 hours after injection. No response in the stroke lesion. And this is 2 weeks after the animal had a stroke. So we no longer have peripheral macrophages being recruited into the stroke lesion. But when we now implant that ECM scaffold into that lesion, this is 1 day after that implantation, you now can see a major influx of cells into that region. This is just to show anterior posterior. So we really get the spatial distribution of these cells through the material, but not just through the material, also around the material. And remember, as we're implanting this material, there's no blood vessels in the material. So how do the cells invade the material is really through the peri-infarct tissue. And that's how they get recruited. So this is just showing when we now delineate the cavity, we can look at that signal and we can compare that to the peri-infarct signal. And that tells us this is kind of the roots, how these macrophages invade into the brain tissue and then find their way into the scaffold itself. We then did histology. So this is the MR image, just the 19F of the MR. And then this is the fluorescent part of the PFT compound that we imaged the same slide using histology, which has made it white so that we can overlay the two. And you can see a pretty nice correspondence in terms of where the 19F MR signal is versus where the 19F, I should say the PFT, is found histologically. This is just in terms of looking at the overlay of other histological markers. And you can see here in terms of the ring of fire where the cells start to invade into the material. And you see the same thing around here. So very few cells in this case that you're seeing inside the material, but you mostly see them sitting all the way around, corresponding to what we're seeing on the MR. So that lets me to conclude that we think that imaging is an integral part of regenerative medicine.
in not just in terms of selecting patients, but really in terms of guiding where things need to go and how much of it needs to go where, as well as then eventually monitoring it. We think that bioscaffolds offer a new opportunity to promote restoration and potentially regeneration of brain tissue. And this example is stroke, but the same can apply to GBM or TBI. And we think that 19F might be an underused technique in terms of really looking at the invasion of immune cells into the brain in different paradigms. We've used it for stem cell tagging, and that's much more challenging. Piotr also knows, but with the 19F in terms of macrophages, we start to get a much better signal. And so at that point, I'd just like to thank Harman Guman, who did most of this work, as well as Rima Azar, who's my current PhD student, who's driving forward these projects, and then all these generous funding agencies that supported us during the years. Thank you.
Okay, thank you so much, Dr. Mora. I think now we only have time for one quick question.
Great, thank you. Great presentation, Michelle. This is fantastic. I really like the histology and everything. I seem to understand those macrophages that you saw. Are they? Do you think it's a positive immune reaction? It's an M2. Do you think they have some kind of beneficial effect? And do you think the material may have some inflammatory may induce some inflammation? And whether you did any behavioral analysis of this?
Yeah. So so the immune response is part of it. So if you don't get an immune response, you're not going to get any restoration of tissue. We published last year in Acta Biomaterialia in terms of the characterization of those macrophages. We're pretty sure in terms of what we're seeing on the 19F is macrophages rather than microglia, because they get tagged peripherally and the microglia don't. And at this early time point, we really just see macrophages. And they're mostly of an M1 type. And so as you go on by 14 days, there's a switch over that you start to get mostly the M2 type. And that switch over is essential in terms of restoring tissue. So the M1 seems to be important in terms of degrading the bioscaffold and secreting things that attract cells in, but the M2 polarization is an essential element in terms of actually restoring the tissue. We've done behavior, and we published that 2 years ago on, I didn't go into details about the scaffold hydrogel, that there's different concentrations, and that conveys different stiffness. If you have a very stiff material, we don't get degradation, and when that happens, we don't get a tissue restoration, and we don't get behavior. So we're now in the stage of where we want to try the softer gel that we get tissue restoration, and then we suspect that we get some behavioral effect, but they might take much longer than what we've seen with the stem cell.
Great, let's thank Dr. Moto again. Our next speaker is Dr. Ruman Raman from the University of Nottingham, and he will talk to us about a neurosurgically applied thermosensitive paste for the delivery of brain tumor chemo and nanotherapies.
Thank you very much, Jordan. If I was asked what would prepare this audience best for this topic, it certainly would have been a dynamic talk that Professor Henry Brem gave earlier on. So I'm going to briefly tell you about a technology which is aim to neurosurgically deliver a thermosensitive paste for the treatment of glioblastoma. And I will mainly talk about some recently published work delivering etoposide and temozolomide for a combination therapy using this thermosensitive paste. And I'll also touch on a study that's unpublished but just concluded, delivering the radiosensitizer or olaparib. A lot of interest in olaparib worldwide, and some ongoing GBM clinical trials. And then at the very end, with just one slide each, I'll tell you about 2 PhD students in my laboratory who are incorporating nanotherapeutics into this microparticulate local delivery system. So Professor Brem beautifully outlined, glioblastoma has seen a very dismal prognosis that has only moderately improved over several decades. Incidence rates the same worldwide. If you look at the survival curve, the orange curve are those patients who are fit and healthy enough to have multimodal therapy, i.e. aggressive surgery, followed 3-4 weeks later by an intense course of radiotherapy chemotherapy. And if you are fit enough to have that multimodal treatment, the median survival is approximately 14 months. But what Professor Brem's research over the years shown is at least a proof of concept for intracavity mediated drug delivery. So as he's shown, this is an image of Cleardel wafers post-surgery. Neurosurgeon will pack 6 to 8 of these wafers around the cavity. That's an image that it's rather rare to see kind of quite a nice concave cavity for glioblastoma. Those of you who've attended theatre will know that the glioblastoma cavity is extremely irregular shaped. So anyway, the Cleardel is it's proof of concept for this mode of delivery. The survival curve there shows you why Cleardel was approved. It gives approximately a 2-month survival benefit for a subset of patients. But of course, that is not tremendously great. There's a huge therapy window to improve on that. So we based this as a success story to try and build on a technology that kind of overcomes some of the limitations of Cleardel. Cleardel is a pre-formed wafer that it has got the drug carmustine impregnated. It can't deliver. It's a monotherapy only, and it doesn't conform to the irregular shaped cavity wall. So we wanted to build on this success. So I'll just show you a schematic of our technology, and then I'll show you a video ex vivo using a sheep brain. So this is a copolymer called polylactic co-glycolic acid polyethylene glycol, called PLGA PEG for the rest of this talk. It was originally developed for a different application for bone regeneration in my institution, and we saw an opportunity to try and tweak this for delivery of chemotherapy for neurosurgery. So if I showed you PLGA PEG here right now, it would be a free-flowing powder. If you mix multiple chemotherapy drugs in saline or water, it forms a paste at room temperature, very much of the consistency of toothpaste or putty. It's been fine-tuned to sinter or solidify at body temperature only, so the microparticles fuse only at 37 degrees, and it does so within 10-15 minutes. And then finally, this sintered material then holds the chemotherapy in place, and in principle, it will diffuse out and hopefully reach the infiltrative residual disease for glioblastoma. And this is what it looks like. And so our hypothesis was that PLGA PEG can deliver sustained and efficacious doses of multiple chemotherapies for local administration. And this is what it looks in practice. So this is our neurosurgeon. This is a cadaver sheep brain. This is the polymer as a paste. And this is just to show you the ease of use. So this is the PLGA PEG paste containing 2 chemotherapy agents, temozolomide, which is a monotherapy for glioblastoma, and a topoisomerase inhibitor, etoposide. And it's just showing that this is the pseudoresection cavity there, and the relative ease of applying this paste. So if you contrast this to the pre-formed solid wafer that is Cleardel, and on the right, the same sheep brain, after about 10-15 minutes, the material has sintered. And this is just to show you that it's retained the shape of the resection cavity. And this material has been fine-tuned to completely biodegrade within about 2 months. So some of the drug release initially is based on a rapid burst release, and then remaining drug will be degradation dependent. So this was the very early stage of the project many years ago. We were just ticking the boxes for clinical utility. This is the same sheep brain taken to an MRI and CT scanner just to ensure that the signal from the PLGA PEG polymer does not interfere with normal brain. So you can see in both images, it delineates the polymer from normal brain signal. And finally, because we're targeting glioblastoma and most of our patients will have an intense course of radiotherapy, we want to ensure that a clinically relevant intense course of radiotherapy does not disintegrate the polymer. This strange-looking dummy here on the left is called an anthropomorphic phantom, which radiologists use for various protocols. And you can see here we gave the we made PLJ-PEG matrices and stuffed it into the brain region of this dummy, and we gave it a 6-week course of radiotherapy. And the electron microscopy images on the right there show you that there's no discernible difference between radiation and non-radiation. So there's no reason for us to think that radiation would cause disintegration of the material and subsequently drug release. Okay, and then the final in vitro work is just to show that we can release temozolomide etoposide. We got about approximately 1 week temozolomide release, about 3 weeks etoposide release, and as you can see here, there is a burst release, and our intention was that is desirable rather than have a very slow, prolonged period of drug release, because we felt that at time zero, at the end of surgery, that is the time where glioblastoma will be relatively least infiltrative. So we wanted a burst release. And then we showed against a panel of glioblastoma cell lines that the GBM was very sensitive to etoposide, and this includes patient-derived cell lines we isolated from the infiltrative margin. Temozolomide much less so, but again, that mimics the clinical scenario. But I will note that the cell line that we used for the in vivo studies I'll show you was very sensitive to temozolomide as well. And then in terms of tolerability and safety, initially, this is what it looks like in a high-grade glioma rat model. On the left is the surgical resection cavity. Neurosurgeon has carefully mimicked the human scenario by removing bulk tumor, but ensuring there is residual disease. And on the right, you can see the polymer is lined the cavity with, in this case, temozolomide and etoposide. And initially, the safety study, we used 2 doses that we'd optimized originally in subcutaneous xenograft, and this shows just that both doses of the combination was tolerated by the animals as judged by the lack of weight loss. And then, so the most important therapy study that you can see, we have been collaborating with Professor Brennan, Dr. Becky Tyler's group here at Hopkins for a number of years. And this was a summary of a comprehensive in vivo study. We felt that this model, for a number of reasons, was the best test bed, not least because it's the only in vivo model that has led to a clinical product and drug delivery, but also, as you can see here with the control animals, it's particularly aggressive. The no treatment animals succumb within about 2 weeks, and even the animals that are mimicking the human standard of care, so surgery, radiotherapy, oral temozolomide, within 35 days or so, all the animals have been sacrificed. So it's extremely tough test bed to test your intervention. And as you can see, we showed a significant survival benefit with PLJ surgery, PLJ PEG with both drugs, which is potentiated by radiotherapy as well. And that day 120, the relatively arbitrary cutoff that Professor Brenn's group had used over several years. And it's just been published in the cancer research. Just to ensure that those brains are relatively disease-free, we got them shipped back to the UK. As you can see here, the no treatment animals and the animals with oral temozolomide, you can see with the H&E staining that at the point of sacrifice, the huge tumor burden going back into the section margin. But in both the PLJ PEG with both drugs and with radiotherapy, you can see that there's no evidence of disease. So this is some unpublished work now that we've just concluded again here at Hopkins. We definitely see the PLJ PEG as a platform technology to really link into our molecular and neuro-oncology work. And as Professor Brennan said, the most important thing really now is to have rational design of agents. But at this stage, it's the feasibility of the technology. It's the bonus that we've seen a survival benefit in those 2 types of agents. We turn to olaparib because there's a number of clinical trials, one in the UK, one in France, where olaparib is approved for ovarian cancer. It's a PARP inhibitor, and it's shown phase 1 trials are finished for glioblastoma, and a phase 2 trial in Lyon has just begun. There's a lot of interest in olaparib, and we figured, and this is of course for systemic olaparib delivery. So we reasoned because of the dose-limiting toxicities, like for systemic delivery, could we try and deliver olaparib using PLJ PEG? And this time we took a slightly different approach where we tapped into other data in the laboratory to try and demonstrate the clinical rationale for targeting olaparib. So it's a PARP inhibitor which can be measured by spector AIF, which is apoptosis-inducing factor. And this is, we turned to some RNA-seq data from 10 GBM samples in our group. This is an unrelated study where our neurosurgeons use 5-ALA-guided fluorescence-guided surgery, and we're very interested in purifying the fluorescent cells from the infiltrated margins, because for glioblastoma's history, we've done very well at studying the molecular biology of what is taken out, but we have underappreciated the degree of heterogeneity, the intratumor heterogeneity. We've not really tried to consider what is left behind in the patient. In this diagram at the bottom, you can see the core rim regions of the central enhanced region of the tumor. We took invasive tissue and then used fluorescent activated cell sorting to separate the infiltrative from non-infiltrative. This was important here to show that the AIF is the effector of POP. It's significantly enhanced in the FACS-positive infiltrative cells. So this was an early indication that olaparib would be a good agent because of the high expression of AIF in I think 10 GBM patients. So this study, as I said, it concluded just last week, and this is a neurosurgical trainee and Professor Brem's lab with Sarah, and this is the work he conducted initially just to show that we do get drug release from in vitro from PLJ-PEG. Ricardo tried to decouple whether olaparib had any cytotoxic from anti-proliferation from radiosensitization, and you can see here the radiotherapy alone actually didn't impair proliferation very much, but radiotherapy with olaparib certainly showed a significant impairment. Similarly, in a clonogenic assay, we showed that olaparib leads to potentiates radiotherapy, certainly with respect to impaired clonogenic growth. And finally, Ricardo showed that this effect was due to apoptosis. Again, most importantly, what happens in the orthotopic study, and this is what was just concluded. And this is quite intriguing because the early arms here, you can see here the blue arm here is the surgery and intraperitoneal olaparib. So this is really mimicking the ongoing clinical trial, although it's intraperitoneal rather than oral. And you can see here that it's only marginally beneficial compared to untreated animals, whereas we were very excited to see that the PLJ-PEG delivered olaparib certainly potentiates radiotherapy, where we have long-term survivors only in those arms. So this is data just concluded, so we haven't got these brains back to analyze. And just one thing to say, I mean, Professor Brand made a very compelling story in how to realistically try and translate research from that endpoint to clinical trials in humans. This is what we are at the moment trying to develop as a translational grant bid in the UK. With discussions with the UK regulatory board, we tried to convince them that this would go through as a device with an ancillary medicinal substance, but they felt that it would have to go through as a drug, as Leodel did, which is a harder regulatory obstacle. This is what we envisage. This is the kit in theatre. The neurosurgeon will open it. One syringe would have the predetermined volume of PLJ-PEG and the two drugs, temozolomide and etoposide. Second syringe would have the predetermined volume of saline, and only at the point of mixing prior to administration will it form the paste. Okay. Finally, just one slide each for to the nanotherapy work going on in my group. This is PhD student of mine, Catherine Beatty. And the idea really is there's a huge, a lot of interest in the nanofield in glioblastoma. By and large, it is systemic delivery. And we thought we've got this kind of platform technology. Can we incorporate the nano into this micro local delivery system? So what Catherine is doing is she's trying to functionalize. She's using some functional chemistry, using techniques called ring opening polymerization, where she can add certain responsive linkers so that in a pH sensitive manner or a hypoxic sensitive manner, she can deliver certain drugs that are conjugated. And the idea is that once the chemistry is developed, she's going to incorporate into the PLJ-PEG paste. So that's how it is different from the majority of existing work. And my final slide is a second PhD student in my group, B.B. McCrory. And there's a question asked at the webinar about drug penetration using these kind of intracavity systems. this is an approach where we thought we would introduce pressure as a variable and use an airbrush style design, but have mechanical engineers make this bespoke for glioblastoma research. At the outset of the project, it was quite a high-risk project, but we got the neurosurgeons involved, and this very basic schematic is based on safety concerns in theatre that you wouldn't have chemotherapeutic mist that would be injected and exposed to theatre staff. So you'd have a funnel at the end that would clean up any excess chemotherapy. But the idea is that this would be a sprayable device that would spray a bioadhesive gel containing nanoparticles with the drug inside. And the gel we're using is pectin. Both these studies are in the middle stages of PhD, and we hope to conclude with in vivo studies in year 3. Okay, and so mainly I'll thank various members of my group. At the back, tall guy is the academic neurosurgeon who conducted all the surgery in Professor Brem's lab. And of course, the key collaborators are those here in Hopkins and Professor Brem's lab. Thank you.
Great talk, and we have time for a question.
Thank you. It was a very nice talk. I want to just come back a few slides when you were showing the syringe when you are actually making the gel. Don't you produce like some sort of micro bubbles when you are, you know, pushing the syringe from both sides?
Yeah, I didn't clarify what we haven't developed this yet. We're going to do the rodent study. It's rather messy. We have we use a wave boat and
Okay, the next speaker is Dr. Miroslaw from University of Otago. He is going to present clipping the wings, cancer stem cells, and the challenges of image-guided therapy of glioblastoma. Let's welcome Dr. Miroslaw.
Thank you very much for introduction. Thank you to organizers and here for a very kind invitation. It's a great privilege to be here.
And I'm going to get you through some of the work I performed in my lab over the years, focused on the brain to stem cells, and touch upon the problems we encountered and some solutions with image-guided therapy in glioblastoma using or label-free techniques in order to appreciate the therapy efficacy and interaction between the tumor and brain. So as we heard today many times, despite some reasonable progress in the therapy of glioblastomas, the overall prognosis is still relatively dismal. And the reason for that might be that we are actually missing the exact biological background of the disease. We don't really know what is the origin of the tumor. We don't really know what is the exact mechanism of the therapy resistance and how it all relates to the overall microenvironment of the brain. So the great, and I think one of the most important progresses over the last years, actually 10 years ago, was the hypothesis written out that there is a certain population of the cells within the brain tumor which resemble very closely some characteristics of neural stem. They are gathered within the brainstem niche. They are interacting with the extracellular matrix. They are controlled by very similar extra and intrinsic cues like hypoxia or some signaling pathways. And these cells can be identified prospectively within the tumor based on the presence of surface markers. We can isolate the cells based on CD133 expression, specificity, and so on. And if we study these cells in vitro, we can show that they have real tumor initiation and progression capacity with self-renewal, with sustained proliferative capacity, with angiogenic potential, and so on, in the radioresistance and immunosuppression. So there are different ways. Well, obviously, this cell population is designed for being targeted during the therapy, and possibly the brain tumor sample target therapy is the way to combat this disease. And there are many different ways to approach this. And you can see here, we can directly destroy the cells. We can try to differentiate, as Professor Bram said, and this was actually a very seminal paper about BMP4 and glioblastoma stem cells. We can also target the niche of those cells in order to let them die, let them succumb, and basically, possibly the combination of all those routes can give us some success. In my work, I was concentrating on the direct destruction of those cells, which can be again performed in a very different way. So we can target the surface markers, isolate, and to specifically target those cells. You can target the mechanism of resistance against the therapy. You can target the microenvironment. What I was interested in was the targeting the signaling cascades, developmentally important cascades such as notch, wind, and so on. In fact, paraphrasing Asian trauma always leads to Baltimore and to Johns Hopkins. Actually, the idea of targeting wind in the signaling pathway came through here while I was doing my research scholarship some years ago, and we were concentrating in the lab of Charles Eberhard. We're concentrating at the time at the one part of the wind pathway, which is the canonical wind pattern pathway. In this part of the pathway, the signal is produced by the binding of the wind molecule to the transmembrane receptor, and then it disengages, so to say, the inhibitory complex, which then allows the accumulation of beta-catenin intracellularly, which is then transported to the nucleus and initiate the description of the downstream gene. So we took advantage of the model which was created here at Hopkins, concentration of the beta-catenin gene, which does not allow the ubiquitination of the beta-catenin and capture of the protein from the cytosol. As you can see, this introduction of this mutation led to the accumulation of beta-catenin in the nucleus and activation of the pathway, confirmed also with reporter assays. So first we wanted to have a look whether there is any phenotype of this modification. We assess different characteristics of tumor cells, viability, proliferation, it was not affected, but to our surprise, the mobility of the cells is very much affected. As you can see here in a very simple experiment, the transfer migration assay, that the modified cells migrated much faster than the non-modified counterparts. And if we started to think what would be the molecular mechanism for that, we came across of the phenomenon of reprogramming phenomenon of cells, which occurs actually mostly in epithelial tissue, which is EMT, epithelial to mesenchymal transition. It is driven by many different cues and regulated by intrinsic transcription factors inducers of the process. And we had a look at our model. We found out that exactly these players, like the plant, trees, and snail, are upregulated upon the constitutive activation of the beta-catenin pathway in our tumor cells. So this is very simplified graph showing how the EMT process might be regulated. I'm not going to go into details. As you can see that these master regulators play an actually central role in that. All of this leads to increased motility of the cells, more pronounced like the signature chemioreactive resistance, and ultimately to support the node modification. So we started to look for the way to inhibit this pathway, inhibit Wnt activity, and came across a novel at the time inhibitor, which is called LGK974, very expressive name, which is actually porcupine inhibitor. Porcupine is an enzyme controlling Wnt molecule before being released to the intracellular space. So by inhibiting this enzyme, we prevented the release of Wnt. We prevented the induction of the signal down to the effector cell. As you can see, this led to the decrease of the viability of the cells, proliferation of the cells, and which was the most important finding of this study, it affected specifically stem cell compartments. As you can see here, we have the diminution of decrease of the percentage of stem-like cells in our culture, time-dependent and dose-dependent, and also in functional assays, our cultures were not able to give rise to colonies anymore in homogeneity assays, as you can see here. And at the same time, we increased the maturity of the cultures, as you can see here, with increased expression of mature neuronal and glial markers. As we heard many times during this conference, one compound is not going to do the job. And being driven by this idea, we combined the LGK, the porcupine inhibitor, with temozolomide, and especially as we had a look at the MGMT wild type cultures, we found out that there is a synergy, which may be potentially in the future a way to overcome the resistance towards temozolomide in this patient. As we had a look on the possible molecular mechanism of this synergy, we found out that there are a number of genes differentially regulated in the cultures treated with both of the compounds, with RDH3A1 aimed for diminution of the gene, which is actually member of the family of genes or proteins responsible for resistance against chemotherapy. The transporter protein, which is exhaling, noxious substances from the cell, and this was significantly downregulated upon the treatment with porcupine inhibitor, which probably leads to better response to temozolomide. We have performed some experiments with aiming at inhibition of the expression, using also CRISPR gene editing, and we found out that the response of these cells upon the inhibition of LDH was much better towards the temozolomide, also leading to the increased recombinationity of our culture. So the conclusion was that AMT, it was actually not really clear, not really known in the field. AMT plays a role also in glial tumors, and it's quite a significant mechanism regulating the aggressiveness of the GBM, being governed both by intrinsic, like Wnt, but also extrinsic cues. We have repeated this experiment also in hypoxia, showing hypoxia-induced activation of the AMT program. And we could find some or identify some compounds which could be used in order to reverse this activation of the AMT program. In the prospect, I mean, we are now in the phase of in vivo studies. In the prospect, it all should lead to the change of the therapeutic paradigm from what I learned as a resident of neurosurgery, where biopsy sample gives just the standard pathological diagnosis, and everybody gets anyway the same therapy. To what is now available, some rudimentary molecular diagnosis, like for example MGMT status, IDH status, or one P92 deletion, to truly tailor patient-specific therapy based on molecular diagnosis and pharmacogenomics to see what is the best compound which is going to work in the patient. But we have, of course, very significant problems with that. First is the intratumoral heterogeneity. We know that what we call glioblastoma is not a uniform disease. There are subtypes, there are different forms of the tumor being characterized by completely different expression profiles and responding most probably to very different therapies. This is not only just expression, these tumors have also very different prognosis with mesenchymal subtype, and you can imagine mesenchymal subtype is associated with Wnt activity being the most aggressive one. But even more problematic is the intratumoral heterogeneity. So we don't only have differences between patients, but within one tumor, we have compartments of different origin, of different character. And this is something which is very difficult to be addressed in our therapeutic regime. It would require the application of many different compounds being specific for different subtypes of cells present in the tumor. So we ask the question, how can we find a way to visualize or to get some information without contrast in basically real time during the surgery about the molecular composition of the tumor, and maybe predict the response of the tumor towards different compounds. So we thought that the best way to do so would be the Raman spectroscopy, which is actually very old and very well established method. So what we are looking at is the Raman spectra, scattering spectra, which are going to be analyzed through the detector, which are going to tell us the shift or show us the shift of the illuminated light and give us information about the matter we are going to examine. So it's not a new concept. We were not the first who thought about the Raman spectroscopy in terms or in the setting of brain surgery. In a couple of seminal works from Montreal group, they have already shown that this is possible to design probe, which is going to be used in intraoperative setting. And with this probe, they were able to distinguish between brain and tumor. The differences are not very huge, as you can see, but with repetitive measurement with a lot of data, it is possible with very high accuracy, actually, to distinguish between tumor cell and the brain, surrounding brain tissue. It is also possible with this technology to see how far the tumor cells migrate from the edge of the tumor. As you can see, with within the 4 centimeters from the edge, visible edge of the tumor, the cells could be decoded with the Raman spectroscopy. This technology could also be augmented by the use of nanoparticles. It's a very interesting approach where basically signal-to-noise ratio in the imaging with Raman spectroscopy could be augmented using nanoparticles equipped with Raman access layer. You can also attach in this very nice paper from Nature Medicine 2012. You can also attach the gadolinium to that, and in this case, we have 3 potent enhancer of the imaging study. As you can see, it enhances the MRI, acoustic, and Raman image. All of those images correlate with each other very well, and in fact, pathological analysis show that this is attributable to nanoparticles. The edge of the tumor corresponds very well to the Raman microscopy with the presence of the functionalized nanoparticles. It could be used also to monitor the extent of resection, and as you can see, there is a huge, very amazing spatial specificity of this image, being able to detect very small pieces of remaining tumor. You can also functionalize this nanoparticles better and try to perform real molecular diagnostics. So it's shown here for the breast cancer, if the nanoparticle with Raman reporter is going to be equipped with targeted antibodies against either EGFR or HER2, it is possible with this imaging to show different subgroups, multiple subgroups of the tumor. We were interested in a bit different approach. We thought that it is important also to see what is going on the interplay in the layer between tumor and brain tissue, due to the fact that we know that EMT, the one expression, drives also modulation of immune response towards tumor. It's shown sometimes that the EMT process gives a kind of energy of the immune system around the tumor. So our question was actually in the advent of immune therapy, is it possible to predict the process whether the tumor is immunogenic or not, and whether it's worth to apply, for example, the PD-1 inhibitor. So some work has already been done in this field. It is possible to distinguish between active and naive T cells with Raman spectroscopy. We have also performed some preliminary data on that, being able to distinguish between treated and non-treated tumor. In this case, we treated the cell culture with notch inhibitor, showing quite different spectra, which could be analyzed also statistically. And just recently, using an excellent expertise of our collaborators from the Otago University and beautiful device, confocal Raman spectroscope, we were able to distinguish anti-tumorigenic and pro-tumorigenic monocytes, as well as differences in monocytic response to tumor conditioned media. So this is just the framework of our interest currently, with the objective to answer the question whether EMT drives the immunosuppression of the GBM, whether we can non-invasively identify GBM-mediated T-cell activation with Raman technology, and whether the targeting of EMT increase the efficiency of therapy with immune checkpoint blockers. So these are the packages of the project we are planning at the moment. Those in red are already performed, already accomplished. So we are now at the first stages of Raman spectroscopy to detect glioma-mediated immune cells. So we are creating a library of spectra with human glioma cell cultures and also synthetic iPS-derived transcriptional subtypes. We create also a library of immune spectra of different cellular immune components to be able to use it in a deep learning algorithm for in vivo application. Well, the scope is going to be to produce or design a device which we can use during the surgery on the fly to say assess the molecular composition of our tumor and the immune response of surrounding brain tissue. This work was, of course, teamwork with many different groups involved. Thank you very much for your attention.
Okay. Thank you so much, Dr. Mashachik. Let me have time for a quick question. Any question?
A very quick question about cultures of the glioma cells, and what experience do you have with cultures of lower grade, not GBM?
Yeah. So unfortunately, it's very complicated topic. There are no, to my knowledge, no stable cell lines available, and very few primary lines, in the field we can look for. But I think that the immortalization of those cell lines would be one of the ways to carry on.
Excellent talk, Jarek, and I really enjoyed it. But I have a question regarding your Raman spectroscopy.
Yeah.
What's the depth of the tissue penetration?
Yeah, that's why we think that we need a probe which is going to penetrate into the brain several millimeters, which is not going to, it's not very problematic during the intraoperative setting. But in fact, it's very long at the moment.
Thank you. All right. And so our next speaker would be Dr. Khulud Al-Jamal from King's College London. Oh, or okay, yeah. So we're going to switch a talk around due to the timing. And so we're going to hear from Symposium 8 Focus Ultrasound. We're going to hear from Dr. Costa Cervantes from Georgia Institute of Technology, and he'll talk about controlled drug delivery and release to brain tumors with focus ultrasound. Hello?
Okay, sorry for the change in the plans, but have to catch a flight relatively soon. So first of all, I'd like to thank for the organizers for the opportunity to present our work on focused ultrasound control drug delivery and release. I will talk about both primary and metastatic brain tumors, and I guess I can try to save some time as well. So there is no need to introduce or talk about the challenges that we face in delivering drugs into the brain, and the primary and the role that blood-brain barrier has in this challenge. I'd just like to point out that although blood-brain barrier is considered compromised in many tumors, this is not the case for all the tumor subtypes, and there are some examples in medulloblastoma tumors. And also it's highly heterogeneous, which means that there is the penetration of the drug across the blood-brain barrier is completely not uniform, and that doesn't allow significant amounts of drug to enter the brain parenchyma. So focused ultrasound has been around for some time, and we and others have shown that can disrupt the blood-brain barrier. Summarizing the data from the past 10 years, we found that there is a four-fold increase in the delivery across a range of nanoparticles and therapeutics, including chemotherapy and other drugs. And also this led to a 3- to 4-fold increase in the median survival time across a number of tumor models, which essentially justified the clinical trials that started around the world and trying to test this technology first to assess its safety and then assess its efficacy. And I think to some extent the safety has been addressed and has been shown both in humans and in many animals that it is safe. However, the big question I think that we'll face pretty soon as we move forward towards the phase 3 clinical trial will be like, well, is this technology effective? And I think one question that's quite important is what are the physical, or if there are physical and chemical properties of anti-cancer agents that when combined with technology will lead to maximum drug penetration and subsequently to optimum or maximum drug uptake by cancers. And this is my talk today about, I will talk about the experimental and computational framework that we developed to address this question, and also talk about the therapeutic strategy that came out of this approach, as well as the technology that we developed to implement this and test these approaches. So first, I'll talk about our research in brain tumors, also breast-brain metastasis. Although brain metastasis are encapsulated tumors, there are several metastatic seeds and foci around the tumor, and all of them have quite heterogeneous permeability. So there is a good justification for disrupting the blood-brain barrier using this technology. So in order to understand the pharmacokinetics of the chemotherapeutic agent doxorubicin, we employed intravital microscopy, and we tried to see how this technology really changes the different transport properties of this chemotherapeutic agent, with the first-line treatment for the primary brain tumor. So what intravital microscopy revealed that after we apply focused ultrasound, we were able to see a 7-fold increase in the improvement of the extravasation of this chemotherapeutic agent. And interestingly, we also found a 5-fold increase in the penetration of this chemotherapeutic agent. These are like profound changes in the pharmacokinetics of the drug in the tumor microenvironment. So the further analysis of the data, which was quite surprising and quite fascinating for us, shows that when we analyze the profile of the drug as it extravasates as a function of time, we found that the profile resembles more convective transport as opposed to diffusive transport, and that was quite exciting. So we wanted to further understand and dig deeper into that observation. So we built a mathematical modeling that describes the primary components of the tumor microenvironment, and again we confirmed that there is a 3- to 4-fold increase in the convective transport, and essentially this suggests that when we disrupt this data, so that when we disrupt the blood-brain barrier, we move from diffusive-dominated transport towards convective transport. And also, as you can see here, this data also confirmed the changes in the blood-brain barrier permeability, which was again of the order of 3- to 4-fold. The good thing of having a validated mathematical modeling describing the tumor microenvironment is that you can do a number of experiments. It's a very useful tool in studying how tumor microenvironment influences drug pharmacokinetics and penetration. And in this respect, what we did is we built a model that has the physical parameters that we extract during the optimization process of the model. And then we studied tumor heterogeneity and other parameters such as the permeability of the blood-brain barrier, and all other parameters, including the cell, the transmembrane cell transport. So what the first thing that we found, as you can see here, we found that ultrasound essentially eliminates or overcomes completely all the transport barriers that are imposed by the tumor microenvironment, including the blood-brain barrier. The second find that we found is that as soon as you overcome all the transport barriers, including the blood-brain barrier and interstitial space, then the dominant or the rate-limiting factor becomes how fast the drug can move from the interstitial space into the cellular compartment. And this suggests that for this small drug is quite significant, because as soon as we increase the transport and we go from the diffusion to convection, the drug essentially is flushed out from the tumor microenvironment. And in order to address this problem, we start thinking what strategies can be employed. And I think people have already found strategies to address this challenge. And this, as this data suggests, if we instead of using a bolus administration, we go to slow infusion, this suggests that we're going to have a substantially significant increase in the cellular uptake, which is what. So essentially, when we disrupt the blood-brain barrier, we don't have challenges related to the diffuse penetration across the blood-brain barrier. We have challenges related to cellular uptake, and we really have to think and take this into account. And slow infusion of the drug could be an answer to that. So that's the first strategy that suggests that when we combine small chemotherapeutic agents with this technology, we definitely need to employ slow infusion. What was quite interesting, though, as we analyzed the data, we found that essentially the blood-brain barrier or the extravasation across the blood-brain barrier is optimum for a very finite window of 4 diameter. What the data essentially suggests that the more we disrupt the blood-brain barrier is not necessarily the better. So we really need to identify ways so we can disrupt the blood-brain barrier with things like 30 to 40 nanometers, which creates it provides a perfect balance between promoting convective transport versus completely reducing the transport, because you have too much leakage from the tumor microenvironment, and in this way the drug does not go through. So the question is, like, how can we optimize the blood-brain barrier porosity, which as the data show, it can be extremely important in optimizing drug transport as well. So what we have shown recently is, it turns out, we and others have shown that, well, it turns out that when we apply the ultrasound, microbubbles vibrate. And these vibrations are generate acoustic emissions. Essentially, these vibrations are echoing what the microbubbles are, what mode of vibration the microbubbles are undergoing. And this is a relatively busy slide, but what we have shown is we can do imaging, and this time is passive acoustic imaging. We can essentially record the echoes by the microbubbles, backpropagate the acoustic field, and essentially localize and characterize the type of microbubble vibration. This is extremely powerful, because we now know that if we have only harmonic emissions, if we send, for example, 1 megahertz and we start recording a 2 megahertz signal, we know that the bubbles have a weak vibration. If we increase a bit the pressure and we can start seeing ultra harmonics, which is 1.5, 2.5, and so on, of the excitation frequency, we have like stronger microbubble vibrations. So up to the point where we have broadband emissions, when you can see here this small hump, when this suggests that the microbubbles collapse. What this means in terms of like assessing and analyzing the tumor, this means like when we do not have this broadband emission, which suggests that the microbubble collapses, we can still have blood-brain barrier disruption, but as you can see, the T2 star weighted image, we don't have any tissue damage. On the other hand, if the microbubbles collapse, we do still have blood-brain barrier disruption, but at the same time, as you can see here for the hypointensity region, which indicates erythrocyte extravasation, we do have tissue damage. Therefore, now we have an imaging technique that could allow us to fine-tune the exposure parameters and obtain the desirable effect, which whether it will be like strong blood-brain barrier disruption or weak blood-brain barrier disruption. So now we just took this to the next level, and what we essentially did is because this method is extremely fast, it takes few milliseconds to reconstruct the acoustic field of the dimensions of the human brain, and we close the loop. And essentially what we can do now, we can adjust the exposure settings so we can have a specific type and mode of vibration of microbubbles. And now we were really excited about that, because that's the first controller of this nature, which allows us to essentially in real time control the microbubble dynamics inside the brain. And we were really excited to take this into the clinics and integrate that technology with the current clinical trials. We think which will be quite significant and quite important in not only achieving safe blood-brain barrier disruption, but also optimizing the blood-brain barrier disruption and also having reproducible results as we go into the challenging environment, the clinical environment. So in the second, I'd like to go back to the previous data and see how we can, by thinking and analyzing a bit more of this data, we can come up with completely new strategy to deliver drugs. So as you can see here, what was quite interesting, you can see here we have, like as I mentioned, 7-fold increase in the extravasation. However, it's quite obvious that the drug goes in and comes out. So this suggests that the fact that the drug comes out means that it has very fast clearance. So if the drug is cleared very fast from the circulation, this means that the concentration gradient and any other gradient is against us this time. So we really need to identify strategies that probably we will slow down the clearance of the drug. So we have the ability to not, so the drug can remain in the tumor for sufficient time so it can be taken up by the cell. Also in this specific example, we use doxorubicin, and doxorubicin by more than 75% is attached to the albumin. What this means, essentially, we didn't deliver a 580 Dalton drug, we delivered a 665 kilodalton drug. This suggests that probably all our findings with respect to this drug exaggerated the role of the blood-brain barrier. What does this mean? This made us think that can we, instead of using free doxorubicin, using encapsulated doxorubicin, and doxorubicin that can be, for example, encapsulated by temperature-sensitive liposomes. And not only this would allow us to, if we can release the drug only at the tumor microenvironment, this will prevent much of the doxorubicin to be taken up by albumin, and also will be, since the blood-brain barrier could be to some extent disrupted, might allow to achieve the desirable therapeutic effect without even disrupting the blood-brain barrier. This was our hypothesis based on this data. So this is for those that are not, this molecules, this temperature, low temperature sensitive liposomal doxorubicin is around for some years and is at clinical trials as well. So as soon as you hit the molecule, you have a quite substantial release of doxorubicin within few seconds, and 41 to 43 degrees Celsius is quite effective temperature. If you don't hit it, your cytotoxicity remains relatively low. If you hit it, then you have release of the drug and the cytotoxicity increases at this DL261 cell line glioblastoma model. And then also what we also were interested to see for how long do we want to hit in order to have sufficient drug uptake. And as you can see here, by incubating doxorubicin with this cell line, we see if we even hit for 10 minutes, we might have 30% cellular uptake, which suggests that if we are able to combine those molecules, those nanoparticles with the high hyperthermia applied locally in the tumor microenvironment, we might have a viable therapeutic strategy. And this is what in fact we did. I'm not talking about how the technology that we developed. I'm going to show you directly the data. So this is a real time now. We have a real time control, but this time what we have, instead of closing the loop with acoustic means, we have an MR guide focused ultrasound system. But what we do, we collect MR thermometry data in real time. We analyze the temperature at the focal region, and we adjust the power of our ultrasound so we can maintain a temperature of the order of 41.5 degrees Celsius in the brain. And this is transcranially as well. So what we found is after doing several experiments, we find quite good reproducibility and minimum to no tissue damage. Those spots that you see are from the spots that we inoculated the tumor primarily. So after we conducted this treatment, we wanted to find out what happened to the drug. So and what we observed by sacrificing the animals with this background signal, we observed that when we apply focus ultrasound plus the low temperature sensitive liposomal doxorubicin, we find almost 3.5-fold increase. We also try higher temperature to see whether there will be any additional benefit. But then I think at 42.5 degrees, because we have a small temperature gradient, there is a trade-off between potentially some tissue damage and some impulse, and so that does not allow the drug to flow through. So there is no need to go to high temperatures. 42 degrees provides provides sufficient release of the drug. So the next question is what happened at the microvascular level, which is what is the important information, because this is where we want to see whether we have penetration. So by zooming in, what we analyze the tissues further down. You can see here we stain, here doxorubicin is red and the vessel is red. What we found when we just administered the liposomal doxorubicin, we found from, as you can see here from the pink, that the drug primarily accumulated at the vessel wall. It was not able to penetrate deep into the brain tumor, into the interstitial space. And this data also, like I said, probably explain why liposomal failed in the clinical trials against brain tumors. Probably the drug stuck primarily at the vessel. Essentially, with these treatments, you might have a short-term benefit, but essentially you're doing angiogenic therapy instead of like doing essential therapy. So, but however, what we observe when we applied the focus ultrasound, we found profound increase in the penetration and the cellular uptake of the liposomal doxorubicin. This is quite exciting news for us because focus ultrasound is already in the clinics and can apply thermoablative temperatures, suggesting that this strategy could be rapidly translated in the clinics, and we are working in this direction right now. So to conclude, I have to keep it short. So ultrasound and MR-guided focus ultrasound with closed-loop methods can promote both the controlled blood-brain barrier disruption and also the control and local drug release through intact skull. This is unique advantages of this technology, and its primary characteristic is that it has different modalities that can interact with tissue and can be non-invasive. So in our results also with the breast-brain metastasis tumor suggest that it can increase the effective permeability of the blood-brain barrier. It can increase drug penetration, and we have a shift from diffusive to convective transport. And also I didn't emphasize that, but it was apparent that it had reduced drug gradients, which can be quite important for also reducing, for improving therapeutic outcomes. So with a GBM model that we apply localized hyperthermia in brain tumor safely through the scalp, and scaling up in this case might not be as challenging as it sounds, because with the mice, the focal size is really large with respect to the brain, so we touch the scalp to some extent. So when we go to human, we have much more space. And scaling up does not mean that it will be necessarily more challenging technically to implement this strategy. So and finally, the target drug release that we demonstrated and we saw with low temperature sensitive liposomal doxorubicin can both improve significantly drug penetration and cellular uptake. And with that, I would like to conclude. And you saw some pictures of the students that they did this work. As Yuton was a PhD student in the lab that worked on the mathematical modeling. Young Kim is another PhD student of the lab that did build the closed loop MR-guided focus hyperthermia, set up and analyze the data with liposomal doxorubicin. Stotson and other PhD students of the lab that worked, among others, they work on the closed loop controller with the passive acoustic pumping. And also like to thank our funding and thank you for changing the program for me. That's at my slide.
Is there a quick question?
Yeah, one quick question.
Okay, just one question. This is time.
Just hello, very nice talk. Very nice talk, Costas. You said scaling up is not going to be hard. I agree with you. I encountered the same issues about having too big of a focal zone and a small rodent. But scaling up, on the other hand, if you want to, I mean, we did a study where we tested the liposomes in a rabbit model, the DX2 tumor model. On the other hand, you do have more control of your focal zone, but on the other hand, focal zone is still then relatively small to some of these tumors that you treat. I mean, have you done any calculations on how long it would actually take to treat an entire, let's say, breast cancer metastases in the brain with a current clinical setup?
The current clinical systems are phased arrays, and what this means, you can steer the beam within a millisecond time frame and have a larger volume. So there are some strategies, but what they're doing, they're applying a spiral. They apply a spiral protocols, and in this way you don't have a single focal spot, but you can hit a larger volume and let heat diffusion to cover the entire region. I think the data are quite compelling, and to some extent they cover large volumes. Whether we'll be able to treat
any brain metastasis or a primary tumor, that's definitely a separate question, and it depends on what the size will be. Definitely the advantage of this technology is that it's non-invasive and to some extent, in great extent, focal, so probably will be more ideal for not tumors that cover half hemisphere, I would say. Those probably not the right technology for that. But tumors that are difficult to access, and it's even better the technology, the deeper you go to the brain, the performance improves as opposed to other technology. So if you have difficult to access tumors, I think this technology is ideal.
I have a very brief question. I was just wondering what happens to the toxorubicin, which is still encapsulated with this lipase when someone doesn't take to clear it from the system.
For the specific, this technology is already in clinical phase 3 clinical trials for liver cancer.
4 to 6 hours for thermidor.
In the patients, there is different.
In a mouse.
In the mouse?
In the mouse, 4 to 6 hours.
For sure, I think it has been it is well established that liposomal doxorubicin has less toxicity as compared to free doxorubicin. I think this is something that's well established. So the pharmacokinetics will be different. That's the goal, to be able to have the drug staying there for a longer time, so we can apply hyperthermia and control release. But I don't know exactly. I haven't done the measurement myself, but what Victor said is.
And also, these are similar to Doxil, but they're not nearly as pegylated. So Doxil will circulate for 24 to 48 hours. These only for a number of hours. And it's a good thing because you're not delivering them by enhanced penetration and retention. You only want them there long enough while you're treating, so you can release the drug, and actually you prefer that they clear out.
Excellent discussion. Let's thank Costas again. Up next, we have Dr. Khalil Jamal from King's College London, and she'll be talking about overcoming the blood-brain barrier using nanomedicine.
Okay, so first of all, I must say it's a very interesting meeting. So I'm a pharmaceutical scientist. I normally go to drug delivery meetings, but this is very special because it's focused on the brain. It attracts neurologists, neurosurgeons, and also other multidisciplinary scientists. So I think the outcome must be very, very interesting. So I'm going to talk to you about something different. So rather than tackling the brain from the outside, we are actually looking at bypassing the blood-brain barrier. So this is not working. Okay, so I'm going to wear the pharmaceutical scientist hat here and just talk about nanomedicine. So nanomedicine is the application of nanotechnology in medicine, whether it's diagnosing the disease or treatment or monitoring. So drug delivery, I understand it from a different aspect, because when there is drug delivery, I always think of the drug and changing the pharmacokinetic of the drug. So we have a problem with a particular pharmacological agents that we would like to use or somehow apply another carrier to take it to the site of action. So we're looking at agents that are below 100 nanometers in size, mostly because this size allows you to enter particularly every type of cells, but if they are too small, they will be excreted very quickly from the body. So you need to retain them for a particular period of time, but they are not too big to be taken by liver, spleen, and lung, and at the same time not to be excreted very quickly. So we have problems to solve. So either the drug is very water soluble or water insoluble, or they are biologically sensitive, or they cannot cross biological barriers. So in all cases, we want to pick the right nanocarriers to help them overcome this problem. So the main aim is really to achieve higher therapeutic index. So what you want to do is have high concentration at the site of action, this concentration at the off-target effect. So eventually you can give much more of your drug without causing systemic toxicity. So this is our ultimate aim. So I'm going to talk to you about nanotubes today, but we are also doing other stuff such as polymeric nanoparticles, lipid-based nanoparticles, and it's kind of a toolbox that we need to choose based on the type of the drug and based on what we know about the pharmacokinetic of the nanocarrier. So because it's a brain meeting, I'm going just to talk about glioblastoma today, but we are also interested in other types of cancer as well as other types of neurodegenerative diseases, including also nose-to-brain delivery. But for the sake of GBM, we're looking at reaching the GBM from the systemic circulation. So there are problems to solve. So what I've learned is the problem is not only delivering the drug, but there is a problem of the actual tumor itself. So it's not as easy as this. Not all drugs work. Sometimes the tumor cells will become resistant or insensitive. And in this particular case, I'm interested in the cancer stem cell population of the GBM. So we have issues that you all know about. So really tackling, ideally, what we want to do is combine a solution to all of them. So we need to have a treatment that's targeted, efficacious, as well as personalized for particular. Thank you very much. Okay, so gene delivery. So we have different forms of material to deliver, mostly for gene correction. So you have the plasmid DNA where you want to deliver things to the nucleus, the RNA where you have the cytosolic delivery, mRNA, and in particular for this application, I'm interested in the delivery of CRISPR-Cas9 for in vivo gene editing. And the idea is you want to have a specific effect on, for example, we can activate certain anti-tumor genes or suppress oncogenes, or we want to correct certain mutations. However, as you all know, we have problems with in vivo stability, crossing the biological barriers, as well as the off-target effect. So there is an unmet need to develop ideally a non-viral delivery system for gene editing in vivo. It has already been reported solid lipid nanoparticles has been used for in vivo gene editing, in this case of the liver, because obviously it's easy to reach. Lung tumor, but actually for GBM, there is little that has been done, and we would like to utilize our delivery system that has been shown to reach the brain to help us with gene editing. So our target here is EGFRB3 because it's a tumor-specific mutation present in pretty much 30% of GBM. It has its own complications leading to tumor prognosis, bad prognosis, and we also, there are clinical trials tackling EGFRB3 from various aspects, and there are also preclinical trials using gene delivery. So this is our aim, is to design nanomedicines capable of in vivo gene editing for mainly identifying in vivo therapeutic targets. Because we know sometimes about certain targets, the tumor can overcome these problems by compensating, and it's very important that we validate these targets in vivo. Obviously, we cannot do it directly into humans, so we have to apply it in preclinical models first. So I'll switch now and talk to you about our nanocarrier. So carbon, if you've heard of carbon nanotubes. So carbon presents in different forms, and depending on how they are organized, they can have different physical properties. So carbon nanotubes, you have the carbon arranged in graphitic structure, and you can imagine a nanotube is made of one graphene sheet rolled up into a cylindrical structure. The problem is carbon nanotubes are water insoluble, so we need to functionalize them so they become water dispersible. So we apply 1,3-dipole or cycloaddition reaction to make them more water dispersible. It also allows for introduction of certain chemical entities and nucleic acids. We've reported in 2011 the direct crossing of the nanotubes into the cell membrane and what we call as nanoneedle delivery. And the advantage of this is you have a direct cytosolic delivery of your macromolecule. So by doing this, you're overcoming the endosomal and lysosomal degradation of the material. It's not the only mechanism that nanotubes utilize to deliver cargoes, but it also utilizes other mechanisms such as energy-dependent endocytosis. So it's really distinguished from other types of spherical nanocarrier by this, what we call nanosyringe or nanoneedle delivery. We already established that these nanotubes are able to deliver siRNA into neuronal cells, and they could rescue the brain from brain ischemic insult. But this was done by direct injection into the brain cortex, because obviously we didn't want to inject them systemically first to validate the target. But then once this has worked, we did extra work to see if systemic administration could be of any use. Serendipity worked here, and what we found is actually for the first time we found if we use slightly narrower nanotubes, which are chemically functionalized, you're able to achieve uptake into the brain between 2 to 5% per gram of tissue. And this was quite surprising because we did not expect this. In this case, these were functionalized with an antibody COMAC1, which was not meant to target the brain, but actually the targeting happened independent of the IgG functionalization. So then we focused on mechanisms and identification if these nanotubes can cross the blood-brain barrier or neurovascular unit, and if so, how. So we published this in 2016, and it was the first report showing directly that these nanotubes, which are approximately 200 nanometer in length and 10 to 30 nanometer in diameter. So they are able to enter into the endothelial cells. So these are endothelial cells isolated from porcine. So they are primary cultures. And what we found interestingly, you can see here from the stem images that they are enclosed within a vesicles that over time opens and sheds these nanotubes. You can imagine this is the brain region and this is the blood region. And the rest of the cell look intact, so your membranes, your mitochondria, so there is no specific damage. Moreover, this mechanism is actually temperature controlled, so at 4 degrees you don't see any of this mechanism. So our hypothesis was probably the blood-brain barrier recognized this material as maybe a monocyte or Trojan horses, and it allows them to enter into the brain. We did further investigation because obviously we had to confirm that this is not an artifact of labeling or indirect imaging. So these are direct images showing the interaction with nanotubes with the neurovascular unit, and also with Raman, this is 2-photon microscopy showing the white spots are actually outside the vasculature and they are within the brain region. To see where they are in the brain, so we applied SPECT-CT images and we labeled these nanotubes with NDM111. And taking into account, we would like to further target the glioblastoma. We functionalize them with NGPET2, which is a peptide, a ligand that binds the LRB1 receptor, which is overexpressed on both the BBB as well as on the GBM. So this is kind of double targeting approach. And you can see this is the brain region of an ounce. So with what we call passive targeting, you have faint signals. I mean, this is a signal to noise ratio. You still have uptake in the brain, but this is much higher when you have the NGPET ligand. In terms of spatial distribution, it's widely distributed into the brain section, and it's more intense when you have the NGPET. So these images were taken, or the section, the autoradiography, were taken 1 hour post administration. After 24 hours, you have almost negligible amount remaining in the brain. So our hypothesis here is, so the blood circulation time was actually short for both materials, whether it's with NGPET or without, but the amount in the brain is almost double when you have the NGPET, and this is the whole brain. So if we do a fractionation, capillary depletion method, you were able to isolate the parenchyma, and you can see that the parenchyma has almost double the amount of the nanotubes compared to the passive targeting. And this is reflected with your parenchyma to blood ratio, where it's above 0.1. Most of the CNS drugs are approximately in this region, so we consider this uptake acceptable. So the idea is probably what you have, these nanotubes bind the brain endothelium and slowly allowing the nanotubes to shuttle across. So the LRD1 helps to recycle the nanotubes inside the brain. So we tested this in GBM models. So this is GL261 cells implanted intracranially into the mice. And we quantify the uptake into these GBM tumors after 24 hours. So as I mentioned to you, after 24 hours, you have very little remaining in the brain. But in mice with brain tumors, you have remaining and retained nanotubes, especially when you have these nanotubes with the intravit. So we improve the retention into the tumor. Again, with the targeting, with the drug delivery, we're not hoping to eliminate uptake everywhere in the body, but all you do is increase the concentration by, if you're lucky, 2 to 4 times compared to healthy tissues. So back to our aim, we want to use these carriers to deliver CRISPR-Cas. So I don't want you to get too excited because I'm not showing full data, but what we've done so far. So we have three ways to deliver the Cas9 nucleases. So the easiest way is really to bind the Cas9 protein together with the guide RNA, short guide RNA, because we know the nanotubes like to bind adsorbed protein due to their high surface area and slightly hydrophobic region. So this is the easiest way. But we know the challenge is, in this case, we have to deliver the Cas9 directly to the nucleus for it to work. Now, our alternative approaches, if this doesn't work, we want to deliver the mRNA. So we would like to make the nanotube slightly more catheric and deliver the mRNA, which in this case would be delivered to the cytosol. And we're also able to use them to deliver the plasmid DNA to the nucleus. So I'm showing you the results with direct delivery of the protein. So for this purpose, we're working with Steve from Edinburgh. He has established this very interesting brain cancer stem cell line, and this cell line is knocked out for PTEN and F1. So we can actually grow it in the C57 immunocompetent mice, which is an advantage for us. And we managed to grow them into the brain intracranially with tumor formation within 23 days. So these are the bioluminescence images. And we like it because we're able to do luminescence images, GFP, as well as if we label our nanoparticles with an optical dye in the near-infrared region, we're able to do the co-localization. So we can quantify the uptake in the tumor and then later on look for the knockout effect using either the luciferase or the GFP. Once we validate the delivery system, we're going to move on to our therapeutic target, which is the EGFR-B3. So we've already validated our short guide RNA for GFP and for the EGFR-B3. So for the GFP, it's a reported sequence, but for our EGFR1, we designed one that actually targets the glycine residue in the mutated form of EGFR-B3. And we've already shown, so this is just an in vitro validation of the sequence. So you have your PL6 cells, which are GFP positive, very little of negative cells. But if you transfect them with your RNB, which is RNA Cas-nuclease protein, you get the knockout. And this was just with 1 to 3 mass ratios. So this is kind of our optimized positive controlled results. We confirmed that we're able to cut specifically the gene at the region of interest. So this is our PSAR amplicon. So we use the gene, we incubated with the RNBs, and then with electrophoresis, you can see that specific cut of the region of interest. So our guide RNA is actually specific. And by Western blotting, you can see there is, so there is reduced expression of EGFR V3. So we're kind of now ready to do the further in vitro and in vivo gene editing. Because we need large quantities of the Cas9, so just to give you an idea, for a single conjugation, we require about 1 milligram of the Cas9, which is quite a lot if you want to buy it, so we have to make our own. And you can see that we managed to get pure Cas9 protein that's specific. So this is the dot plot showing the with the anti-Cas9 antibody. And with a commercial Cas9, we get 70% knockout. With our one, we get 60%. So we were kind of happy with our protein production method. And then we loaded the Cas9 on the CNT by simple electrostatic incubation, and we evaluated the Cas9 loading. So we managed to load 0.4 milligram of the Cas9 to a milligram of the CNT. Again, that's quite acceptable because looking at the amount of the CNT that will reach the brain, we have quite enough of the Cas9 to reach the brain as well. And we managed to, I mean, we can see it's kind of intact in the expected molecular weight region. So we looked at the uptake in cells. So these are the PL6 cells transfected. If you incubate them with the complexes, you can see the black dots reflect the nanotubes. So the one you see are obviously the aggregates, but you have the ones inside the cells that we cannot see by naked eye. So when we see this image, we know there is good internalization into the cells. And we confirm by flow cytometry with the anti-Cas9 staining that actually the Cas9 is internalized into the cells. So we're currently working on the in vivo gene editing ability, and we've done also some studies showing that the Cas9 on the CNTs is able to reach the brain by SPECT CT images. So we're ready to test the efficacy in the PL6. Well, so maybe next time I should be able to share more data with you. So at the same time, we're working with a different type of lipid nanoparticles, which is cationic. It's the neutral at physiological pH, and for that we're working with the delivery of the mRNA as a parallel approach. Okay, so we talked about that. So that's it. So I would like to thank the PhD. So basically the work I've shown you was on the CNT uptake in the brain was the PhD of Omar Kaffa. It was a BB Senior Investigator Award where Noelia and Julie worked on this project, and currently all the Cas9 work is done by Nadia and Pedro Costa, and our collaborators are helping on the various aspects. Our funder, obviously, and my group for the continued support, and for you for the invitation. Thank you very much.
Due to time, maybe one quick question.
Okay, maybe two quick ones. So one, how long does it take to cross into the brain, across the blood-brain barrier, after you have given the nanotubes? That's one. And then the second one, when they is the structure preformed and then it expands to fill the area, or is it a solution that then makes the two?
Okay, so the question about the penetration into the brain. So in vivo, within 5 minutes, we see the nanotubes in the brain. The ultrastructural images show it's a slow process. So this tells us again about the in vitro and vivo extrapolation. So we don't know whether the protein corona plays a role in internalization in vivo, but in vivo it's 5 minutes in, 1 hour to 4 hours out. So about the formation of the nanotubes, you mean? Yes. So actually, we don't make the nanotubes. We buy them, but we functionalize them. But there are some labs that make them by CDD or other methods. But we buy them from a supplier, and then we conduct the shortening and the chemical functionalization. So they're already tube-like structures of micron length, and then we chop them up to below 300 nanometers.
Right, thank you.
Okay, thank you so much about Emma. And the next speaker is Dr. Webster Kazasa from University of Zimbabwe, and he is going to present from Radiological and Slovakia cure of brain tumor. The sign of progress now showing. Let's welcome Dr. Kazasa.
Hello, everybody. I'm sure you are tired. You want to leave. I'm going to do be very quick, since I'm not a scientist like most of you. I was a classmate of Piotr and Michał, and they invited me to come and talk to you about this topic. This is a very fun topic, isn't it? From Miroslaw to cure of brain tumors. I'm a clinical oncologist. I see with patients, don't have animal models, even though we have plenty of animals in Zimbabwe. I talk to these patients and they actually want answers from me. So when I told them that I was going to Baltimore and discuss about glioblastoma, I have 5 patients with glioblastoma at the moment. So they're expecting answers from me. And I got a bit of some from you guys. Well, radiation oncology, I mean, probably these three names are very, very important for us. William Röntgen, Becquerel, and Miroslaw. That's what makes us who we are. People who are here doing imaging, if you're in radiation oncology, if you're in diagnostic imaging, you all use what this guy discovered. Probably none of us, most of us would be out of work if it weren't of these 3 people. So in basically those 3 years, 3 Nobel Prizes were issued to people who changed lives for most of you guys. You might not like these guys because, but these are the guys who are keeping you and feeding your families because of the three things that they got. We are here today. Basically, we are excited because of excitation of electrons. What we see and what we hear is because of electrons. If electron is excited, we are excited and we get paid. I get excited when I ionize. Some of you don't ionize probably, just do photoelectric effect. Some of us base our money on Compton effect. But at the end of the day, it's all about these particles. So a few particles and a pocket of energy, and there's a whole profession which are making money out of it. So again, I heard somebody talking about the amount of sarcomas of the base of scalp that occurs when somebody is radiotherapy to what? When kids have radiotherapy. I think sometimes we over-exaggerate how toxic radiation can be, or how carcinogenic it is. But we should all remember there's no dose below which radiation cannot induce cancer. Even the lowest dose that we do with imaging can excite electrons and can cause what? Can cause transformation. But anyway, I'm here to talk about what these guys did. They allowed us to be able to image tumor, to see where it is, probably check its response, and probably allow us to see whether it's cured or not. But what are we doing with these brain tumors? Brain tumors are only 2% of all cancers, but apparently they are the 4th in the number in position of how they actually cause loss of life loss, because they are in children. Most of the children end up probably we lose children early because of this. This is the commonest brain tumor. Brain tumors are the commonest cancers in children. Because of that, they actually make life loss significant as compared to other cancers. On number 4 after testis, cervix, and neurosurgery lymphoma. So they are very important. And I understand Monica, who works with pediatric patients, understands this issue. And when she sees a child with pondent gliomas, she's furious because sometimes you can't do anything. But I think we are trying our best. Now, if you look at what has happened with survival, we talk a lot about what we can achieve. We've done a lot with nanoparticles, with brain barrier, which we are trying to focally open with high dose ultrasound scan. We are doing a lot of things, but at the end of the day, our survival are not phenomenal, but we are doing our best. If you look at this series which was done in King's Hospital, where probably Our Lady is coming from, in the 2 decades, the improvement in median survival has been barely something like 4 months. Or it looks to be a lot, but we are doing our best. But sometimes when we fail to do our best, we always start Will Roger. I understand you know this guy was called Will Roger. Will Roger was a comedian. I'm not sure if there's anybody from Oklahoma or California here. Sometimes what we end up doing if we can't see survival, we start classifying patients. If you look at this right survival, but just classifying patients into mid to age, we start seeing some big improvement, isn't it? But I think we are doing a lot, but Will Roger phenomenon is a phenomenon that has been known in medicine. When we classify patients, we start doing better. If you look at glioblastoma in the 20 to 40, the 30% level, 90%, it drops to 30% when we are above 50. Otherwise, we still in trouble with these tumors. Now, I'm going to be quick. We talk about background noise. We heard this term being said many times by many presenters that there's a lot of background noise. And we need to what? To remove it. There is also a lot of background academic noise. Background noise from scientific evidence. So if we are to, I don't know where this study is coming out. These guys, the supervisor curing, we are lucky during that time. There was no internet, there were few researchers, there was very few background noise. And nowadays you have to deal with background noise so much research, you need to navigate through it so that we get to some conclusion. Or else we have to make sense out of the noise. There's so much research that's going on, probably we are not thinking it's noise and we are not making sense out of it. The amount of work that has been done here, probably we are all pulling ourselves. She spoke about nanoparticles, Pedro talk about his stem cell injection, another guy will talk about his temozolomide. We all probably don't listen to each other, and we end up doing so many things in our own corners, and we are not pulling the same side. And we need to probably make sense out of the noise that we're creating in medicine. Now, we use radiation energy in 2 ways: to image our tumor and to deliver cure. If we can't see anything, we can't give radiation. Without imaging, we wouldn't be able to cure anybody with radiation energy. It would be nice to get more ways of imaging the tumor so that when you are radiating, we really see what we are supposed to do. This is what is happening with reconstruction and fusion of image of MRI and CT scan with T1 and T2 weighting. Without MRI, it's very difficult to control tumors with CT scan alone. But I mean, we are sort of getting some improvement. We also have the PET scan, which are improving our ability to control tumor and deliver radiotherapy to our target organs, where it's sparing normal tissues. The last is the presentation which was done, which was showing how that SPECT CT scanning would actually improve our ability to control and see the edges of the tumor so that we deliver accurate radiotherapy. There's this thing that was done, I'm sure somebody read, you guys read about it, the hopes and the predictions of people about these brain tumors. There are a lot of people who were asked in this crystal ball prediction, and they're talking about this. This was done last year, and people are talking about this disruption of the BP for us to give radiation to deliver a lot of dose without chemotherapy to the tumor by all mechanisms, or as well to be able to profile our tumors properly. Again, this summer we talk about if we are able to turn the negative trials into something positive, because I'm sure there are things that we're missing that we may actually get out from whatever is the negative trials are showing us. But again, we all need to team up to get the best result out of what? Out of cure. They always say if the only tool that we have is a hammer, everything around you looks like a nail. So we end up doing one thing because that's what you know most. But if probably you team up with those with sharpers and picks, probably you actually do much better. If you combine all modalities of chemotherapy that we have, that molecular immunotherapy, conventional hormonal treatment, you combine radiation instead of beam, brachytherapy, sealed and sealed source surgery, endovascular, open, and if you use all sorts of imaging, I'm sure we're going to be able to get much more cure. When I was listening to you guys, you do a lot of things that are being said. the catheters that are being introduced with the lumens, it's possible that we can actually do a lot with brachytherapy in brain tumors. We seem not to be doing much about brachytherapy in brain tumors. So if you can have a catheter going into a tumor, into a catheter, it's possible to implant seeds. There is a role. There's an old paper, if you go into literature, look what people are doing with brachytherapy in brain tumors. There's little, but people did a bit and forgot about it and moved on. But again, the answers, if the wafers you can put polymers, chemotherapy polymers, you could also drop in the radioactive material, you can put in seed implants, the iodine implants, palladium implants, which can give those around the tumor, which you've already given chemotherapy, which can be acting as, which can be giving radiation at the same time you're getting sensitization from the chemotherapy that you give. So the problem is there could be a combination of the polymers, wafers, and radiation treatment, which I didn't hear anybody talk about it. Again, we all are in the imaging world. We like things what we see. We see cerebral, there's what we call cerebral outcomes, secondary outcomes, and primary outcomes. For us, when we image tumor regression, we are happy the tumor disappeared and there's local control. But that's in our world when you image and you see things. There's what we call secondary outcome, which is what patients are sometimes very, very excited about, whether their quality of life improves, whether their disease-free survival, or the best thing that patients want. This is what the disease-free survival and overall survival. I call it the proper p-value. With the p-value that we calculate, this is the patient value. We always calculate our p-value, which we are happy about, but the patient value sometimes is missing. Patient value probably will be this outcome, not our statistical significance, which we always calculate. They are happy when they're significant. The reason why Petri and colleague asked me to come to here is probably they're trying to make a plan so that they get a bigger animal model. I've agreed that I'm going to do that for them. So I'm sure there's a guy who's going to organize a big go MRI and CT scan. When they come to Zoom, we're going to be able to do probably a bit of a stroke model in the end of this tree. And I'm sure it'll be easier for these guys to go in with their catheters. There's a big bowl. You can put in 15 catheters for everything. Well, now the question that we asked is there a sign of progress in cancer screening? Yes, there is a sign. All what you are doing, guys, is phenomenal. It's a sign. And I'm sure probably sign is going to be part of this progress. A sign grow, and as you guys do much more research, I think the sign of progress are here to stay, and we are going to see much more coming on. And in 2051, we are going to have this thing in Niagara Falls. Thank you.
Okay, thank you so much, Dr. Kasesa. And any question?
I think this is a great note to end this session on biomaterials and nanotechnologies. Let's thank all the speakers again, and then we're going to have just a really short, maybe 5-minute just stretch and go into the next session. But let's thank all the speakers again for the great session.
We started with medicine. Good. See you. Thank you very much for coming and then for helping with sharing.
There'll be no catching up, obviously. It will probably even longer. Is this like a Polish conference? Is that how it works? The sort of time is sort of the sort of thing, if you're having a good time, you speak around.
Well, I don't know. This is a job of charity. Okay, so you didn't mean. Okay, because when you exactly, because we met at Hopkins, but you were there.
That's not last until like late hours. But we were trying to stay on time.
Because I could just say like a few words at the end of like a closing words, you know, see it outside. That, you know, it's like because it's late, there's no slides, nothing. It's just just a good kind of look at this. Timing is a program, but yeah. So
You check the battery. 92%. Micro USB. So this is ready. We have an hour. If you would like to take your seats, we're going to begin the last session. I'm Peter Searson, this is Wei Zhu. We're both from Johns Hopkins, and we have the pleasure of introducing the last three speakers of the symposium today. So for those of you who are keeping track, the last two presentations, the second to last one we've already had, the last one isn't here, so we've just got the first three as listed in the program here. So the first presentation in the last session here is the prevalence of ultrasound effects on the extracellular space, how expanding these regions can enhance both local and systemic delivery, by Victor Frankl from University of Maryland.
Thank you. Thank you for the introduction, and thank you for whoever's doing for hanging around. Appreciate you being here. Well, first of all, I want to thank Monica and Eric and Fjord for inviting me to speak and giving me the opportunity to tell you about some of this work that we've been doing. Regarding my title, you can see it's quite long. Actually, it used to be longer when I submitted it, but I was asked to shorten it. So the only thing that's missing at the end is in solid tumors. So as it will soon become clear, I'm talking about a drug delivery in solid tumors and how we can try to modulate the tumor microenvironment. And it's been for improving drug delivery, and it's been something that I've been working on in part over the many years of my non-illustrious academic career. One other thing I want to say, I was going to introduce the other speakers who are still here behind me. Rang and Han doing some very cool stuff. Costas, as you saw, some cool stuff. So I'm going to be sticking to more mechanistic work, less kind of image-guided stuff. I have a couple of image-guided slides, but other than that, I'm going to stick to more the mechanistic work. And I'm going to start with this slide here. So this is a slide. This is a relatively simple, straightforward study that was carried out in collaboration with Graham Woodward's group, who presented yesterday, and also with Anthony Kim, who works with him at the Neurosurgery department at the University of Maryland. Makes these really cool nanoparticles, and you'll be seeing some for this brain work and some later on for the other tumor work. So this project was carried out in these ex vivo brain slices. They were freshly harvested, kept in chilled artificial CSF, as you're supposed to do. And we used a non-focused low-energy ultrasound device similar to the ones that are used in physical therapy. And basically, we were able to show that by giving these treatments to brain slices, that we could expand not only the extracellular space, and we'll be hearing that word a lot over the course of my talk, but also the perivascular space. For those of you who are not familiar with it, the space is adjacent to the individual blood vessels. We did some image processing. We were able to show that we can indeed significantly enhance or expand these regions. We also did some standard histology, tetrazoium, to show that we weren't destroying the tissue, using a positive control for kind of over-robust treatment. We also then, in a parallel set of slices, we injected these nanoparticle probes. These are coated probes with polyethylene glycol, so they don't stick to the extracellular matrix, and instead they're only restricted by in terms of their size. And this technique, this technique basically tracks them with something known as multiple particle tracking. It determines this metric known as mean square displacement, or MSD. And basically, this is a surrogate for the diffusivity or the kind of diffusion and movement of the particles. It allows you to compare things like particle size and also the medium that you're working with, as in our case. And so we're able to show, again, when we pre-treat with these low energy ultrasound exposures, that we can significantly enhance the MSD values for both 100, 200, and even remarkably 500 nanometer nanoparticles in the tissue. Now, of course, we were interested in seeing if we could also do this in vivo. For this, we used an MR-guided focused ultrasound system, and I won't get into too many details about it because you've heard quite a bit over the last couple of days. This system allows you to again treat with very accurate image guidance. We treated a relatively large region in and around the striatum, and then we injected our nanoparticle probes, similar probes, and this time we did it by convection-enhanced delivery. I need to mention that these pulse-focused ultrasound, or PFAS exposures, that I'm going to be calling them over the next 5 or 10 minutes, are essentially very different than the ones that are used for opening the blood-brain barrier. The ones that were developed by my group over a number of years, they're relatively high in acoustic pressure, typically 5 times greater than those used for opening the blood-brain barrier. We don't use microbubbles. And also, we're not targeting the vasculature. We're actually targeting the parenchyma directly, and we're trying to generate effects, as you saw earlier, for those brain slices. So now looking at the results, first of all, for Evans blue dye, which is a relatively small molecule, we see a greater volume of distribution. And basically, we sectioned and we looked at all the particles over the entire brains, determined the volume of distribution. No real difference, apparently because the molecule is so small, it doesn't really need any help from the ultrasound. With the nanoparticles, we found, as you'd expect, a decrease in the overall volume of distribution as you went to a larger nanoparticle size. But in each case, we found a significant increase, again, in the volume of distribution when we pre-treated the brains to these PFAS exposures. And I just want to mention that we weren't looking to, optimize and get, large region of distribution. We basically needed to titrate the amount that we're putting in there into the brain so that we were able to make a quantitative comparison. So these exposures that we were using in the brains were actually developed in my lab when I was at the NIH years before coming to the University of Maryland, and we did a lot of experiments in the muscle. The muscle is more uniform, easier to treat, of course, and we were able to show, again, in a non-destructive manner, we can not only open up the spaces between the individual muscle fiber bundles, but also the tissue remodels back to its original state over a period of about 2 to 3 days. And we also injected probes into the muscle after treatment. We gave a cocktail in this particular experiment of fluorescent albumin and nanoparticles. The albumin, again, is a small molecule. It basically shows you the convective front. These are in vivo images that were captured with a multispectral in vivo imaging system. Much better distribution, but no real difference, again, with our PFAS exposures. With the nanoparticles, on the other hand, they normally are restricted to the needle tract, but here you can see we're actually getting the nanoparticles kind of moving away from the needle tract through these gaps created in the muscle. And if you look now at this, these representative cryo sections, you can see quite nicely again. Normally stuck in the region of the needle tract, we get really nice distribution through these gaps that were generated in the muscle. Now, we did a lot of mechanistic studies, and I could spend, the whole day just talking about this slide, and I'm not going to. Basically, we found, we proposed a mechanism based on what's known as an acoustic radiation force. It's generated through a transfer of momentum from the ultrasound wave to the medium. This creates a localized displacement. It generates a very steep gradient of displacement on the side of the focal zone. And we found actually that the strain that's generated by these forces from these displacements actually peaks just off axis, a few millimeters on the edge of the focal zone between the region that's being displaced and that's not being displaced. So this is where the strain is being generated with each individual pulse. And basically, we proposed a mechanism that with each pulse that we give and the repetitive strains that are created, that we're actually working on the relatively weak points in the tissue, in this case being the interface between the cells or the other structures, and as a result, this is gradually expanding the extracellular space. And again, this is being done in a non-destructive manner. Now, of course, we wanted to see if we could also use this for a therapeutic purpose. We did a bunch of studies in different tumor models. I'm going to show you a few of those. In this one here, we actually injected plasmid DNA encoding for TNF-alpha. It's a very potent cytokine. We found that compared to the TNF-alpha on its own, we got significantly slower tumor growth when we pre-treated with our PFAS exposures. Actually, in the data we published, the study we're still calling HIFU, high intensity focus ultrasound. If you now look at some representative tumors, and I apologize for that they don't look very nice, but they kind of exemplify what we found. Not only were the ones that just received TNF-alpha of approximately twice the size as we saw in the growth data, but compared to some partial hemorrhage in the upper region of the needle tract, we got a much deeper and broader region of necrosis with the PFAS and some pitting at the surface. And we assumed that this was happening, again, because we're getting better penetration and distribution of our agent. This was validated when we then injected, we then injected fluorescent nanoparticles again. We led with fluorescent nanoparticles. And again, we found that they're normally restricted to the needle tract. These are whole tumors that were cut open. And you can see with the PFAS, we're actually getting much better distribution and penetration into the tumors. And again, we did some electron microscopy, which we love to do. And you can see now, again, these regions in the extracellular space that are expanded, a little more heterogeneous than you saw before, because again, these are solid tumors. And these were not present in the untreated controls. And we're also interested in seeing if we could also do this with systemically administered agents. We're not sure what we were going to get. So in this study, we actually treated a different tumor model, and we then injected these fluorescently labeled monoclonal antibodies with FITC, and we found that we were not only getting better penetration at the surface of the tumors, but also in the more central regions. And this was shown with image processing, looking at the FITC signals. We also labeled the vessels, the vasculature with fluorescent lectin in red. We found that we're also getting better penetration moving away from the individual blood vessels after this agent had extravasated. Now, the results that I showed you for the TNF-alpha were kind of pretty straightforward, right? We saw we were creating these structural effects, expanding the extracellular space. The agents are getting better penetration and distribution, and as a result, we got a better therapeutic effect. Now, here, we switched the FITC to yttrium-90. Now we also got an improved therapeutic effect, slower tumor growth, and as a result, better survival. But the question now was, again, straightforward effect for the direct injection. However, why were we getting better delivery with our systemic administrations in this particular study when all we showed earlier was we're just creating effects at the level of the extracellular space. And that essentially was the topic of my, or the title of my talk. Why, by creating these types of effects, are we getting better systemic equilibrium? In order to answer that, we need to take a closer look at the tumor microenvironment. It's been well described in regards to its barriers for uniform and adequate drug delivery. On one hand, you have fibrillar collagen, which can prevent the movement of agents when injected directly into the tissue, and also when they extravasate. This is especially true for large agents such as viral vectors and nanocarriers. In this study here by Rakesh Chain's group, they showed quite nicely that when they co-inject these oncolytic viruses that are fluorescently labeled with collagenase compared to the injections alone, these are in these tumors growing in these dorsal skin chambers, they of course get much better distribution because they're degrading the collagen. We carried out a very simple experiment in collagen gels. We grew them we made them with collagen 1 at a physiological concentration, and we found that when we treated them at a single location and then immersed them in these particles, they only get taken up in the treated region. Even a day later, they really haven't moved away from that region, indicating that we aren't able to create some kind of mechanical effects to affect the collagen. Now, the other factor is high interstitial fluid pressure. This occurs as a result of a lack of functional lymphatics combined with leaky and immature blood vessels. This can create very high interstitial fluid pressures, typically with a very steep gradient as you go from the periphery of the tumor towards the center. And in some cases, the interstitial fluid pressure can be as high almost as the microvascular pressure. And of course, that's very bad if you want to deliver things systemically. Typically, large agents require convection in order to extravasate into the perivascular space. So we did a number of studies to kind of investigate the potential effects of our exposures on the IMP. In this first study, we infused directly into the tumors, and we measured in real time with an inline pressure probe. We were very interested in the baseline pressures that we got when the pump was on. We then turned the pump on, let the pressure rise to reach a plateau, and then let the pressure return back down to these levels. And at these upper levels, what we knew was happening here is that the system is essentially in a state of equilibrium, and that the flow that was being pumped into the tumors was actually equal to the flow going out, and hence these plateaus. So looking at the results of these studies, first of all, for these baseline pressures, we see that these are lower, consistently lower in the P+ treated tumors, and essentially we got the same thing at these upper plateaus, again, where the system was in equilibrium when the pump was on. Now, this kind of data can be analyzed using something known as Darcy's law, which shows the relationship between pressure and flow for a system with a characteristic hydraulic conductivity. And without actually looking at these values that we were getting here, we can very simply say that because we're working with constant flow rates, the lower pressures that we're getting are somehow telling us that we have increased the hydraulic conductivity of the tissue. Another experiment we did was using something known as acoustic radiation force impulse imaging, or ARFI. Basically, this is a type of remote elastography that uses these high-frequency pulses, where you're able to not only determine the maximal displacement that you're getting in the tissue, but you can also look at the rate at which the tissue returns back after you've given those pulses. And that's what we were interested in. It basically reflects the elasticity of the tissue. So in this experiment, we measured a number of times over the surface of the tumors with ARFI. We treated with our P+ exposure. We did the measurements again. And then we're able to see that in each of the tumors that we did this, that after giving our exposures, we found a significant decrease, again, in the rate at which the tissue was relaxing back to its initial state. Now, in the absence of any whole-scale damage being produced in the tissue, which we know doesn't occur, the only way to explain these results is that we had somehow reduced the amount of fluid in the tumors. You can just imagine a balloon that's filled very tightly with water. You press it, it kind of bounces back right away. You remove some of the water, and the kind of bounce back is not nearly as quick. Now, this is the last experiment that I'm going to be telling you about. It's something actually that's being done by my student, Lee, who's in the back somewhere. Oh, there he is. So this is an experiment that's kind of culminating all the stuff that we've done up until now. Here we're using the classic method known as the wick and needle method to measure the interstitial fluid pressure within the tumors. We used two sets of 10 tumors, very closely matched in size with very low overall variability, which is very important. And then we measured the pressure from the edge of the tumor all the way through to the center and then all the way through to the other side. So one of the first things we found is that in the center, which is where the pressure is higher, we got a 30% decrease in the interstitial fluid pressure for all, average for all 10 tumors. And if we now look at all the average data for all the tumors as we move from one edge to the other, we find not only do we get a much less steeper curve going from the periphery to the center, but we also get a lot less variability, which is also an important factor when it comes to the tumor microenvironment. Now, in a parallel set of tumors, we treat them the same way, same sizes, same number of tumors. We're actually still collecting and processing the data now. We injected these fluorescently labeled nanoparticles. And first of all, we found overall approximately a 60% increase in the number of particles getting into the tumors, as indicated by the fluorescent signals. And more interestingly, we also segmented the tumors at 1/4 diameter intervals. And if you look at the trend that we're seeing now here with our results, again, as we continue to collect them, we're getting relatively less particles in the periphery of the tumors with our PFAS exposures and relatively more in the more central regions. Now, this kind of data can be analyzed in a more abstract manner. But first of all, I want to mention that this is the first time that we've actually had data where we're directly quantitatively comparing the two. Up until now, we've collected all this data anecdotally. We've shown better delivery, better penetration, reduction in IFP, increase in hydraulic conductivity. Now we actually have a true data set where we, in the same tumors or the same sets of tumors, that we can actually compare the IFP with the delivery of these agents. If you look at it in a more abstract manner, you can see that essentially what we're trying to do is flatten the curve for the IFP, and as a result, get better and more uniform delivery across the tumors with our delivery of our agents. Ultimately, the goal is essentially to flatten the curve so that your tissue is behaving more like normal tissue, and again, you're getting more uniform delivery across your tumors. And this is essentially kind of in parallel with what they're trying to do or already started doing with Avastin, where they're using it to normalize the vasculature, and as a result, also lower the IFP. All right, so just quickly to summarize these results and explain what we think is the mechanism for generating these effects. So first of all, this we know we're creating this repetitive focal mechanical movement in the tissue. This is generating localized strains. And because we're working with a heterogeneous medium comprised of cells and extracellular matrix, this is creating structural alterations like expansion of the ECS, as we saw, and the disruption of collagen. This is increasing the effective pore size of the tissue, allowing for better penetration and distribution of our agents and improved therapeutic effect. This, of course, pertains specifically to the direct injections either into the tumors or the muscle. Now, because we're working with the tumor microenvironment, these effects here can also increase the hydraulic conductivity of the tissue, which increases or improves the interconnectivity within the tumor microenvironment. It allows for improved flow from regions of high pressure found in the core of the tumors to the periphery where the pressure is lower. It also allows essentially a better reabsorption or increased reabsorption of fluid through more functional vessels, also found in greater abundance in the periphery. This lowers the overall IFP and further contributes to increasing the delivery in terms of increased extravasation for systemic deliveries and also penetration of the administered agents. Again, both extravasating and also injected directly. I'm just going to tell you one more thing before I finish my talk, and that's in terms of what we're pursuing as far as a clinical translation for this type of procedure. We've been looking very seriously for treating head and neck squamous cell carcinoma, including talking with medical oncologists and head and neck surgeons. We see head and neck as a candidate for a number of reasons. For one, these tumors, because of the intricate anatomy in and around the head and neck region, they're not amenable to complete dissection or ablation by focused ultrasound or other modalities. They're also, for the most part, accessible for treatment with a focused ultrasound, approximately 70% or more, depending, based on where they are located. And also, these tumors suffer from very poor drug delivery, where if someone presents with a primary head and neck tumor, they're typically treated with a concurrent chemo radiation therapy, where cisplatin is generally the drug of dose, but it also has very severe dose-limiting toxicity. So we've already shown using our nanoparticles that we can eliminate for now this type of toxicity. You can see here, this is free drug. These are the cisplatin and the nanoparticles, and we continue to collect this data. We're up to 2 weeks, again, no toxicity. We've We've also shown that we can enhance the delivery of these nanoparticles, as you saw earlier. This is a different experiment. We're getting about 30 to 40% more of these nanoparticles than the particles on their own with our exposures. We've also shown that if we load these particles with cisplatin compared to free drug, we're getting more than a 3-fold increase with these particles alone, and then more than a 4-fold increase if we first treat with our focused ultrasound exposure. We're also looking into using targeted nanoparticles for the FN14 receptor, which is overexpressed in many solid tumors, including head and neck tumors. And lastly, we're also looking at using these cisplatin-resistant tumor models that are generated by essentially exposing them in vitro. And one of the cool things about these tumors is not only are they have a higher IC50, but they also overexpress this FN14 receptor for potentially better drug delivery. All right, so that's it. Before I finish, of course, I want to acknowledge everyone who contributed to the work I presented today. A lot of the work was my time at the NIH Clinical Center in the Radiology Department. Some of this data was generated by my graduate student who I co-mentored with Desmond Zderich from George Washington University. And of course, all of my colleagues at the University of Maryland School of Medicine, and especially Ali, who's sitting here, who's got a fantastic job on a lot of these projects. Of course, thank you for your attention.
Time for a quick question? I have one. Do you have any evidence from your experiments that ultrasound actually increases the number of circulating tumor cells? And is that a clinical problem?
It's a great problem. It's a great problem. So we did
Great
actually.
problem?
No, I mean, it's a great question. It's not a good one. It's a bad problem. So we've actually, we did a study. We have one of the only 2 published papers looking at the effects on potential metastasis, where we looked at metastatic burden in the lungs in a breast cancer model that metastasis only the lungs. There's a ton of, even though we did 50 animal groups, there's a ton of variability. A lot of people are skeptical with the potential effects of doing that because we are, disrupting collagen and so on. But then there's the whole seed and soil kind of hypothesis that even if you not only need release the cells, but the cells first of all have to be the ones that are ready to metastasize. So potentially in a metastatic tumor, this could happen. Again, the jury's still out, but it is something that needs to be looked into. But as far as we've seen, there isn't a significant effect. Like I said, we did a study, there's a lot of variability. Something needs to be looked into further. But the idea, I guess, would be that to start treating before the tumors become metastatic, and then essentially, I mean, when you do when guys remove tumors by surgical resection, there's millions of cells that are circulating right through the blood, and they don't necessarily become metastatic. So that's the kind of argument that we use, at least for now.
Sounds really cool. Okay, let's thank Victor again.
So our next speaker is Dr. Hongzhen from Washington University, so let's welcome our speaker.
Okay, so I have to head to the airport right after my talk. So if you have questions or think about opportunities for collaboration, feel free to contact me, and here is my email address. So my name is Hong Chen, Hong as in Hong Kong. I'm an assistant professor from Washington University in St. Louis. Today I'm going to talk more about focused ultrasound-mediated brain drug delivery. And our lab has been interested in the treatment of DIPG. And I think I can skip this. Everyone already probably know DIPG is very hard to treat, and there is an urgent need for non-invasive technique that can circumvent the blood-brain barrier for the treatment of DIPG. And then, so we already know focused ultrasound combined with microbubbles can induce blood-brain barrier disruption. And the way it works, I believe many of you already know. So microbubbles combined with focused ultrasound. Let me see, right? It's okay. The video is not playing, but the concept is when we apply focused ultrasound to microbubbles, the microbubble are going to expand and contract, which push and pull on the blood-brain barrier and leads to enhanced permeability of the blood-brain barrier. And then our lab already showed using this technique, we can achieve non-invasive and localized delivery of radio-labeled nanoparticle to the pump where the AIPG occurs. So this is normal mice. We use this to demonstrate the concept that we can use Folks ultrasound combined with microbubble this technique to achieve non-invasive and localized drug delivery to the pumps. We also did a lot of safety evaluation and is already published. Then the question we were asking ourselves is that although this technique works very well, we still have to inject the drug through systemic circulation. So it's associated with potential toxicity to other organs. Then that's why we look into another pathway, so another route for drug delivery. And the routes that we look into is intranasal delivery. Intranasal delivery is already a brain drug delivery technique used started for probably 2 decades, and there's already clinical trial delivering insulin for the treatment of Alzheimer's disease through the intranasal route. And the concept is that intranasal delivered agents can go directly from the nose to the brain through the trigeminal nerve and the olfactory nerve pathway. And then the challenge with this technique is that the drug delivery is not targeted to where the disease is located. And second, the delivery efficiency is very low. So we were thinking whether we can apply Folks ultrasound at the target brain location to enhance the drug delivery that is administered through the intranasal path. And then later I will show you our hypothesis to support this concept. So I started working on this technique since 2014. And today I'm going to show you some of the results that we've already get. So this is a video to demonstrate the concept. The intranasal delivery drug goes through the nose directly to the brain through olfactory nerve and trigeminal nerve pathway. And after they reach the brain entry points, they distribute in the whole brain through this heart pumping induced perivascular pumping effect. So the drug will transport along the perivascular space and distribute in the whole brain. So the drug is already beyond the blood-brain barrier, and it minimizes systemic exposure because the drug directly goes from nose to the brain. And Folks ultrasound with microbubble, we already know microbubbles can be activated by Folks ultrasound to expand and contract, which push and pull on the blood vessel. At the same time, also push and pull on the perivascular space and the extracellular space, which we think can lead to enhance the penetration of the drug that is in the perivascular space deep into the extracellular space. So this is our hypothesis that the effect that we call it microbubble pump effect compared to the perivascular pumping effect. So we hypothesize that microbubble pump effect can enhance intranasal administered drug, the delivery efficiency of intranasal administered drug at the Folks ultrasound target brain location. So the objective of our study so far is to develop this technique we call fusing for drug delivery to the brainstem because the DIPG occurs mainly at the brainstem. And also brainstem is unique in that it's directly connected with the nose through the trigeminal nerve pathway. So we're looking to demonstrate non-invasive and localized delivery by this technique to the brainstem, quantify the delivery efficiency, evaluate the systemic exposure, and explore the potential delivery mechanism. So this is a simple illustration of how it works. So we use fluorescent labeled gold nanoparticle as our model drug. It is administered to the mouse through the nose, and microbubbles were injected through the tailbone, and then we apply Folks ultrasound targeted at the brainstem. So this is a study timeline. So after the treatment, we sacrifice the animal, harvest all the organs and the brain, do fluorescent imaging to look at spatial distribution, and then quantify the gold concentration to look at to get quantitative results. So first, this is a representative image of the mouse brain in a horizontal view, and the brain. So we can see fluorescent labeled nanoparticle locally delivered at the focus ultrasound target area. So these results combined with our previous results. In our previous study, we already showed we can use fusing to deliver Texas red labeled dextran and also brain-derived neurotrophic factor to a target brain location. So this result is consistent with our previous finding. It shows that this fusing technique has the potential to be expanded to other brain area, and I also have the potential to deliver different type of agents. And then what we did is we compared the delivery efficiency of fusing with focus ultrasound-induced blood-brain barrier disruption, and then use intranasal delivery and IV delivery by itself as our control. So after the treatment, we get the brain and the section to brain slices. So on your left are the grayscale images showing the fluorescent images to show the spatial distribution of the fluorescent labeled nanoparticle. On the right are the photographs of the brain slices. So these are the slices where the focus ultrasound was targeted. And as you can see, there's clearly enhanced delivery at the focus ultrasound target location for the fast BVD treated brain. But compared with fusing brain, there's clearly higher fluorescent intensity. And then we quantified the delivery efficiency based on the gold concentration. So this is a plot of the percent injected dose per gram of tissue for fusing and fast BVD, IN only and IV only. And as we expected, focus ultrasound-induced blood-brain barrier disruption achieved a higher delivery efficiency to the brainstem compared with intranasal only and IV only. But then what was surprising is we found fusing achieved 1 order of magnitude higher delivery efficiency than the fast BVD. We're still trying to repeat the study and trying to further validate the results. And then we look into systemic exposure. So we harvest all the major organs and look at the fluorescent intensity. And then as we expected, fusing similar as IM delivery, we only see enhanced fluorescent intensity at the stomach and intestine. Well, for fast BVD and IV, you can see the fluorescent intensity in all the major organs. And then we did a quantification of the gold concentration. So this is a plot of the percent injected dose per gram of tissue for all the blood and all the major organs. And then, so the blue color is the fusing, yellow color is fast BVD. As you can see, for fusing, we only see higher gold concentration in stomach and intestine. The reason is because the nanoparticles were given to the mouse using liquid drops. So the nanoparticles were swallowed into the digestive system, to the stomach and intestine, and over time it can get out of the animal body. And then we look into the potential mechanism. So the first thing we did is we harvest the nose tissue and the trigeminal nerve and did fluorescent imaging. It clearly shows fusing delivery goes through the nose to brain pathway. And then because there's enhanced fluorescent intensity in the nose and the trigeminal nerve, and the fast BVD, as we expected, there's no fluorescent intensity, enhanced fluorescent intensity in the nose and the trigeminal nerve. And then we also quantified the gold concentration, so consistent with the fluorescent results. For the fusing delivery, we have higher gold concentration in the trigeminal nerve and the nose. And then for the fast BVD, which is IV delivery, we have high concentration in the blood. So it clearly shows the two drug delivery technique uses different drug delivery pathway. And then we also see these are some our preliminary work where we take the brain and then cut into slices and then do the fluorescent imaging. So this is a control slide. So we have 50 labeled dextran injected through IV, which highlights the blood vessel. And then we have the fluorescent labeled nanoparticle given through intranasally, and then apply focus ultrasound. So what we found quite interestingly in that, so this is the blood vessel highlighted by the green color, And then you see there's surrounding the blood vessel, in the perivascular space, you see the red color. That's the nanoparticle, the fluorescent label nanoparticle delivered intranasally. And then we also see the red color in the extracellular space. So which kind of align with our hypothesis that the intranasal, the minutes nanoparticle distribute along the perivascular space. And then the focus ultrasound technique may enhance the penetration of the nanoparticle from the perivascular space deep into the extracellular space. We're still trying to do more of this type of work, trying to understand the drug transport in the brain when we apply fusing technique. Okay, so to sum up, so I think I hope I did a good job to show that fusing is a promising drug delivery technique that can potentially have high delivery efficiency of the gold nanoparticle to the brainstem, and also can minimize exposure to major other organs. So our ongoing work is to evaluate this technique using a mouse model of DIPG, and also to try to understand the mechanism. Another work that I did listed here, because the big concern is how this technique can be translated to human. So another part of the work that we're starting to work on is to use a pig model to see whether similar enhanced delivery can be achieved in large animal model. Okay, I want to thank my group. So this work, most of the work is done by my student Summer, and this work is in collaboration with our pediatric neuro-oncologist, Josh Rubin. I also want to thank the funding support.
Thank you very much, Dr. Chen. So any questions for Dr. Chen?
So what's the usual distance of the transfer of the nanoparticles out of the perivascular space to the focus ultrasound? And how can you relate it into the clinical scenario where you have quite significant tumor volume to cover with
Yeah. So how far the nanoparticle penetrates compared with a nearby blood vessel, that's actually something we are trying to quantify right now. But in terms of covering the whole tumor, because focus ultrasound has the advantage that we can raster scanning different brain areas. So we have the possibility to contour the tumor and then cover the whole tumor. So
sequentially cover the tumor with.
Yeah, so we can move the transducer around or steer the beam around to cover the whole tumor. That's one of the unique advantage of focus ultrasound drug delivery is we can actually contour the tumor to achieve drug delivery to fit the shape of the tumor.
And what happens to the nanoparticle in other brain regions?
Yeah, that's a good question. So the nanoparticle will also reach other parts of the brain region. At the end, our goal is to achieve enhanced delivery to the tumor while keep the amount of agents that the other parts of the brain below the therapeutic level.
Okay, let's thank Professor Hong, Professor Chen for her talk. Okay, the final talk, hand-picked by the symposium organizers to be the very last talk of the symposium, no pressure, is Targeted Drug Delivery in the Nervous System with Ultrasonic Proton Caging by Raghuram from Stanford University.
All right, thanks everyone, and thank you for the organizers for inviting me here, and thank you for sticking it out to the bitter end. My name is Raghuram. I'm a neuroradiologist at Stanford, and working on the technique of ultrasonic drug caging. First, I'll have an equity in a couple of Bay Area startups, which have no direct relation to this. So I don't need to explain to everyone again why we might want localized neurointerventions. What I will say is what I'm focused on is enabling more non-invasive interventions. So to enhance the penetration of whatever technology that we develop into further clinical applications. And the main thing I'm mostly focused on is to do targeted drug delivery. The idea that there's a lot of drugs out there that we have efficacy for. We know that they're efficacious, but what's really limiting for their use more generally in applications is their side effect profile throughout the brain as well as in the body. And so for many different applications, what we really want to do is, continue to give them systemically, but have these agents only act in a particular region of the brain or body. And if I were to identify kind of more generally the ideal technique for a non-invasive neurointervention, it would be able to target any region of the brain or the nervous system with clinically relevant spatial and temporal resolution. By that I define clinically relevant being on the order of a few millimeters at least, because that's the order of which we know that different functional brain regions or different parts of the tumor might change. And temporal resolution on the order of seconds, because that's how long it might take to ask the patient a question in response to the intervention. They, of course, have no off-target or permanent non-therapeutic side effects. So ideally, whatever you're doing would just act there and have no other action other than the thing that you want it to do. Be image guided to account for anatomic variation that we know each person has. And if the goal is to modulate neural activity, you would want this thing to be able to have a robust and predictable underlying mechanism of action, whatever you're going to be doing, and adaptable to the variety of signaling methods that the brain might use, excitatory, inhibitory, or neuromodulatory. And I say a lot of this because I think focused ultrasound gets us most of the way there, because we have FDA-approved hardware that can target any brain region transcranially, non-invasively, with millimeters and millisecond scale spatial and temporal resolution. That can be image guided with either real-time MRI or neuronavigation. To support this idea, there's a simulation study did when I was still at Hopkins, where we simulated using a transducer that we had on hand, which can designed for uterine fiber ablation. So not even designed for neural applications, but with that transducer, in principle, we can target any brain region we want. These white boxes overlaid onto a real human's CT scan are each 1 centimeter on edge, and the red squiggles are the full width half max. And we see that with this transducer, we can, in principle, target wherever we might want with millimeters of resolution. The only issue especially for the question of modulating neural activity is how we might get ultrasound to have a robust, predictable neuromodulatory effect that is versatile enough to modulate a variety of things that we might want it to do. And for that, turn to this field of ultrasound-mediated drug delivery. And the idea is that if you have a particle that can be loaded with a given drug and then administered to the patient systemically, ultrasound, the drug will stay inert as long as it's bound in the particle. And if ultrasound can induce release of the drug from that particle, then the drug would have the desired effect that you might want only at the sonic phase site, with a robust pharmacologic neurointerventional mechanism that can be easily adopted into the modulation of whatever receptor system you have, given the libraries of compounds that the pharmaceutical industry has developed to be so targeted. So in an eventual application, a patient would receive an intravenous infusion of these nanoparticles. They would undergo an image-guided transcranial focused ultrasound treatment. That ultrasound would induce intravascular drug release, and then the drug would cross the blood-brain barrier on its own to have its effect in the brain. Or if you're talking about the peripheral system, you wouldn't have the blood-brain barrier to even worry about. So thus far, we've made such nanoparticles. Our nanoparticles are composed of 3 ingredients that have already been given to humans in different forms. There's a biodegradable polymer, PEG-PLGA. We chose PEG-PLGA after doing a screen of different polymers, and chose it because everyone uses PEG-PLGA, and so it's been used for there's quite a history that we can piggyback off. as we're looking towards clinical translation. And B, it was actually one of the best performing polymers when we did our screen. The second ingredient is our drug of interest, and we're right now focused on reformulating known and utilized drugs. And I'll go over some of the drugs that we put into our part in a minute. And then the third ingredient is a nanoscale droplet of perfluoropentane. Perfluoropentane is a perfluorocarbon that's been used in a variety of ultrasound contrast agents, as well as potentially designed as a blood substitute. And so it has its own case file with the FDA for its use in intravenous delivery. The PFP is the business end of the ultrasound sensitivity. Under the action of ultrasound, that perfluoropentane expands or deforms. That induces porosity in the polymer layer with that deformation. And that porosity is what allows the drug release to come out. The drug then after release, crosses the intact blood-brain barrier to act in the brain. So far, we've established a clinically translatable production pipeline for these nanoparticles, and established their safety and tolerance in rat studies. And we're now working to go to the next level with large animals. So right now we've shown that as long as the drug is hydrophobic, we can put it into these particles, essentially. We've encapsulated anesthetics, psychedelic, chemotherapeutic, and cardiovascular or vascular vasoactive agents. And I'll say that we've, in addition to anesthetics to act on the brain, we've also encapsulated anesthetics to act in the peripheral nerves. Everything else about the particles stays essentially the same, whether it's their biodistribution, the particle clearance kinetics, and the profile of drug indication from it. And I'll say that they last in circulation with a half-life of about half an hour. That's often popular. To assess the temporal resolution for the drug release, we use propofol, which is a general anesthetic that essentially shuts down brain activity if it gets put onto the brain. Propofol acts quickly and spreads really limitedly in the brain. So it's a good model drug, if you will, to assess the spatial and temporal resolution of RFP. And it also has a nice functional assay in that we just have to look at the amount of brain activity as a readout of where the drug is. So to assess the temporal resolution, we use this assay where we flash the light in the rat's eye and measured electrophysiologically the potential that was generated by that light flash from the rat's occipital cortex. And then we applied ultrasound to either the primary visual cortex, V1, M1, the primary motor cortex, as an anatomically and functionally distinct control region in this visual assay, as well as the lateral genicular nucleus, LGN, which is a relay nucleus in the visual pathway. First, note that in order to affect this assay, we needed, for free propofol, we needed at least 2 milligrams per kilogram IV bolus in order to affect this potential. 1 milligram per kilogram on its own didn't do it. But nonetheless, if we gave 1 milligram per kilogram of the encapsulated, nanoparticle encapsulated form, when we applied ultrasound with those propofol loaded nanoparticles on board, we saw an immediate drop of that potential, indicating an anesthesia of that activity that was not seen with just blank vehicle-only nanoparticles. Again, so if we applied the ultrasound alone, we see no particular effect. If we give the bolus of nanoparticles on their own, there's no particular effect on the potential. But with the ultrasound and the nanoparticles on board, there was an effect. The effect showed a dose-response relationship with the applied ultrasound intensity. We first did not see it with blank nanoparticles. We also did not see it with the low intensity of the ultrasound. But as we raised the ultrasound intensity above threshold, we saw this deflection in that potential that deepened as we went further up. Quantifying that, we see dose-response relationships with the applied ultrasound pressure and burst length. And we also saw specificity with where we were sonicated. So if we sonicated in the visual cortex, we saw our effect. If we sonicated in that relay nucleus in the lateral genicular nucleus, we saw our effect. But if we sonicated our negative control region, the motor cortex, we did not see our effect. The effect half-life, this is now the temporal resolution. So first we noted that the effect turned on as as soon as we started our pulse sonication and recovered as soon as we stopped the sonication. While the effective half-life itself was around 10 seconds, which we know is the rough pharmacokinetics of propofol itself. So our model, at least temporally, is that the drug is on, if you will, as long as nanoparticles are on board, the ultrasound is on, and then also determined by the usual pharmacokinetics of the drug itself. To look at the spatial resolution, we used PET, the same FDG, the glucose analog metabolic PET that we use clinically, except with a much smaller scanner fit to the rat. And we saw that with blank nanoparticles, we saw no particular effect of sonication during the sonication. But with the propofol-loaded nanoparticles, we saw a dropout of metabolism, indicating anesthesia, limited directly to the zone of where we're sonic, indicated by the full tap matrix, which is indicated by this oval. When we turned up the intensity of that ultrasound to kind of max where we were willing to go, we saw that we filled out more, that anesthesia zone filled out more of the ultrasonic focal zone, but did not bleed over. Quantifying that out, we saw that we actually had the effect of the propofol was limited to the ultrasound focus, and that we actually had a dual kind of control of the spatial profile of the effect. If we turned up the intensity of the ultrasound, we increased the amount of the brain that was affected by the propofol, but we actually didn't increase the depth of the effect. Whereas if we increased the timing of each ultrasound pulse, we deepened the effect itself, but we didn't increase the spatial profile of it. Modeling this out, we see that there's an effective in vivo threshold of about 1 megapascal, which is well achievable by usual focus, by clinically available focused transcranial focused ultrasound systems. So essentially, from the electrophysiological assay, the drug seems to act only when we apply an ultrasound. And with this assay, we see that the drug only acts where we apply an ultrasound. As a separate application, we put drug nicardipine into these particles. So I'll say that part of why we chose propofol is that clinically we do something called the WADA test, where we thread a catheter to the enterocarotid artery and infuse anesthetics like propofol to assess left versus right functional region localization. So as an analog of that, you consider the nanoparticle kind of ultrasound technique that we have developed as a focal version of the WADA test. One additional thing that Monica does is infusing nicardipine to treat cerebral vasospasm for patients post-subarachnoid hemorrhage. And we thought that nicardipine would be another good application, potentially non-invasive version of that catheterization. But B, this could also test the localization question. Because one potential criticism was, well, what happens to all the other drug that got released and say didn't enter the brain? Isn't that just going to have this huge systemic effect elsewhere? So we did this assay because nicardipine only has to act on the blood vessel itself. It doesn't even have to get into an end organ. And B, if there is a systemic effect, we'll definitely be able to see it. So we did this. We made nicardipine particles, and we looked at the rat's aorta, which is the highest flow vessel of the body, where it would be most likely for the drug to just go downstream. And first, showing that, nicardipine acts by relaxing the vessel smooth muscle, so the compliance of the vessel wall increases. And so with each pulsation, if it's effective, it should increase the degree of the vessel motion. So this is an ultrasound image of the rat aorta. And I'll say that in first position, we applied ultrasound immediately upstream of where we're imaging. And in a control experiment, we reversed those positions. So in the this position, before, this is with the nanoparticles on board, before the engaging pulse is applied, we see that, this aorta is pulsating a little. But after we apply the ultrasound, we see that, or at least to my eyes, that the vessel motion, the walls of the vessel are moving quite a bit more, indicating that nanocarpine is having an effect, at least in the aorta downstream of where we engage. If we quantify that out, so we saw no particular, so with just free nanocarpine, the same dose as what we gave the encapsulated form, we do see an effect. But that with our encapsulated nanocarpine and encaging strategy, we do see our effect. That effect is actually even more than what we saw with a matched dose of free nanocarpine, indicating that the volume of distribution of nanocarpine was restricted. We didn't see that with light nanoparticles. We didn't see that with the nanocarpine particles on their own. We didn't see that with ultrasound on its own. And most critically, we didn't see that when we just reversed the position of the transducers. So the same amount of ultrasound, so the same amount of nanocarpine is presumably getting out of the particles, but there's actually no particular effect on the vessel pulsatility, indicating that whatever systemic amount there was getting out, just going downstream, at least wasn't enough to affect that aorta just a few centimeters away. This effect turned on within just a minute of this ultrasound, pulsing, underlying that, how fast this is happening. And then as a further argument about the localization, this is going to go back to a bit of physiology, so bear with me for a bit. But one way that you can look at, when nanocarpine is acting and it's relaxing that smooth muscle, it's going to drop the vascular resistance, the resistance to flow. That's why nanocarpine is an antihypertensive. It drops the systemic vascular resistance. When you drop resistance to flow, you increase the velocity in the vessel that's feeding that resistance. And certainly with systemic free nanocarpine, we see that the aortic velocity increases. And when we are uncaging just downstream in the lower aorta, and all that nanocarpine is getting out into the legs, we also see that velocity. But when we're uncaging in the upper aorta, we don't see that velocity increase. Indicating that even though the rat's blood flow is about 0.5 meter a second, and the rat's whole aorta is only about 5 centimeter difference, we at least have that degree of localization of our drug effect. So our next steps right now is we're developing new ultrasound systems that are better suited to this technique of ultrasonic drug encaging, both for preclinical as well as clinical purposes. We're developing out all these different applications, whether they're in the neurologic psychiatric space, within the cerebrovascular space, or in the oncologic space. And we're doing what we can to move to first-in-human trials. We've already identified a regulatory strategy with our FDA consultants and partner GMP CMOs as well as GLP CROs. And as long as we can raise funding, we're targeting a first-in-human trial in 2 years. With that said, I'll wrap up and just say we think that this technique of ultrasonic drug encaging is a safe and versatile tool for non-invasive modulation of the nervous system. The bioeffects of the drug encaging are limited by the spatial and temporal extent of the ultrasound therapist, as well as the properties of the drug itself. So that's about 10 seconds for the case of propofol, and about 1 megapascal threshold for that we've seen in propofol encaging. And we're hoping for a first-in-human trial in 2 to 3 years. For that, thank you very much to funding agencies, all the folks in my lab who are actually doing all this work, and thank you for listening. And very good.
Any questions?
Yeah, so a great talk. I know some of it before. So it looked like at 650, very technical question, because you're using really relatively high acoustic pressures, and I was wondering about the mechanical index that you're getting with those pressures. We treat, some of the data shows we're treating with a frequency that's twice as high and using pressures at 1/4 lower. So typically you would expect that
Using pressure, wait. So you're using pressures that are twice as high? And
no, you're using frequencies that are twice as high, pressures that are 1/4 where you were using, or 1/3, let's say. So our mechanical index was substantially lower than that. And those were pretty close to what we detected as being at the safety level. I was wondering what you would see
So how are you defining the safety level?
Well, because mechanical index is the pressure divided by square root of the frequency.
I mean, all I can say, I mean, we've done MRIs, histological evaluations, and we haven't seen any microhemorrhage or fractionation of tissue or.
You did SWIs and scars.
Correct. Yeah, I have.
No, you don't have to show me that. I know where you come from. It's done right. It just seems. Anyways, we should probably talk about this offline. But I'm just saying, it just seems better. And then the other question in terms of the clinical translation. So I know everyone at the FDA that the ultrasound work, and I saw them on their research program. They are not anywhere near having something injected into the brain and being treated, and especially an agent that has another agent inside. They're taking their time now, just allowing for gadolinium to be injected, or maybe therapy injected afterwards. In terms of drug interaction between your ultrasound energy and the agent that you have, I mean, that's something. I mean, I can tell you for the application for transdermal blood relief, very low applications in skin, and this is Bob Langer's group, they essentially created so many issues for them that they had to agree in the end to first treat and then apply the agent. We're talking about very simple agents in the skin, the extremely low non-focused exposures. Again, I don't want to rain on your parade, but I'm telling you the odds of anywhere within years and years from now, for them administering an agent into the brain, some kind of psychoactive agent that can affect drug activity, and then having you treat it with relatively high ultrasound energy. And I mean, the burden of proof is going to be on you to show that no interaction between the two, no modification of your drug. I mean, it's a long way from getting approval in terms of having an application being done mainstream patients.
Oh yeah, well, I mean, mainstream adoption, for any of the things we're talking about the past couple of days.
A decade or more. Again, just from the reviews that I've seen and being familiar with the board there and the approval there. So again, it's just a comment that I know personally the transdermal delivery stuff is that one of the guys who was on there was on my PhD. That's the kind of those are the kind of issues that he was.
I'll say, perhaps blissfully optimistic until they.
I mean, it's a great application. Don't get me wrong. I'm just saying that I also know Graham's trials and tribulations to get a chemotherapy study done. And there again, you're injecting the agent after the treatment. Very wary of interaction and drugs, especially.
Okay, there's no more questions.
So thank you very much again that you stayed so long. I think that all sessions from the morning of the yesterday till to the afternoon were really great. There was the webinars and the keynotes were really highlights of this event. So one more time, thank you very much. We didn't have time to have the business meeting because there was so much stuff going on here scientifically, and this part we can still accomplish through Zoom in near future. And then at this meeting we will decide where we will go further about the journal, the next place for the meeting. Obviously, it would be the best way would be to alternate the continents, because it's always from the one continent is most of the people. So it would be great to get with the message to new people. Okay, and then I know that we have also a lot of publicity on online, and I know that Dr. Brem got even the congratulations from from Israel, so definitely people from all over the world were participating in our meeting. So again, thank you very much. And now giving the mic to Roman, who will say a couple of words from CPTDC. And that was really essential to do this meeting together and then to bring on our side and on the side of CPTDC people was a really excellent amalgam of topics. So one more time, thank you very much. And then Roman, hello.
Just Mirek, just as you said, thank you to Simon for inviting the consortium to join this meeting. It's very clear in the field of drug delivery, we really underappreciated neurointerventional and imaging for confident on drug delivery studies. So it's something probably going forward when we can discuss future sign meetings, whether we remain as a joint partner, because we'll certainly be a funded consultant for a further 3.5 years. So certainly scope to host a similar meeting on this again. So thank you very much, Mirek, Pietro, and Mike, particularly for organising this meeting. It's been tremendous. Thank you.
I will not hold you much longer, but I have to say something. There was a lot of work with preparation of this conference, and quite a few of people contributed. But if we gauge the effort in preparing all of this, I think we could divide it 20 to 80. 20% of effort was by many of us, but I think 80% of effort was by Mirek. He definitely spent a lot of his time, and what he did was tremendous. So thank you very much.
The message again that I already talked about it is to use this meeting as a real way to make real collaboration. And Mirek, we'll have you work on our website also to